Yes, sir.
Sir, yes, sir. I'm ready. Good morning to one and all. On behalf of Department of Science and Humanities, Nehru Institute of Engineering and Technology, I welcome you all for the CSIR sponsored 2 days national level seminar on state of the art and future perspective of hybrid supercapacitor for greener environment. We are much elated too in sharing that this is our fifth CSIR sponsored national level seminar. We have successfully completed 4 CSIR sponsored seminars in the field of physics, chemistry, and mathematics. One of the marvelous things about community is that it enables us to welcome and help people in a way we couldn't as individuals. With this beautiful quote, I invite Dr. Shalini Pakyam Kamala, Professor and Head, the Department of Science and Humanities, to welcome all.
Respected Chief Guest, Honorable Principal, Dr. Periyasamy, Coordinator of the program, and all the faculty members and participants, a very pleasant morning to you all. This is a scenario where everywhere we search for the alternate for fuel. Though science people give a lot of reasons for it in terms of global warming or pollution and all other terms. But even nowadays, it is the concern of the lay people because of the cost of the fuel. So when we go for the alternate, lot of researchers are going on in that. And here, Dr. Periyasamy is interested with supercapacitor, and the topic he is directly related with greener environment. So it is much more special. Having great concern over the environment, the topic is designed and giving awareness over it is really very much appreciable. With a great appreciation to Dr. Periyasamy, assistant professor and coordinator of this program, let me give my welcome address. Let me first of all welcome our trustee, Dr. Advocate Dr. P. Krishnadas, and the Secretary, CEO and Secretary, Dr. P. Krishna Kumar, in their absentia. And it gives me immense pleasure to welcome our principal, Dr. P. Maniyarasan sir, who's a person always who drives us, who's behind us to make us to come forward in all the aspects. Especially in terms of research, his role is remarkable in the Department of Science and Humanities. Though it is the fifth program, fifth CSIR sponsored seminar, it is because of the interest he showed on the department, we try to reach it. We welcome you, sir. And I'm very much happy to welcome our senior scientist, Dr. M. Satish, Electrochemical Power Sources Division, CSIR, Sikri, Karaikudi. Actually, many of the reputed faculty members, welcome, sir. Many of the reputed faculty members and few students, they are very much interested to hear from you. Making us this very statement, they have changed their time here and they have joined. So we are also very much eager to listen from you, sir. Welcome to you, sir.
Welcome.
And it's a great pleasure to welcome all the faculty participants who are having special interest over this. Your research interest should be really appreciated, and a very special note of interest to the student participants who have shown your interest towards it, and you spend time for it. And I appreciate and Dr. Periyasamy sir again, and I welcome all the faculty members of NIET and other department faculty members. Thank you. Welcome you all. Thank you.
Thank you, ma'am. A successful person finds the right place for himself, but a successful leader finds the right place for others. May I now invite Dr. P. Maniyarasan, our beloved principal, Nehru Institute of Engineering and Technology, to give the presidential address. Sir.
Thanks, madam. Most respected Chief Guest of the Day, Dr. M. Sadish, Senior Scientist, Electrochemical Power Sources Division, CSIR, Sikri Karikudi, and our respected HOD Madam, Dr. Shalini Madam, and the coordinator for this event, Dr. Perisami Sir, and all the faculty members, participants from the various institutions, and research scholar. Very good morning to one and all present here. First, I would like to thanks my sincere thanks to our chief guest, behalf of our management and faculty member. In spite of his busy schedule, Sir has accepted our invitation. He will be going to give the speech in the area of the supercapacitor. Behalf of management and faculty member, our heartfelt thank you, sir. My sincere appreciation to the S&H department, Science and Humanities department. This is the 5th program. They are periodically getting the fund from CSR, regularly conducting. So that is really appreciate the effort made by the HOD madam and the coordinator Dr. Perisami sir and his team members, everyone taking the pain and strain, organizing even for them, all the people. The topic today we are going to discuss that CSR sponsored 2 days national seminar on state of art future perspective of hybrid supercapacitor for greener environment. Really, that is a current topic for the all engineers or research scholars. We are seeking the power shortage. We are getting the power from the conventional source of energy that will be going to exhausted in again maybe the short period of time. We are looking for the alternative energy, electrical energy, hybrid, and so many things. But storing energy, that is a big task. The storing energy, because the AC current we cannot store. We can convert it to the DC form. We can able to store it with the help of the batteries and the electrical vehicle. The heart of the system is the battery, the capacitor. Now we are talking about the supercapacitor. Capacitor, everyone knows to store the electrical energy. Maybe that supercapacitor, that is a latest topic that it speaks about it store the energy for a longer period. Because I am a mechanical man, the eminent speaker will be going to deliver the speech in the area of the supercomputer. That right person, I'm also waiting for that. But every engineer, every research scholar keen on that. Maybe everyone knows that now China is facing this shortage of the power shortage. Due to that, we are always, our automobile sectors are depending on the electronic components sector, that sensor, everything we are procuring from the China. Now 5 lakhs vehicles are waiting to get the sensor. That everyone knows that, because the Australia refused to give the coal to the power sector. Normally the power plant always running with the help of the conventional system, the thermal power plant. The coal is the main part of the system. So due to that, we are facing that. World is facing the critical problem. Maybe in another 3 months, if the power shortage will continue, maybe the vehicle cost will rise. So this is a time we have to think about the supercapacitor. We have to how we can able to store the energy for longer period. If can able to store the energy from the lightning, you can store we can give the electricity for the 200 or 200 villages for a longer period. In that way, we have to think. So I don't want to take a long time. Anyway, my sincere appreciation once again goes to the organizer, meticulously arrange the program for all the engineers, all the research scholars. Once again, my sincere appreciation goes to them. My request to all the participants, because eminent person going to deliver, because maybe the eminent scientist waiting to deliver the speech, maybe SAR is working in that area. So we are going to get the thing. So this type of the seminar and all, it is a forum we can able to interact and discuss and find the new things. Always we are moving from known science to unknown science. Known science is only 5 to 10%. Unknown science is more. So that space we have to reduce interacting the eminent people during this type of seminar. Once again, my sincere thanks to the chief guest, organizer, and thanks for the given opportunity. Once again, utilize the opportunity and do the best for our nation. Once again, I wish you all the best. God bless. Thank you.
Thank you, sir. No person was ever honored for what he received. Honor has been the reward for what he gave. Today we have a great personality from CSIR Sikri Karaikudi as our chief guest for our inauguration ceremony. Dr. M. Satish received his PhD in chemistry from IIT Madras in the year 2006. Then he moved to National Institute for Materials, Japan for 3 years as a postdoctoral researcher from 2006 to 2009. He joined as a JSPS Research Fellow at Tohoku University, Sendai, Japan in the year 2010. In April 2012, he joined at CSIR Central Electrochemical Research Institute, Karaikudi. Currently, he is working as a senior scientist in Electrochemical Power Sources Division. His research is focused on the development of advanced materials for energy conversion and storage. He has published 152 research articles in reputed international journals, 6 book chapters, 150 plus conference presentations, and 2 patents in his credits. He has H-index of 38 and total citation of 5,900 as of September 2021. He has guided 4 PhD students, 4 students are pursuing PhD, and he has guided several MSc and MTech students' projects. With this brief introduction, now I would like to invite our today's chief guest, Dr. M. Satish, Senior Scientist, Electrochemical Power Sources Division, CSIR Sikri, Karaikudi, to deliver the inaugural address. Sir, please.
Very good morning to one and all here. First, let me express my sincere thanks to the principal and head of the Department of Science and Humanities, as well as all the faculty members involved in the program. A special thanks to Dr. P. Priyasamy for his constant effort. From the right beginning, he has contacted me maybe 4 or 6 months before itself. So for this kind of program, and then even for before applying the program, he contacted me, and then constantly is updating me the progress of this proposal. So I thank entire people of Nehru institutions for their support and giving credit to me to inaugurate this program. Also, I should congratulate all the organizers and then the people involved in this program for selecting such a wonderful topic, which is a need of the hour. Okay, so since the entire country is moving towards green and sustainable energy storage systems, supercapacitor is one of the system which is not avoidable. Particularly for if you talk about electric vehicle or high power equipments operation, then the supercapacitor is very essential. Nobody can deny on that. Maybe I have more. I will be more convenient if to talk to you when I have the slides in my presentation. So maybe I take this opportunity to thank the Nehru Group of institutions, and particularly Department of Science and Humanities, and then the department and Dr. Periyasamy and other faculty members for giving this opportunity. I also thank other faculty members or invitees and the students from other institutions who are ready to spare their valuable time to listen for this 2 days program. And then one more thing I want to acknowledge here or appreciate the team that they have find excellent people. I have seen the list of speakers, so they have find very excellent speakers. Almost they are all are pioneers in this area of supercapacitors in different aspects. So in that way, I think this end of the 2 days program will be a very good feast for you to understand from the top to bottom as well as the entire spectrum of supercapacitors. Supercapacitor may be a very small area of energy storage, but even if you go there, and then there are a lot of things can be done, and then there are so many other opportunities also available. I think the speakers list which you have selected all are pioneers in different aspects. So I hope that at the end of the 2 days session, then you will be you will be much expertise in this supercapacitor area. So please don't miss any talk for the next 2 days, and then really it will be helpful for you. So with this, I thank one and all one more time for the Nehru institution for this opportunity. Looking forward to talk to you on the first session. Yeah. Thank you. Thank you.
Thank you, sir. Gratitude is when memory is stored in the heart and not in the mind. I would like to invite Dr. P. Perisamy, Assistant Professor of Physics, to propose vote of thanks. Thank you, sir. Dear participants, now we shall move to the first technical session 1 by our today's guest. Now I request Dr. M. Satish, Senior Scientist, to take over the session.
Yeah, thank you, ma'am. Just a minute, I will share my slides.
Yes, sir.
Can you able to see my slides, right? Okay.
Yes, sir.
So, very good morning to one and all here. Before going into the talk, I once again thank the Nehru institutions, the founder and principal, as well as the head of the department, and the organizers, Dr. Perisamy and his colleagues, also other invitees from the different colleges and research scholars. So as I told you earlier, my talk will be very fundamental on this supercapacitors. Since you see the list of speakers, all are expertise, having a lot of expertise in this area. So maybe I'll just give very brief introduction about supercapacitor, how it works, or where it needs, where it is badly needed, and what CSIR SICRI is doing it. But I hope the other speakers also will talk their own research as well as their perspective on the supercapacitors. But by end of this 2 days program, then definitely you will be get well versed in these supercapacitors. So I'm coming from this CSIR. I'm sure that all of you know that even this program is sponsored by CSIR. So I thank once again the CSIR for the funding as well as for giving support for all of us for conducting such a program. So under the CSIR, there are 38 laboratories. Each laboratory has its own unique agenda. For example, this particular lab is focused only on this electrochemistry-based research. The name itself, you could see that Central Electrochemical Research Institute. So that deals with all kind of electrochemistry. So similarly, there are other labs which are deals with some different aspects of chemistry, physics, engineering, or biotechnology, biology, or whatever it may be. So we have a Central Food Research Institute (CFTR) in Mysore. We have a Central Leather Research Institute in Chennai. We have National Physical Laboratory in New Delhi. We have National Chemical Laboratory in Pune. Similarly, there are various laboratories for each specific applications. So this particular lab is mainly focusing on the electrochemistry, not related to only chemistry or physics. You can see we have 6 different departments. So each department has its own agenda. For example, the corrosion and material production mainly involves how to protect the corrosion in the marine environment or the concrete structures or in the kind of bio environment. So wherever the corrosion occurs, or they will give some suggestions, or the consultancy, or they will also give some kind of production by through having some kind of corrosion, anti-corrosive materials. So here we involve both civil engineers or electrical engineers or maybe structural engineers. All these people comes in this category. And then the electrochemical power source division, I belongs to this particular division, where we are doing on various R&D activities on energy storage systems, like fuel cells, or like your lithium-ion batteries, or lead-acid batteries, or supercapacitors. So there are some new upcoming systems like redox flow batteries, or lithium-air batteries, or aluminum-air batteries. So these all are upcoming batteries. So wherever you any kind of batteries, people are working on this division. Similarly, when you're coming to electroplating and metal finishing, you can see this is a purely metallurgy related research. But here the common point is the electrochemistry. So we use electrochemistry to plate metal, or we extract a metal from this ores. So that's why this even there's it's a metallurgy department, but we are deal with electrochemistry. So we have electrochemical process engineering division, such as, for example, industrial dye effluent, or your desalination of water. All this process can be taken care by this department, where once again there is involvement of chemistry, physics, as well as engineering people. We do have a conventional divisions like organic and materials electrochemistry division, but the point is here we are not like any conventional organic chemistry synthesis or material preparation or all these things. So okay, here we work on electrochemistry based or electrochemistry induced organic transformation or organic reactions. Similarly, the materials which are being used in any of these areas in electrochemistry will be developed in this particular division. We do have a electrodics and electrocatalysis division, where people are working very fundamental development of new catalyst system as well as the materials, and then they will do the core research on this electrochemistry for different applications. So I'm sure by seeing all this department, you can understand this. We are not only we require any chemistry or physics or engineering people. We need a combination of all the people. So before going into this talk, maybe I can also take one more slide on this. Then maybe for some of you or some of your students or friends, it may be useful. We used to entertain MSc, MPhil, and ME and MTech students for their final year projects. So either in chemistry, physics, or nanoscience and technology, or material science. So all these, even these engineering areas, selected engineering areas, we can have the students in our campus. So basically, it will be 3 months or 6 months or even up to a year. They can stay at CSR Secretary. They can do their final year dissertation work. So of course, there is a selection process. So it has to, application has to be submitted through proper channel, that in the sense through your research kit, and it has to be forwarded by the head of the department or institution to our institute. Then they have a selection based on their eligibility. Then they will be allowed for staying here. Of course, they have to pay some nominal charges for their based on their duration at CSR Secretary, but these charges are very nominal. So if some of you or some of your friends or students are interested, then maybe you can ask them to go to here. You can see that our website, www.secretary.res.in, where you can see academics under this there is a guidelines for application for the dissertation work. Basically, we have two deadlines. One is will be in the November, the other one will be in the March, so that the people will be accommodated both in the winter as well as the summer season. So you can spread this information to other colleagues or students. Coming to my research group, we are working on various aspects of material science. And though I claim that is MBA electrochemistry, but mostly our group is working on various materials development that is useful for electrochemical energy storage application, very specifically on supercapacitors. Here we develop some 2D layered materials like graphene or MOS2 or a few layers of boron nitride. So all these kind of materials will exfoliate by using the supercritical fluid. We also synthesize some oxides or sulfides by using supercritical fluids, and then we'll use for either battery application or supercapacitor applications. We do very core research on Fullerene self-assembly, where we use liquid-liquid interface to assemble this particle into different morphologies. But coming to this last part where we are working on carbon-based materials for supercapacitor applications. So all of you know that the renewable energy sources are badly needed these days. Since our conventional fuel or conventional electricity or conventional energy we are getting from coal or diesel or petrol, whatever it may be, that is keep on depleting, and then people are now looking for alternate sources. So not only the depletion of the conventional fuels, in addition to this, there are a lot of carbon dioxide emission already. There is a lot of issues in the world. People are trying to reduce how to reduce the CO2 emission in the environment. When you use a conventional fuel, obviously either directly or indirectly you have to produce CO2 or some nitrogen compound or sulfur compounds that ultimately affect your environment. Coming to the renewable energy sources, there are a variety of sources. So for example, some of the sources which we are enjoying it. For example, the solar photovoltaics or solar thermal power, we are using this energy. But of course, this amount of energy which we are using is very, very small. And coming to wind energy, again, we have a lot of windmills, either in the southern part of Tamil Nadu. Even if you take a Tamil Nadu, whether in southern part of Tamil Nadu, or if we go to the western part of Tamil Nadu, you could see there are a lot of windmills. But the problem with the windmills are like you cannot increase the production. Even if that can be done, it's not a stable system. That is a major issue. The wind is very good in maybe for a few months in a year. Even within that few months, even within a day, there are a lot of changes. Fluctuations will be there. So it may not be a very constant source for producing electricity for our conventional needs. That is the issue. Similarly, for the hydropower, the last 3-4 decades, we are enjoying the hydropower. For example, the electricity comes from a Mettu Dam or Periyar Dam or such kind of small dams. We are producing electricity. But unfortunately, when you want to move all your energy requirements towards the electricity-based or sustainable energy sources, then definitely there is no possibility for improving these hydropower activities further. Since already there are a lot of issues on this water sharing or water availability. So this increasing this hydropower to further level may not be a big. I think that will not be a very good idea. So similarly, the biomass or ocean energy or waste to energy we are using in very remote areas. But the amount of contribution by these sources are very minimum. Also, for increasing to the next level for these sources is very, very difficult. The government is planning to convert all your conventional vehicle into electric vehicle. Okay, in such a case, we may need huge amount of energy. So that cannot be met out from these sources. So coming to solar, again, there are a lot of opportunities. Maybe I will show you some slides, then it will be conveniencing to you. So this is a primary global energy consumption in 2019, if you see the 33% comes from oil, and then the 24% comes from the natural gas, and then the 27% comes from the coal. So if you see the renewable energies is only 5%. That's a global data. If we coming to India, we are in much better position. If you see our global energy our Indian energy consumption is only 53 from coal, and then 35.9% from the renewable energy sources. So here we have only 5%. The renewable is only 5%, but India, as far as India alone, if you see, there are we have 35% of, or almost I can say 36% of renewable energy sources. After that, it's a 12% comes from the hydro, and then 10% comes from the wind power, and 9.6% comes from the solar, and then the bio and small hydro or waste to power are very minimal. Now, if you want to increase this renewable energy, then the best options are these three. So that large hydro, and then wind power as well as solar power. We discussed about this, how to what are the possibilities for increasing the hydro power based electricity or wind power based electricity. There are very limited scope, but one of the promising sources is the solar power, since the solar power which we are converting is most underutilized. Okay, so if you see again this data, then it will be very impressive to you. For the 1,25,000 tetrawatt solar energy strikes the surface of Earth. Okay, the global energy consumption is only 13.5 tetrawatt in 2001. Out of this, 85% comes from the fossil fuels. Only 15% is made out from this. But if you see the 2050 requirement, it's only 30 tetrawatt. Okay. If you convert 0.16% of Earth with the 10% efficient solar cells, already we can be able to produce 2/3 of our requirements. Okay, so that is the scenario, 2/3 of our world requirement. But at present, this solar electricity, we are already enjoying it, but the cost is the most worrying factor, since the cost of the electricity goes to the solar panels production. At present, we don't have any technology to make our own solar cells. We are particularly the solar cells are based on crystalline silicon-based materials. So though we have a lot of silica, conversion of silica into silicon is the cost involving process. So that's why this process of the electricity is very high. Also the efficiency, even if you see the global requirement is 10%, but what I can say is the commercial solar panels which we have in our hand is having more than 25% at least. In some cases even to 40%. So right now, it's the cost of the electricity comes from the solar panels are 2 to 3 times costlier than the conventional fuels. The electricity comes from the conventional fuel. But when very soon this scenario will change, in the sense maybe after 4 or 5 years, definitely these solar powered electricity charges will be much lower than the conventional electricity charges. Maybe now I hope that it maybe there you can understand there are very promising probabilities for having producing solar based electricity that in a very cheaper manner. But unfortunately, sun is not available in the night time, so we have to store the energy for our activities during the night time. Since you can see almost 1/3 of our requirement is the electricity we need in the night time also. In such a case, we have to look for some kind of energy storage system. In such a case, batteries or supercapacitors or hydrogen storage are some of the best available sources. The fuel cells and solar cells are not an energy storage system. They are theoretically or fundamentally, if you see, these are conversion devices. It will convert fuel cells convert chemical energy into electrical energy, where the solar cells convert light energy into electrical energy. But these cases in batteries and supercapacitors, you can store directly the electrical energy in the form of chemical. When you want it back, you can get it directly the chemical energy into electrical energy. But in between, I put a hydrogen storage. I take 1 or 2 minutes to just elaborate what is hydrogen storage, why people are interested on this. So if you see the energy density of lithium-ion batteries is only 0.54 megajoules per kilogram. Whereas the conventional gasolines or the petrol or diesel, the maximum is 46.9. Whereas the hydrogen is 120 megajoules per kilogram. If you compare with the batteries, the hydrogen is 220 times more energy density. Even for conventional battery, it's much better than the conventional fuel, where it can source 2.6 times much higher than the petrol or diesel. So these are the factors why people are recently started. Actually, the 10 years or 15 years before, hydrogen energy was booming like anything. But after some time, they moved into the another system, since there are a lot of issues in the hydrogen energy, even starting from the hydrogen production and hydrogen storage or distribution. So all these things has issues. So that's why they have moved away from the hydrogen. But recently they have realized that again the hydrogen is maybe one of the promising unavoidable source. So last 2 to 3 years, government is initiating a lot of projects and then activities towards the hydrogen-based economies. So not only hydrogen is a fuel, it is much better than the conventional fuels like methane or gasolines. So if you see some of the fuel properties, I don't want to go into the details, but in all these aspects, this hydrogen is much better or very equivalent to conventional fuels. So that's why the hydrogen storage and then hydrogen production and distribution is booming like anything. Hydrogen production through the splitting of water is another big area where we have plenty of water in the universe, but that could be converted into hydrogen. Since in atmosphere we have very small amount of hydrogen, less than 0.5% of hydrogen is available. So obviously we have to go for some sources. So coming back to here, the energy storage devices. So we have two options, as I told you earlier, the batteries and the other one is the capacitors or supercapacitors. Here there are two, you can ask me a question, why if you want to store electrical energy, why we need two different sources or two different devices. One is called batteries. Even batteries, there are different kind of batteries. I'm sure that you all are aware. There is a primary batteries, there is a secondary batteries, right? So under this, even the primary batteries and even the secondary batteries, there are different other kind of batteries are comes into the picture. But here the batteries and the supercapacitors are entirely different. Okay, I'll tell you. There are two many important aspects when you talk about energy storage systems, particularly electrical energy storage system. One is the energy density, the other one is the power density. Okay, so if you see here the power density of the capacitors or supercapacitors are much higher than the batteries or fuel cells. Whereas if you see the energy density of batteries and fuel cells are much higher than the conventional capacitors. Even for supercapacitors, this is a reasonably very high energy density. So I will tell you what is energy density and what is power density. Then it may be clear why people are looking for two different devices. Or you should have some device somewhere here. It may be a battery, or it may be a capacitor, or it may be a hybrid of batteries and supercapacitors. But that should give maximum energy density and maximum power density. So that for our practical application, we can use this. The battery, the energy density in the means how much amount of energy I can store in the device. Okay, so it basically depends on the quantity. Okay, how much quantity I can store in my particular device. So in the batteries, I can store a huge amount of energy when compared to capacitors or supercapacitors. So the power density it means how fast I can charge my device or how fast I can discharge the energy from my device. Okay, that's basically the rate of charging and rate of discharging of device. So the rate of charging of capacitors or discharging rate of capacitors are much higher than the batteries. Supercapacitors are nothing but the capacitors, but the energy density is improved maybe several times higher. So that's why we call it as a supercapacitors. People will call boost capacitors or ultra capacitors, different kind of names. But here mainly the difference between the supercapacitor and capacitor is the energy density is higher when compared to the conventional capacitors. So how this energy density is higher, that what we come to see, but they are following a different mechanism of charge storage. Maybe we will see in this coming slides. So what are the use for this supercapacitors? Why we need high power? For example, I make a car, okay, with some of these batteries are supercapacitors. The moment for example, if I run a car with only batteries, I want to go for 400-kilometer distance. If I charge my batteries for maybe 6 or 7 hours, I can make it 100% charge. Then so once I made 100% charge, then I want to travel, then I can cover 400 kilometers. There is no issues. But the problem is I cannot go more than 20 kilometers per hour speed. I can go 400 kilometers, but I can go only very slow manner. I cannot go maybe 80 kilometers per hour or 100 kilometers per hour speed. So here the rate of take, why the speed why I cannot go for high speed is I cannot take more energy from my batteries. I can take very slowly the energy from my batteries. Even if you reach the 400 kilometers, then if you want to charge the batteries again, you have to wait for another 6 or 7 hours to make it 100% charge. Or if you want to come back, again you have to wait for almost half of the day to charge your batteries. Whereas the supercapacitors are ulta. When have supercapacitor, even you can travel with the speed of 200 kilometers per hour. But you cannot go more than 4 or 5 kilometers, or worst case maybe 10 kilometers. After 10 kilometers, again you have to charge your device. But here the advantage is for charging you need maybe a minute or maybe 30 seconds or less than a minute. Again you are ready to go for 10 kilometers with the speed of your interest. Okay. Here the speed is not important. We can go very high speed, but only thing is the distance you can go only for few kilometers. So that since the energy, the total amount of energy stored in the device is very less. So that's why we need some device somewhere here so that I can go maybe 100 kilometers per hour speed with at least minimum 400 kilometers in a stretch. So that's what people working in batteries, they are working on high rate batteries so that the batteries can be charged very quickly or discharged very quickly. People working in capacitors or supercapacitors, they are working on this direction to increase the energy density without compromising the power density. So at present, the supercapacitors and batteries are having its own use. For example, in the case of race cars, the supercapacitors are needed to start the engine, and then initially 1 or 2 minutes your petrol or diesel engine will not reach a maximum speed. It needs maybe 1 or 2 minutes to reach. So during that time your supercapacitor will support. Since after that your supercapacitor will be completely discharged, so you cannot use it again. And not only that, in many cases we can also use for startup. So when you use a lithium-ion battery for your electric vehicle application, when you start the engine, you need a peak power. Okay, that cannot be taken from your lead-acid battery or lithium-ion battery. You can take it, but the problem is the life of this battery source goes down. So in such a case, your supercapacitor can be used. So also the regenerative braking system, I don't know how many of you are aware, when you apply a brake in your car, you can produce electricity. Okay, generally this electricity will be this energy will be wasted as a heat. But now we have a device that could convert this mechanical energy into electrical energy. So whenever you are applying brake, that means you are generating the excess energy into electrical energy. So that electrical energy can be stored in your supercapacitor device. So how do you see the market of supercapacitors? If you see 2014 to 2025, it's predicted for up to here, you could see this compound growth rate is 30%. Okay, so all because of these applications in the consumer electronics, and then as well as the industry, as well as the automobiles. Since these applications are slowly coming up, the supercapacitor market is also coming up here. So here maybe I'll put one more slide to make you to understand what is the energy density and power density. Here it's both are running race. One is 100-meter race, the other one is a marathon race. That is the difference. Okay, for here the speed is so important. The distance may not be very, very high. It may be only for very short distance, like 200 meter or 100 meters. Here the distance is too high, so that means 30 kilometers or 20 kilometers. But the speed is not so important. Speed is important, but you cannot run like this. So both these need some special skills, right? Similarly, for example, if you take a cup of water, so this is the amount of water stored in the cup is very small. So that means this is only little amount of energy can be stored. But when you want to take it out, you can simply pour it off. Or similarly, if you want to fill it up, you can simply just put it in a drum and then you can take it. Whereas here, in the case of batteries, you have huge amount of energy when compared to here, but the rate of discharging and rate of charging is very limited. So that's what exactly happening in your real supercapacitors and battery system. With this, maybe I'll just go into some of the fundamentals of supercapacitors. So here I just compared the different properties of capacitors or supercapacitors and batteries. Capacitors, I think you might be seeing in maybe in all your electronic circuits, you could see there is a small black color balls. If you see that will be like microfarad, 10 microfarad or 20 microfarad, worst case maybe 100 microfarad capacitors will be used. There the role of the capacitors are, if there is any fluctuation in the current, okay, or if in case of any charge current during running your circuit, so that will be taken care maybe for microseconds or milliseconds. Okay. So here we are talking about supercapacitors, where the capacity is maybe a microfarad. Here we are talking about 100 farad or 1000 farad capacitors. So here 10 power minus 6, here 10 power 2. So almost the difference is 10 power 8 times. Minimum is a 10 power 8 times increment in the energy. So that's why we call them as a supercapacitors. So charge discharge time here generally is a picoseconds to milliseconds. Here it will be milliseconds to minute. In batteries it will be in hours. Whereas coming to life, the temperature is more or less similar. But when you're coming to lifetime of your device, if in the conventional capacitors, you could see its lifetime is 10 power 8 cycles. Almost your entire life, if you buy one capacitors, generally it should be okay. Okay. Whereas coming to supercapacitors, the cycle life is very high, but it's slightly lower than the conventional capacitors. But still, this is very huge. At least 10-15 years, the lifetime of the supercapacitors will serve for you. Okay. Whereas if we're coming to batteries, I need not to say, since most of you may be experienced, the maximum is maybe 150 to maximum of 1500 cycles. Maybe 4 or 5 hours, or 5 years. Then after that, you can see there is a very drastic change. Even if you're unlucky, even within 2 years also, your battery will get failure. So the power density, we have already seen. The power density is very high for capacitors compared to supercapacitors. Supercapacitors are much than the batteries. When coming to energy density, it will be vice versa. Where batteries has very high power density, energy density. If you see the weight, in the case of capacitors, maybe several grams, whereas in the case of supercapacitors, maybe only few grams. Whereas in the case of batteries, it may be, it depends. But if you see equivalent to this, then it will be in kilograms. So how it works? I'm sure that you all are aware conventional capacitor, how it works. Conventional capacitors are generally made up of 2 parallel plates, conductive metallic plates separated by a dielectric medium. Okay. Here the metallic plates are replaced with some highly porous conductive material. In such a case, most of the cases, this is a carbon. Since a carbon is highly conductive and then the carbon also you can make it a high surface area carbon. So you should need high surface area, lightweight, and conductive material. So you can just replace this metal plates with this conductive carbon as an electrode. And then instead of dielectric medium, I just put a filter paper over there. That the filter paper which we are using in our laboratory can be replaced. In the case of electrolyte, you just take some kind of sodium chloride solution. You can put a sodium chloride solution. You dip this paper into sodium chloride and put it in between these two electrodes. Now your capacitor is ready. Okay, so when you have such kind of scenario, when you make a capacitor, nothing will happen. This so this we have the electrolyte is absorbed on this filter paper pores, where the sodium ions is covered by chloride ion is covered by the sodium ion because of the charge attraction as well as the repulsion. Okay, so when you connect this device to the external circuit, the moment I try to pull some electron from top to bottom, so by through some applying some external electricity, so this will happen like this. So when you remove some of the electron through external circuit and put it here, so this plate will become negative charge, this plate will become in positive charge. So once the negative and positive charges are created, the ions in the electrolyte move towards this opposite direction. In the sense, the negative ion move into the positive plate and positive ion move into the negative plates. So now there is a double layer has been generated. Okay, so but still if you see these ions are still within the electrolyte, it's only absorbed on the surface of the material. So if I can separate more number of charges, I can increase the energy density of the device. So that is the point. If I can separate only 100 charges, I can my capacity is maybe I can say maybe 100. If I can separate 1,000 ions, then maybe the capacitance may be 10 times higher. So how do you separate more number of ions? You should have more number of surface area, then you can have we can separate more number of ions. Also this so the surface area is so important. Now I remove it, the external circuit. Now I give some load. If I start using my mobile phone or my computer, this electrons move through this external circuit and then go back here. And then once all these ions go back, the negative charge and positive charge disappear. So in such a case, again, these positive ions are attracted by the negative ions and negative ions are attracted by the positive ions. It will go back to this situation. If you see here, I already charged and then discharged my device one cycle. So here I do not make any new bonding or new breaking up, new bonding. I did not move one ions from here, this side to that side, except these electrons. Okay. So that's why even if I do it this charge discharge cycling for n number of times, so nothing will happen to this system unless otherwise physically you break the system. Okay, so this is called electrochemical double layer capacitors, where your metallic plates are replaced since the carbon materials are very light in weight. Okay, so and then you could have very high surface area. For example, if I have 1 centimeter squared metallic plate, then it may be several grams. Whereas for the same 1 centimeter squared, I can give maybe few milligrams of carbon only is required. Even 1 milligram of 1 gram of carbon, I can give 2,000 meters squared surface area. Then you can see how I can increase the energy density. So that's why the energy density of the supercapacitors are much higher than the conventional capacitors. So that's what we have seen in here. Supercapacitor are basically divided into two parts. One is electrochemical double layer capacitors. I explained in the previous slide this particular mechanism. Only charges are separated. We need high surface area carbon. It's a highly reversible and stable system. But I cannot keep on increasing the surface area of the material. Here it not necessarily only carbon. Some metal oxide also can be used. But only thing is we need some conductivity. So I cannot keep on increasing the surface area of this my material. So beyond certain value, then the mechanical strength and electrical properties of this material will be different. So that's why I have some limitations in increasing the energy density of my supercapacitors. So the new concept came with pseudo capacitors or redox capacitor, where as like lithium-ion batteries or any other batteries, some kind of redox reaction takes place. But only the condition is it should take place very fast and it should be highly reversible. So that this also will be considered as a supercapacitors. If this reaction takes place very slow, then it will become a batteries. So, some of the materials are known for this, like for example, a transition metal oxide, ruthenium oxide, manganese oxide, and then conductive polymers has been well known for these particular applications. Very recently, there are another category, it's called hybrid capacitors, where the combination of EDLC pseudocapacitor or combination of different materials can be used. Generally, in supercapacitors, the same material can be used as a negative as well as the positive plate. Okay, so such whereas when you go for batteries, the anode materials are different or cathode materials are different. Whereas in the case of conventional supercapacitor, you can use the same material as your anode and cathode, but you can also use different materials also. In such a case, it will be called as a asymmetric supercapacitor. We can also use different combination of material like battery type material and a supercapacitor type material, so that we can have a hybrid device. So I don't want to go into confuse this, since maybe some of the speakers also will talk about this. So we will see very fundamental about this supercapacitor. Now I'll take 1 or 2 minutes to explain you lithium ion batteries, are to show you or demonstrate to you how this lifetime of batteries are much lower. I'm sure that you have been used lithium ion batteries. Maybe it will serve you only for maybe 3 or 4 years. Because I just explain you the mechanism, then it will be easy for you. So the one side, the anode side, you have a graphitic material. Graphite is nothing but that layers of carbon materials. In between the layers, there is a small gap that is called van der Waals gap. So here in the cathode side, you have some metal oxides, lithium cobalt oxide or like kind of lithium iron phosphate. Okay. So when you charge it, you are doing the same thing. You are pulling one electron through by connecting this to the external circuit. You are pulling one electron from this side and putting it here. Whereas once if you remove the electron, the lithium will become Li plus and then move towards the electrolyte, and then it comes here and get intercalated in between these two layers. So once if you remove all the lithium from this side to this side, and then you have made it 100% charged. Then when you use you give a load, then this electron wants to go back through the external circuit, the lithium has to come out. When the lithium comes here, Li plus, it will associate with the electrolytes. It will go as a bulk molecule. Here, it has to, after this, it has to come out from this sphere, and then it will only the lithium ion will go here. So this is the same thing I put in different manner. This is a graphite, and then this is a lithium cobalt oxide. Generally, we use crystalline material. So in the crystalline material, the ions are have the fixed position, right? For example, this is a cobalt ion, this is oxygen ion, this is a lithium ion. When you charge it, you are removing all this lithium ion. The first condition is even after removing all this lithium, the structure has to be stable, just not get collapsed. Okay. So once if you move all the lithium ions here, when you discharge it, this lithium ion has to come. When it's coming back, it has to go and sit its original position. Okay, it should occupy the original position. So that's what it is. There are problem starts. When goes here, maybe for example, 100 lithium ion goes here, maybe 99 when you come back. 1 or 2 will get strongly absorbed on the surface of this carbon. Since this carbon maybe have some kind of defect sites, or it may be strongly absorbed, it may have some kind of functional groups, it's strongly bound, then it will not ready to come back. Even it come back, sometimes it will go and sit in other voids spaces. So then next time it may not be available for charging. Or there may be another process called, there is a dendrite formation. There are so many other issues are also there. I don't want to go into the details, okay. So basically when you're charging and discharging, you are losing few lithium ions. So that's why when you have 100 lithium ions in the first cycle, maybe after 20 cycles, you could have maybe only 90 lithium ions or 80 lithium ions. So that's why when you buy a mobile phone, though it shows 100% charge, it will serve you for 2 days. Even after 1 year, if you see, you can, that the values will be shown it's 100% charge. but it will not serve you for even 3 or 4 hours. Okay, the same for the same use, within 3 to 4 hours it will be completely discharged, because the number of lithium ions settling between anode and cathode is drastically coming down. After a certain time, if you see, maybe out of 100, maybe only 10 or 15 will be settling. So that means your battery is almost gone. So when you start using your mobile phones or any electronic devices, from the first day onwards, there is a degradation start in the case of lithium ion batteries. So we'll come back to the. I hope now you are familiar with how this lithium ion works, why it is a cycle life, or the cycling performance of the lithium ion is very poor, and then why supercapacitor shows very high performance or very high cycling rate. So this is capacitors, conventional capacitors, which can be used in the electronic circuits. Here we are talking about ultra capacitors. Wherever there is emergency operation or high power operation, even for this airplane, the doors are opened by using capacitors. I can say super capacitors. And there is emergency landing, all these doors has to be opened. If you try to take the energy from your batteries, then it may not be. Okay, that's why they are using super capacitors. As I told you earlier, the regenerative braking system also people are using a lithium-ion super capacitors. So whenever you apply a brake, the energy will be produced. That since the electrical energy produced in a fraction of a second, your battery will not accept all the charge immediately. So such a case, you need a super capacitors. So not only that, they have demonstrated supercapacitor based bus. So this bus can get charged maybe within 30 seconds, and then it can go to 3 to 6 kilometers per charge. So wherever there is a operation like city buses can be used by this kind of supercapacitors. But the requirement is the bus stop has to be equipped with this kind of charging facility. So the bus goes and stops here, immediately it will be gets charged. So the passengers come out and then the passengers goes in. It will take maybe a minute or maybe 30 seconds. So that time is sufficient for charging this bus to travel for another 6 or 7 kilometers. By the time it should it should reach the next bus stop. That is the main kind of issues. So wherever there is a cities, and then the city buses where we have the bus stop every 4 or 5 kilometers, and then you can use this kind of buses. So not only that, even the high-end cars, the Lamborghini Sian is introduced a car that is completely made up of supercapacitor hybrid. It has very impressive specifications, like it can go within 2.8 seconds, it can go to 100 kilometers per hour speed. And then total engine weight is only 34 kilograms. And then this is a completely made up of with a supercapacitor based hybrid. Okay. So this is they have following energy accumulation technology. That is a world first, rather than the lithium ion batteries. So maybe you can just check those information in the Google. Maybe you can get more information when you have free time. So, okay, when coming to maybe another 10 minutes, I will just take it for what we are doing at the CSI Sikri. So we have, coming to the R&D activities, there are a lot of opportunities either to make carbon-based materials or metal oxides or sulfide-based materials or polymers-based materials to replace this electrode material. So once if we make the material, the fabrication is very simple. You make a material and add some conductive carbon, or if you use a very highly conductive carbon, you just add only a binder and paste it on your aluminum foil or nickel foil or any foil which you have it, and then put it in, cut into two pieces. One will be your anode side, one will be your cathode side, or one will be positive, other one will be a negative. Make sure that you have the size of the amount of material coated on this side is all equal. So you can go use a very simple technique called cyclic voltammetry, where you need only one electrode. The other electrode will be a reference electrode. The other one will be a counter electrode. Counter electrode will be a maximum of like kind of platinum foil or platinum mesh will be used. The reference electrode can be anything, like based on your electrolyte, you can change this reference electrode, silver chloride or mercury sulfate, or saturated calamine electrode, whatever it can be used. Here you can run a cyclic voltammetry that will give you about the performance of the material. So it will give you again whether this electrolyte is good or not for your application or for your materials. Okay. Also, it will give you what is the potential window you can do your charging and discharging. So all these fundamental parameters can be derived from this three electrode system. So three electrode system is very essential, particularly when you use some new material or first time when you make some material for using these for supercapacitor application. The three electrode system will give you enough information to fix the potential window, to understand the performance of the material, or in case of any modification is required or change of electrolytes are required, then you can do that by having three electrode system. Also, you can get some kind of tentative values like a specific capacitance or specific capacitance value from this three electrode system that will give you some idea about how your material performance when compared to other reported materials. So whereas when you want to calculate the energy density and power density of the device, then definitely you should go for a two electrode system where as I told you earlier, the same material will be used as a positive and the other one will be used as a negative. Then you could see you can do the same cyclic voltammetry as well as the charge discharge, galvanostatic charge discharge method, so that you can calculate the specific capacitance of the device. From the specific capacitance, you can also calculate the energy density and power density. So the specific capacitance you are derived from this three electrode system should not be used for energy density and power density calculations, since this is always will be much higher side than this. Even these values we are getting from the two electrode system will be slightly overside when compared to the real performance of the device. So for example, here I can get some 400 farad per gram, and then in the case of two electrode system, I can get only a 300 farad or less than 300 farad per gram. Even in the same system, when I go for device fabrication, it will give you only half of that. Maybe out of 300, it will give you only 200 per gram. So the point is here is the take home message is here is you first run the three electrode system and understand the system and optimize the potential window, optimize the electrolyte and optimize the electrolyte concentration. All these parameters you can optimize it. So after this, you can go for the two electrode system for the real measurements. So here the energy density of the device is basically depends on this equation 1/2 CV squared. The C is the capacitance. The capacitance is varied in this either one of the parameters, surface area of the material or structure of the material or morphology of the material or size of the material and conductivity of the material and what is the porosity of the material and what kind of functional groups on this material. So that's why even, for example, the same cobalt oxide or nickel oxide, when you make spheres, it will be different performance. When you make nano fibers, it will be a different performance. When you take nano tubes, that will be a different performance. Okay. Similarly, when you make microporous, mesoporous, or combination of microporous and mesoporosity, then definitely this will influence the C values. So that when you increase the C, obviously the energy density will be increased. The other way is the V squared. V is the voltage, that the working voltage of the device. So this mainly depends upon the stability of the material and then what kind of electrolyte which we are using for the supercapacitor application. Basically, if you use aqueous-based electrolyte, then the voltage is may not be greater than 1.6 or 1.7 or worst case 2 volt. Whereas when you use some organic electrolyte, you can go up to 2.7 or 2.8. When you use ionic liquids, really you can go 4 or 5 volt also, but your electrode has to be stable. So, but here it's a V square. That's why even there is a small change in the V, obviously it will influence large in the energy density of the supercapacitor. So here you see in 2006, we can see how many numbers of paper have been published in supercapacitors. For example, this is maybe hardly few hundreds of paper. Maybe I can say less than 500 papers have been published in 2006 or 7. In 2020, you could see this movie, more than 5,000 papers are coming every year based on supercapacitors. So this clearly shows that the super research on supercapacitors are increased very rapidly in last past few years. Okay. So I'm sorry, this is a very little old data. It's almost, maybe I have prepared this slide in March or April. Now it may be more than 5,000 numbers of papers, or very close to 5,000 papers. So among these, if you see the materials which have been explored, the composite material have been explored, conductive polymers and metal oxide and waste to wealth material and metal organic frameworks or zeolites have been extensively used. But among these, the carbon is one of the material which have been explored a lot, because the availability and stability and then cost, all the of the carbon-based materials are advantages for supercapacitor applications. So that's why we also have started with carbon-based materials. Of course, we explored some metal oxides also, but the device purpose, when you want to go for a commercialization, then this carbon-based material is the best choice at present. So people also started long before in carbon-based materials. So they take some activated carbon or carbon nanotubes, they decorate with some kind of metal oxides or some polymers, conductive polymers, so that electrochemical double layer capacitance comes from this carbon material, and then pseudo capacitance comes from this metal oxides or conductive polymers. So in the same system, you can have electrochemical double layer capacitance and pseudo capacitors, so that the energy density can be much higher. The similar way, I am sure that I need not to introduce what is graphene. When the graphene comes, the graphene conductivity is very high, as you all know, but the surface area is also very, very excellent. It has 2,630 meters squared. When you have such kind of high surface area with excellent conductivity, then the supercapacitors can be made for using these graphene sheets. But as usual, you know that supercapacitors, graphene-based materials are known for highly restacking. So in the sense where even if you exfoliate it, when you dry it for electrode fabrication or processing of making supercapacitors, it will get restacked as like your conventional graphite. So we need to put some spacer molecule when you have a monolayers of graphene. So when you decorate some metal oxides over this surface or some polymers over this surface, and then this, when you allow to dry it, it will not restack as like this case. So since you have in between some spacer molecules of metal oxides or conductive polymers. So that's the scenario we have also explored it. We took some graphene oxide and then we have in situ formed some metal oxides by direct metal complex formation, but without any heat involvement, we can decompose this metal complex into metal oxides. So that is advantage of this process. We can also we made manganese oxide, nickel hydroxide, cobalt oxide, copper oxide, zinc oxide decorated graphene sheets. But only thing is this process doesn't have any heat treatment, like 400 degree or 500 degree heat treatment to make the metal oxides. Since metal oxides are generally required high temperature treatment in our higher atmosphere for getting crystallinity. But here we could able to get crystalline material without any heat treatment. That is advantage for this. But unfortunately, when you want to scale it up, it is not very easy for producing in tons. So that's why we try to make some bio-derived carbon, particularly waste materials. For example, the rice straw is one of the large amount of waste material in Punjab, but unfortunately, it's not waste material in Tamil Nadu. But in Punjab, there are burning tons and tons of rice straw. Similarly, the corn cob is a huge amount of waste throughout the world. So this can be converted into activated carbon by carbonization followed by activation process. So I'll tell you what is the change is happening. Carbonization is a very common process. We are doing it for even the charcoal, which we are getting it is a carbonized material. But the activation is the major process, which is involves a very tedious process. It also decides various steps also. For example, in the case of activation, we are simply making holes on this graphite or the carbon material. So this you could see is the same magnification. It looks like very brick-like morphology. And the same thing after treatment, you could see there are a lot of pores has been generated. So the electrolyte can easily penetrate through the pores. Also, there is new surface area is exposed. So there are a lot of surface area has been access to this surface area by having mesoporous and microporous combination. We have varied different materials starting from 17 watt-hour per kg to now we can able to make 76 watt-hour per kg by changing type of carbon material from different sources. But that is not our that is not the only our strength. We could also able to make a device. So a few years before, we made a very tiny device. It's made up of bioderived carbon materials. But the advantage of this device is you can also bend it like this. Now there are a lot of requirement for flexible and bendable devices. Such can be fulfilled by having such kind of supercapacitors. As I told you earlier, we also works on various electrolyte changes, or we can also make some different kind of arrangement. For example, this is one is activated carbon, the other side is metal oxide decorated graphene oxide. So I can make asymmetric capacitors so that I can have the potential is very high. So usually when I use only activated carbon on both sides, then my potential window in a aqueous electrolyte will be only 1 volt or less than 1 volt. When I have a asymmetric system, then I could able to have the same system. I can have maybe 1.6 or 1.7 volt. I told you even there is a small change in the V, greatly it get influenced by the energy density, since that is a V squared. So that's why by using asymmetric thing, we have also made a small device like this with 1 centimeter squared electrode. We could able to light by connecting two LEDs, two devices in series. You could make one LED to glow. When you have 5 devices to connect in series, we can able to make several LEDs to get glow. The same concept we have also made it in large scale, in the sense of 5 centimeter squared electrodes. So similarly, 6 or 7 electrodes may be made like this as a small bunch. This is like this. There are 6 devices has been made, and then these 6 devices can put into small. Maybe we can replace the lead acid battery container. There is we have a 6 compartments. So each device is 1.6 volt. Now, if we connect all these 6 devices into series, you can get 9.6 volt. So the stored energy in this device is 30 milliwatt hour. So not only that, you can also roll it this capacitor. Here, for example, we made a tape, carbon coated tape for 4 meters length with a 10 centimeter width. So similarly, there are 2 tapes have been made. In between, you keep a roll of separator, carbon separator, and then you can roll it like this. So once if you roll it, you can just make a lead, and then you have to seal the can. In such a case, you can get 45 farad with a voltage of 2.2 volt with one single device. Okay, so this is a device which we made it maybe 3 years before, and then very recently we made it a commercial like supercapacitor device where the loading is only 1.2 grams. That height of the device is only 2.3 centimeter. With this, we can have a stored energy of 15 milliwatt hour. So here, the other case, you can have only 30 milliwatt hour with a large size capacitor. This is a very tiny device. With this, we can have a 13 milliwatt hour energy can be stored on this device. So this I just show you working performance of this device. You could see this. There are 70 LEDs in the back side. So this device can be just charged for 30 seconds, and then when you connect this device into this, when you connect this board to the device, this board can be powered for more than 30 minutes just by charging 30 seconds of this device. Not only that, we also made attempt to replace our lead acid battery in your bike. which is generally used for starting of your bike application. So here we would used a 16-volt supercapacitor with a 16 amp rate performance, where we made a 58 farad capacitors. We simply replaced this lead acid battery, and then we could able to charge this bike for 7 times without charging this device. So you could see there is a small video over there. So this device has been replaced with our lead acid batteries. We also compared our device with the conventional players, the carbon which we have used for 45 farad and 18 farad capacitors is much higher. In the case of they are using 7.5 grams or 13 grams, where we are using only 5.6 grams instead of 13 grams, or 1.3 grams instead of 7.5 grams. But of course, there is a small change in this. But still, if you see this performance of the carbon is almost twice than this conventional capacitors. So right now in Sikri, what we are doing is we are making a 12 volt to 500 farad supercapacitor assembly. So that will be made as a small unit. So that will be clubbed with batteries. Then we are going to have a hybrid system to run a vehicle. Particularly the hybrid will be made it with a lead acid battery as well as a lithium ion batteries. Now this research is going on. Now we are already made a hybrid of supercapacitors and lead acid battery by tri-wheeler application. So here we want to see how the battery performance or the lifetime of the battery can be improved when you have a supercapacitors. Since when you have this kind of hybrid, so the amount of energy withdrawn from your batteries are very constant. Okay, so the excess energy required when you start a vehicle or when you move a vehicle with a heavy load or when you move a vehicle in a hump, then the excess energy will be taken from the supercapacitors. So the battery will be in very safe condition. So it will be operated in a very stable condition. So because of this, the performance of the batteries will be very high. So with this, I conclude, and very soon maybe we have our indigenous system for green and sustainable way of storing the energy that could save our environment as well as that will serve for our future applications also. So with this, I take this opportunity to thank our director, Dr. N. Kalachali ma'am, for giving opportunity to work on this area and supporting us for both financially as well as technically. I also take this opportunity to thank some of my students who was actively involved in my supercapacitor fabrication, like PhD students as well as the BTech students. Last but least, the funding agencies. So without them, it's very difficult to run a lab. So I take this opportunity to thank all of them for their generous support. I also thank you all for your valuable time to listen this course. Yeah. Thank you. If you have any questions, I'm very happy to answer.
Sir, good morning. Sir, good morning, sir. Sir, can you hear my voice, sir? Sir, I have to speak with the professor. Yes, sir, I have one doubt. Sir, are you hearing my voice?
Sorry? Yeah.
Sir, good morning, sir. Thanks for a nice presentation.
Yeah.
So I have doubts, sir. Actually, the activated carbon made out of coconut, sir, which has the highest physical surface area around 2,500 meters square per gram. And some people are made of activated carbon by fruit peel. As you said, you have made up of activated carbon some other materials. Actually, what are the difference between to made up of activated carbon, sir? Some other source of materials like you made up of corn materials. So what's the difference between, sir? What's the efficiency if we are using some other activated carbon?
Yeah. That's actually very important question. Is maybe I can say this there are variety of compounds have been reported. Okay, so for conversion of bio waste into activated carbon. So some of the cases there are inherent heteroatoms. For example, nitrogen and sulfur or phosphorus containing species. When you carbonize it, it can be retained when you make a carbon. So that means that you are doping a carbon. You are doping some heteroatoms into the carbon matrix. So that can be happen naturally. So that is one of the difference. But that difference may be very high in the when you go for a high temperature treatment. In most of the cases, when you go for a high temperature treatment, this heteroatoms usually it will evolve it. Okay.
Okay, sir. Okay.
So, but still there may be a lot of chance for having some very small amount of this kind of heterosome. That is one. The second thing is that the ash content as well as the carbon, the nature of the carbon or the compound which you have it for the carbonization is entirely different. So, for example, the lignin content when you carbonize from a kind of wood source, so there is a kind of reasonable amount of lignin. Similarly, when you go for some kind of peels like orange peel or kind of other material, so there will be some unique compounds. When you carbonize it, always you will get a different kind of functionalities on the surfaces.
Okay.
So that makes the carbon is different from one another.
Okay, sir. So one more doubt. So what about charcoal, sir?
What about the
Coal, sir. Coal. Charcoal.
coal?
Yeah.
Yeah, coal also can be converted, but that's again the way how you are converting it and what is the basic cost. All these things is the matters. When you start with coal, then the process may be. I mean that the cost will be more.
So okay, sir. So okay. Thanks, sir. Thanks, sir.
Yeah, thank you. Thank you. Yeah. Here, that's why it is not necessary. Both can be used as a positive and negative. Anything can be used, I can say. Okay. The only thing is when you connect it in series or parallel, then you have to be taken care. The same side has to be put it in a positive and negative. Otherwise, here there is no polarity. Anything one side, if you the positive and negative terminal can be anyone. What kind of? No, sorry, I didn't get what kind of binder. Okay. Yeah, binder. There are majorly there are two kind of binders people are using. One is PTFE and PVDF. So it is depends on what kind of processing which you are doing it. When you use a wet processing, I think you can it's better to go for PVDF. When you go for dry coating, then you can use a PTFE. How to construct? Yeah, of course, supercapacitors are very simple. For example, as I told you, if you make the electrode ready, you take a carbon paste and put it on some substrate like maybe aluminum foil or nickel foil or SS foil. The one here is you have to select a suitable electrolyte. If you are using KOH or if you are using sulfuric acid, these are the commonly used electrolyte. People are also using neutral electrolyte, sodium sulfate also. In such a case, based on the electrolyte compatibility, you have to choose a current collector. Once that has been done, then if you want to make a device, then you have to coat it in maybe 5 centimeters squared or 1 centimeter squared based on your requirement. And in between, you keep a paper, maybe separated paper and soaked with some electrolyte. And then you have to cover it or seal it with some maybe aluminum foil or whatever it may be. Or if you want to have large capacity, large farad capacitor, then you can also do stacking of several layers of electrodes, both the positive and negative terminals. Then you could have make the device. Only thing is you have to make sure the electrolyte is not coming out from the system. So that's why you need kind of small sealing or small closing in your container. Yeah, that is a major issue. People are working on it. I don't have any solution as of now. So this is one of the major issues, which is the drawback for supercapacitors. But as I told you, the supercapacitor is not good for storing energy for long duration. So wherever there is a peak power requirement, only that time it can be used. In such a way, you can limit the use at present. Basically it can be used. Okay, so only thing is you need some ions to get absorbed on the electrode surface, but generally they may not use for phosphoric acid. So there are certain requirements. For example, even sulfuric acid, you cannot use pure sulfuric acid or concentrated sulfuric acid, right? You need some 1 molar solution or 2 molar solution. Similarly, the conductivity is the matrix. In such a case, you can use it. Anything, any salt can be used. If you have a positive ion and negative ion, not necessarily phosphoric acid. Even sodium chloride or potassium chloride can be used.
Hello. Sir, good morning, sir. Is it audible, sir? Hello.
I can see the other questions. There is a should we check compatibility between current collector and electrolyte? Of course, yeah, we have to select the compatibility. Otherwise, you can get a hydrogen and oxygen evolution. That in the sense, you may not get the full potential window of your material. Yeah, that's why I answered. That is very requirement. That is very essential. For example, if you raise nickel foil into or nickel substrate into your sulfuric acid, before the potential window of your material, then there will be a nickel dissolution may happen. Okay. Yeah, basically you can use. I told you anything can be used when you use sodium sulfate. That means a neutral electrolyte. Generally, the performance will be you may have only uh, pure electrochemical double layer capacitance. That's why people will go for some kind of acidic or alkaline solution. Otherwise, aqueous neutral electrolyte is the best electrolyte for commercial application. Yeah, that is a very interesting question. Since when you are making a flexible device, your electrode also has to be very flexible. You can go for some kind of carbon cloth or some conductive polymers. Okay, so such kind of substrate can be used. Yes, the idea is similar. Okay, For example, when you use batteries and supercapacitor in a hybrid mode, the problem, for example, when you use battery alone, why the problem comes is, for example, the battery is rated for maybe 20 amps current. When you start it, maybe you may need 25 amps or 30 amps. Okay, so that means whenever you make it 25 or 30 amps from your, try to take your batteries even for a very fraction of second, your battery lifetime will go down. So what we can do is, when you combine these batteries and supercapacitors, the 20 amps comes from your batteries, the rest of the 5 amps or 10 amps comes from your supercapacitors. So in such a way, your battery will be very stable. So always it will give you only a 20 amps current, or you are taking a 20 amps current from your batteries. So obviously that your battery lifetime has to increase. So that's the idea. Yeah, the pseudo capacitance is nothing but almost like your batteries. Batteries, we are getting the reaction is only a redox reaction. One is a charging or discharge, sorry, oxidation or reduction reaction, where the exchange of electrons are involved. In the supercapacitor also, we are using the same thing. But the thing is, the reaction should be highly reversible, and it should be highly very fast. Okay, in the sense, the oxidation and reduction takes place in a very fraction of second. Then only you can charge and discharge your device very quickly. So such kind of redox process, there is an involvement of electron. That is, the exchange of electron has to be very fast. Okay, so that's why we call them as a pseudo capacitance. There is a redox reaction, but that is not should not take place in the conventional way. Conventionally, the redox process takes place in very slow manner, but here it should take in very fast manner. Yeah, thank you one and all for your active participation. Even if you have any questions, maybe you can write to me in email. I'm happy to answer it. Yeah, thank you.
Good morning. Good morning. So thank you, Dr. Pereswamy, for your kind words. At the outset, I would like to thank the organizers, the HOD, principal, and the management of Nehru Group of Institutions, or maybe College of Technology, for arranging such a very nice event. And the topic selection for the event is so apt for the current days. In the inaugural, as Dr. Satish told, my friend told, so the organizers have aptly framed the topic to energy storage devices, in particular the power dense devices, that's supercapacitors. And the range of the speakers selected also so apt. So I'm fortunate to be one among such elite group people. I see my friend Dr. Satish, there are several friends, Dr. Karthik, Dr. Kodan Raman, and many other people. I wish the participants will be enriched with the content on the energy storage devices, in particular supercapacitors. So congratulations and all the efforts that your team has taken. I hope the participants will enjoy the benefits of these lectures. And so I feel it is tough to give lecture after my friend Dr. Satish. He has spoken most of the content on the basics of supercapacitors. So thank you. That made my job very simple. Thank you, Dr. Satish, for your wonderful presentations. So now let me move to my content. Anyway, you will see some of the overlapping content because the topics selected or given was more similar. You will see some overlapping content. Maybe if you find something different, you can take home. Otherwise, do not scold the presenter or the organizers for the repeated topic. So let me admit that. So I'll be sharing my screen. So is my screen visible? Am I audible? Yeah. Thank you. Thank you. Sometimes the internet is wobbling, so please pardon me if there is any interruption by the network. Yeah, I can reconnect within few minutes. Yeah, so the topic that was given to you is on the recent developments on supercapacitors, hybrid versus supercapacitor. I hope I will give the justification for the title at the end of the, or as we get on the topic. So you would have seen this image available in the open literature. I have taken it from NASA website. And I usually give this image to enlighten the importance of the usage of the light or the electricity. And you see that throughout the globe, so much of energy is being utilized. And wherever you see on the earth, you see the bright spot, it means that so much of electricity is being consumed. As usual, the American nations, the Northern America, European nations, and the tiny nation Japanese, they consume a lot of energy. We, India, also not bad. So compared to maybe other parts, so we also consume significant amount of electricity. And as Dr. Satish rightly pointed out, it's about 13.5 terawatt or trillion watts of energy. That's roughly about 14 trillion watts of energy. I'm using this slide for last 5 years also. I started with the 12 trillion watts of energy, 13 trillion watts of energy, 13.5 trillion watts of energy. Now it has increased to 14 trillion watts of energy. You see that the world is moving towards the consumption of more energy. And if I translate this trillion watts of energy into the energy that you have to get it from Niagara Falls, we need 3,000 Niagara Falls. You can see the potential or the amount of energy that the globe is consuming. So of course, there is a 10%, about 10% of deficiency throughout the globe during the consumption of energy. It means that some parts of or other, they are not having the energy. But this much energy, 14 trillions of energy is very huge. Unfortunately, we have only one Niagara Falls. And so you know that about 80 to 85% of the current energy, that 14 trillion watts of energy, is coming mostly from the chemical fuels. How? By means of burning of such fossil fuels. That includes not only coal and gasoline or diesel or any carbon-based conventional fuels. And Dr. Satish elaborately gave the percentage of the coal utilization and maybe carbon fuel utilization and other sources. So roughly is about 80 to 85% of the chemical energy. By means of them, we get the energy. And we know the consequence. It is obvious. We have been witnessing already the global warming. And this year's Nobel Prize has been given to the prediction for the global warming, which is the main cause for this global warming is the emission of toxic gases by means of burning of fossil fuels. So which includes nitrogen oxide, nitrogen dioxide, carbon monoxide, even carbon dioxide these days are considered as a GHG. And of course, partially decomposed hydrocarbons all contribute to the greenhouse gases, which lift the surface temperature as well as the sea level temperature. So we call them global warming. So thanks to those three Nobel laureates who predicted using the algorithms the rise in temperature, or that led to the term global warming. In one hand, the emission of fossil fuel, the burning of fossil fuel leads to emission of toxic gases. On the other hand, the reserve for such fossil fuels are also getting depleted. So there is an estimation that by 2050 or so, there is going to be a huge energy crisis because all the resources or reservoirs available for the conventional fossil fuels is getting depleted or getting consumed. So unless we are going to discover new resources or new places of fossil deposits, so we are going to have a severe energy crisis. So we know that the use of such carbon-based fuels leads to adverse effects on the environment. So there is a new technology being considered by the automobile manufacturers called the selective catalytic reduction system, where urea will be used along with the water. So hydrolysis of urea releases the ammonia. Ammonia can react with the nitrogen oxide, nitrogen monoxide, and can decompose these toxic gases into nitrogen. Or we may have a green emission or clean emission. So we may not have a nitrogen oxide or nitrogen dioxide emission. So for an effective implementation of this selective catalytic reduction system, you require high performance sensors. So thanks to Professor Mura, so my postdoctoral mentor who interested me on the development of these sensors. So I am very much thankful to my postdoctoral mentor, Professor Mura. So I had a very long experiences on developing sensors, and one of our sensors, ammonia sensor, is being implemented by Mitsubishi corporations. So in one way, the combustion of fossil fuels leads to emission of fossil fuels. What could be the possible solution to get rid of these toxic emissions? So one solution is to go to use of hydrogen. I'm sure all of you will agree with me, the use of hydrogen will give you energy and water, no other emissions. But unfortunately, we do not have raw hydrogen. But hydrogen in the form of water or biomass available in plenty. Or in other way, so we need to go for use of alternative sources of energy, which must be sustainable in nature or renewable in nature. So we all should remember that the Mother Earth on which we live is borrowed from our future generations. So we should leave the Mother Earth as such as we borrowed or without damaging much, so that our future generation also will get benefit out of that. So in terms of usage of electric energy, so we need to shift towards alternative energy sources. So they are sustainable or renewable in nature. So they are sustainable or renewable in nature in such a way that you consume them, but you leave them something that it will replenish, so that our future generation also will get benefit out of that. So maybe as long as the Mother Earth is existing, we are going to have wind. And as long as the sufficient wind speed is available, you can convert the wind energy into electrical energy. As long as the universe is existing, we will have a sun. As long as the sun is existing, it is possible to convert the sun energy into electrical energy using at least two technologies. One will give the electrical energy, another one will give you the storage of heat, so that can be retrieved anytime. In all, so any alternative energy source should have these attractive features. It should be available in abundance and renewable in nature, and it should not be harming the environment. Even a given small amount, it should be able to hold more energy and available low cost, affordability, transport, all many attractive features you should be having. Very importantly, it should not lead to social harmony. Use of such energy sources should not lead to any social harmony. So it should be socially acceptable, compatible. So given those attractive features, we have a countable number of renewable energy sources. We are not having 3,000 Niagara Falls, agree, but we have a one sun. So there is a saying that even if you use 1% of the solar energy, it is possible to power the whole world using these technologies. So solar photovoltaic technology may be combined with the solar heating technology. So then we have a biomass, bioenergies. So carbon in the water or hydrogen in the form of biomass, plenty available. We have bio waste, agricultural waste, domestic waste, etc. Wind energy, hydro energy, geothermal, ocean, tidal, etc. Unfortunately or fortunately, the very characteristic of these alternative energy sources are they are either time specific or location specific, sometimes both. So when I say time specific, the sun is available during the daytime only. Most of our energy, as Dr. Satish told, is requiring even in the night time. 30 to 40% of energy is requiring even night time. Unfortunately, we have only in the daytime sunlight. If at all you want to use solar photovoltaic or DSSC, you can use only in the daytime, and the effective sunlight is available only from maybe 9 a.m. to 4 p.m. And you require energy in the night time. That is time specific. On the other hand, the energies on the alternative energy resources such as wind energy, they are all geographically specific or location specific. You cannot install the wind turbine all the places. For example, the wind speed available in Pondicherry is not enough to convert them into electrical energy. You need to have a sufficient wind speed so that the wind turbine will undergo rotation, and how that will the kinetic energy associated with wind can be converted into electrical energy and can be transmitted from one place to another place. So the places like Tuticorin or Haralvalmudi, so we are very fortunate. The southern part of India or southern part of Tamil Nadu is very fortunate to have sufficient wind speed so that wind energy can be reaped. Of course, it is also season specific, not only location specific, and it is season specific. But in all, the energy generated from all these alternative energy sources need to be transported or transmitted from the point of generation to the end users, which requires huge infrastructure. And so this transmission of the power from one place to another places or from the point of generation to the end user inherently associated with the loss of power loss, about 30 to 40%. This is equal as not generated. So the one of the options could be to store that energy and use them whenever you require, wherever you require. So this requires usage of a storage device. So your electrochemical energy storage device or electrical energy storage device can support this. And that must be affordable in nature and must be efficient in usage. So they come under electrochemical energy systems or electrochemical power system or energy system. We have three prominent electrochemical energy systems: fuel cells, batteries, and supercapacitors. And the 2 days from today and tomorrow, so you are going to listen to various lectures on this aspect. So while fuel cells are energy conversion devices, the chemical energy stored on the fuels can be converted into electrical energy as long as you fuel the fuel. Once you stop feeding the fuels to fuel cells, it will stop producing. They are sustainable in a sense. Whereas batteries and supercapacitors are energy storage devices. So the energy stored here can be used anywhere, anytime. That's the greatness of these supercapacitor and the batteries. Of course, there are differences between the batteries and the supercapacitors. So the energy stored in the batteries are very large and they are energy devices, whereas the supercapacitors are power devices. So the energy stored in the supercapacitors are very limited, but the power that you can derive from the supercapacitor is very high, exceedingly high. So what are batteries? They are basically electrochemical cells. You can also call as galvanic cell or voltaic cell. When I say galvanic or voltaic cell, the potential developed by these systems are positive. It means the electrochemical reactions taking place in these galvanic cells are spontaneous. You don't have to do any other additional effort. You just connect the circuit with the help of a anode, cathode, and electrolyte. So it will start producing the positive potentials. When you compare the batteries and the supercapacitor, there are merits and demerits in both cases. So as I told, so the supercapacitors are power devices. So very exceedingly high power it can deliver. So I think similar image was shown by Dr. Satish also, like a Usain Bolt. Supercapacitors are like a relay runner. So 9.11 seconds, he reached 100 meters. Very high power he could deliver. Whereas batteries are like a marathon runner, very well explained by Dr. Satish. There are other differences and comparisons. Uncomparable cycle life you can have for the supercapacitors. So this is very much possible when you have a EDLC based supercapacitor. So because there are no changes in the material, no volume change, no material change, carbon remains as a carbon, or any other EDLC material, they remain as such. So there are no changes in the volume, there are no changes in the crystal structure, there are no changes in the compositions. So you get unlimited number of cycles. What is this cycle life? So cycle life means how many times you can charge and discharge. 1 lakh time, as high as 1 lakh time. Of course, the energy stored in the supercapacitor is limited. I think similar cartoon was shown. So the rate of delivery of energy is nothing but the power. So supercapacitor can give very high power instantaneously. Why high power is demanded? And you know that most of the nations are moving towards electric vehicle, and use of electric vehicle need to be improved. So many nations have already came up with the electric vehicle policy, even in India. So we are already into FAME 2, fast So sorry, I don't know how many minutes I was out of network. So just 1 minute. 1 minute only. So I got call. I thought somebody else. So that's the problem with this Google Meet. Maybe in Zoom or in. So not very long, na. So 1 minute only, right? Okay. I will resume. So is it visible? Okay. So I think this is the application model of a supercapacitor that I was talking. So I think it was interrupted. So it happens many times almost. So if the available power is constant and your intended power requirement is instantaneously varying, so it is not possible to get this instantaneous power. So you need to have such devices, supercapacitors. So that can supply such an instantaneous power. Or your required power is constant and available power is varying. So you cannot feed this available power, which is instantaneously huge, to the system. The system will get damaged. So you need to condition that. So for conditioning up that high power, you need a supercapacitor, ultracapacitor, so that the required power is kept constant. In either case, so the supercapacitor can find their applications. What are supercapacitors? Why they are called supercapacitor? We know that conventionally, if anything exceedingly performing, we attach the prefix super. It's basically capacitor. The magnitude of the capacitance or the charge stored is exceedingly high compared to the conventional parallel plate capacitors, and they are called the supercapacitors. We know 6 in cricket, super 6, something like that. Or conductors, we know very well, normal conductors. And we have superconductors because the conductivity is exceedingly high. Conduction at zero with zero resistance is the superconductors. Similarly, here capacitor, the capacitance stored is exceedingly high, so you named it as a supercapacitor. So depending on the material that is being used, these supercapacitors are also called as ultracapacitor or lightweight capacitors, etc. So depending on the type of the material being used. If the type of the material being used is carbon, you call the supercapacitor as a ultracapacitors, because ultra refers to the mass. So carbon is having lightweight compared to maybe other metals and metal oxides. So you name them as a ultracapacitors. So even in the case of supercapacitor, you can play around with the capacitance or the charge stored, use of surface area, or the distance between the separating plates, or the electrodes here, and the electrolyte. And this is the circuit or the symbol used to describe the capacitor or supercapacitors. So a little more on the ultracapacitors. So the best explored material for ultracapacitor, so he is mostly carbon-based materials. The very reason is it is having conductivity mostly. Okay, so even the worst the activated carbon will have some conductivity. Okay, but they have very huge surface area. Huge surface area is very important because it is going to work based on the EDLC, just charge separation. There are no Faradaic reactions. So this charge separation can be increased if you have a larger surface area. So larger the surface area, larger the charge separation you can have. Larger the charge separation, better or more efficient the charge storage. So these are other features. Of course, the charge separation is extended to some distance only, very short distance, maybe a few nanometers. So there are 4 theories to explain this EDLC. I think this is not the medium to go for that. So based on the type of the charge storage, so there are 2 types of capacitor. I have another classification maybe towards the end of my lecture. So conventional EDLC based capacitors, so they are non-Faradaic. It means that there are no charge transfer reactions or electron transfer reaction or Faradaic reactions, mostly carbon-based materials and some maybe alkali earth metals, oxides, they show such kind of behavior. Only requirement is they should be having large surface area. Whereas pseudo capacitors or redox capacitors, So they store the charges or energy by means of a definite Faraday reaction. That Faraday reaction can be happening only on the surfaces or on the electrode itself. So either electrosorption or electrochemical reaction can take place. And I think this cartoon can give you a better view. So in the case of EDLC, you see that it's a charge accumulation or charge separation between the electrodes. You can use two electrodes, single electrodes. So you need to take a suitable electrolyte in such a way that charge separation occurs and it holds the charge. Whereas redox capacitors, so there can be a definite redox reaction. So ruthenium oxide and manganese oxides are considered as a redox material. Of course, they are not. They have only electrosorption. They are not changing their oxidation state or etc. But it's only exchange of proton or OH minus depending on the electrolyte. But there are many other potential materials like hydroxides and polymer materials or even functionalized carbon. So there is a definite Faraday reaction, not just electrosorptions. So there is two distinction methods in the case of supercapacitors. There is only a charge separation at the electrode-electrolyte interface in the EDLC. In addition to charge separation, here the predominantly charge transfer or electron transfer or the Faraday reaction is the main reason for charge storage in redox capacitors or pseudocapacitors. I usually use this analogy to explain the differences between the ultra capacitor or capacitor versus the batteries. So this is called a water tank analogy or water tank model. So assume that you store water in a tank, and so to get the water, you need to have an opening, maybe a tap. So capacitors are something like this. The storage volume is very low, but the tap size is very large. So it means that whatever the energy stored can be given up quickly, very high power. The rate of delivery discharge of the water is very high. That is nothing but power or power density. And whereas ultra capacitor, the tank size is little large, but the tap size is moderate. So compared to this, it is less. Compared to the tank size, large. So it means the charge stored is large, but the power density compared to capacitor is less. Whereas the battery is almost opposite. You have a large tank size compared to the capacitor, but the tap size is very low. So after opening, so only slowly it can deliver the energy. So by this way, you can understand the importance of these three devices. So I'm still in the introductory stages. So I have to go. I think I have to hedge it. There are many other differences or comparison between the capacitor and the battery. So you will have a linear charge-discharge profiles in the case of symmetric capacitor, whereas you have a plateau type charging discharging profile for the batteries. So you can see that the slope is constant here, whereas the slope is instantaneously varying, dynamic. And it is highly symmetric in the case of supercapacitor, whereas in the case of batteries, the charge-discharge profiles are having a definite plateau. So having a definite plateau is advantageous. It means that the constant supply of voltage or the power. So whereas in the case of supercapacitor, it's highly symmetric. So the slope is instantaneously varying. It is dynamic. So if you try to do the cyclic voltammeter for these two devices, EDLC and the pseudocapacitor, for EDLC you will get rectangular type cyclic voltammeter. The area under this curve is the equivalent to the charge that is being stored. Whereas in the case of redox capacitor or pseudocapacitors, so they don't have a rectangular, but they have a peak. So the appearance of these peaks informs that or imply that there is a definite electrochemical reaction or Faraday reaction is taken place. So materials like PANI or the combination of PANI and polyaniline and graphene oxide, functionalized graphene oxide, or reduced functionalized graphene oxide can all show such kind of CV profile. So these are the metrics you can use to quantify the charge storage. Either you can use capacitance. Maybe if it is a battery material, you use capacity. Once you know the capacity or capacitance, it is possible to estimate the energy, and the rate of delivery of the energy is nothing but power. And using this formula, the maximum power formula, so P equal to V square by 4 or it is possible to estimate the power, and of course the normal power also one can obtain. So I think I'm done with the basics or basics. I think whatever Dr. Satish has covered, I think there are many content overlapping. I hope it will be advantageous to you, definitely. So from here on, maybe about 15 minutes or also, so I will take you to the recent developments that has taken place on the materials. So for simplicity, I will restrict myself for the materials that are developed in our lab in Pondicherry University. So mostly they are the carbon-based materials, oxides, hydroxides, and composite. I think I need to correct this composites. And so use of sustainable means to derive the electrode materials is a current trend. So as the Niti Aayog, Government of India has predicted that there is going to be a huge demand for the energy storage devices. So the supply chain or the raw materials for bringing such a huge amount of batteries or supercapacitor is highly demanding. So people try to explore all sorts of energy sources or material sources. You can see that very recently in our lab, we have explored these sources, glass waste, mobile back cover, the waste talcum powder or silicone caps, etc. So we have been using all these in our day-to-day life. And there are agricultural or domestic waste. For example, so this palm fruit or walnut or spent honeycomb or denatured milk. From all these sources, either we have generated metal or metal oxides or at least carbon, activated carbon, and use them for battery or supercapacitor applications. If they are biomasses or agricultural wastes, you get activated carbon. Other than that, maybe for glass, from glass, so we get silicon and related materials, and depending on the sources, you get their respective materials. These sources are very unique. The biomasses or the agricultural wastes are very unique. Each material, each source gives a unique carbon. So that's why so many papers, publications, patents are being happening. They are not same. They may be agricultural waste, but each are different. So this is one system where we have explored the widely available this tree, and the palm tree is widely available in Tamil Nadu or in southern part. So maybe sometimes it is edible, eatable. Sometimes the components of these palm trees are mostly eatable, and it is used for many other applications. And this fruit, mostly it is becoming waste. It just falls down or falls down from the tree to the ground and just decays. What we have done was we have captured that and unskinned it, and we got a skin. This I think I have a better graphical abstract. Yes, unskinned. So we got a chopped fibers, palm fibers. So that was subjected to carbonization followed by activation using, I think we have used KOH activation. There are other methods of activation using phosphoric acid or zinc chloride, etc. We have used KOH, that is most widely used and efficient method of activations. And you can see that, so the after activation, the material is characterized, the carbon, activated carbon is characterized. So if you activate at 500 degree, this is the morphology you get. 600 degree, you get this. At 700 degree, you get highly porous morphology. And it is unique, as Dr. Satish also told. So how do you know that it is a carbon? So the best method to characterize these materials are to go for X-ray diffraction, and it can be complemented by using spectroscopic technique like Raman spectroscopy and IR spectroscopy. These are the Bragg profiles or XRD profile where you see the formation of carbon. And the carbon is not very fine, the peaks are not very fine, so we went for Raman profile. The appearance of this D band and G band confirms that the formed material is having a carbon, and it is more like a graphic nature. As you can see from the TEM images, it is highly porous. Okay, so we have done other characterization like surface area and elemental mapping, analysis, etc. So I do not want to go into the detail. Let me go to the electrochemistry part. So this is the 3 electrode data. So mainly we do this 3 electrode data to screen the material for use of whether it is a symmetric, asymmetric, or redox, or EDLC behavior, or battery behavior, you can know. So 3 materials we have generated. So you, depending on the activation temperature, 500 degrees, 600 degree, you can see that they all can store the charges. And it so happened that the carbon that is activated at a 700 degree could give higher capacitance of as high as 300 farads per gram. So that is optimized temperatures. So that is through 3 electrode data. 3 electrode data is of no use. Practically, it is no use. So you can know it can store only charge, but you cannot quantify in terms of energy density, power density, etc. So you need to go for 2 electrode system. So we have developed our laboratory prototype of coin cell, maybe something like this. So yeah, typical coin cell we have fabricated. So maybe these are the components of coin cell we have made. So we have used 2 carbon electrodes, symmetric. Okay, so we have used aqueous. We have also explored a non-aqueous system for other materials. And so what are the performance of this supercapacitor, ultra capacitor? So I call this as a ultra capacitor because the material used is carbon lightweight. And you see that there is a rectangular type of cyclic voltammogram which confirms that it can be a EDLC behavior. What is the charging and discharging profile? Nearly symmetric at a high current. So at low current, maybe there is a deformation. That is not important. What is important is what is the energy density, what is the power density. You can get energy density as high as 30 watt-hour per kg. And you can get the power density as high as 3000 watt per kg. And it can be powered to demonstrate a commercial 2.7 LED. So it glows for more than 30 minutes on single charge. So it means the mere waste palm fruit can be converted into usable form or maybe a valuable material. So by adopting a suitable chemical methods. In the same way, we also recently explored walnut. Walnut, it's not widely available in India, but in other parts it is widely available, especially places like Afghanistan or Turkey. These biomass very much available. So after consumption of this walnut seed, the shell is just thrown or dumped into the environment. So I'm not sure whether they are having any manuring mechanism, etc. But what we have done was this walnut having a very hard shell can be converted into activated carbon by using the same method. So you crush it, then carbonize it at a 300 degree, then activate it at a different temperature. We have done it using KOH activation. Then confirm it using conventional X-ray diffraction and complement it by Raman spectroscopy. So what is the performance? This is the performance at a 3 electrode system. So 500 degree activation, 600 degree activation, and 700 degree activation. And you can see that in this case, the 600 degree activated carbon shows excellent capacitance of 300 farads per gram. Hence, we have used that electrode activated at a 600 degree. Then we have gone for ultra capacitor device, or the real device. So again, we have made a conventional kind type capacitor, and these are its performance. 5000 cycles, no change in the capacities. No change, no degradation in the capacitance. At a 6 ampere per gram, so we have discharged the capacitor, and it is still aqueous. So it can be operated up to 1.4 voltage. What is the power energy density? So earlier it was 30, here it can go little above 30, close to 35 watt-hour per kg at a power density of about 500 watt. And it can be optimized for about 400 watt per kg of power density. Still the energy density is close to 30 watt per kg. That was aqueous system. And Dr. Satish rightly told that the advantage of going to non-aqueous is you can lift the working potential from 1.4 or 1.2 to even 3 voltage or even beyond 3 voltage depending on the electrolyte. So here is the performance of non-aqueous ultra capacitor. So where we can go as high as 3 voltage. So it's double the voltage, operating voltage compared to the aqueous system. So you can see that this is the performances. The energy density at about 500 watt per kg is close to 45 now, and it can be stabilized up at about 15 watt per kg with your power densities of about 4800 watt per voltage. And so you can see that it can be performed, it can be cycled for 10,000 cycles in the lab. No change in the degradation. Of course, this is a typical for a carbon-based material because there are no changes in the electrode structure or composition or crystal structure, etc. It maintains. So 10,000 times you do charging and discharging, you get the same energy density or power density. And say a singly charged such a device can be powered consumer electronics maybe more than 30 minutes. So it means that the energy density of that device is increased. Use of waste derived materials. And that is conventional capacitors. So very recently, the development of sodium ion capacitor or potassium ion capacitor is also picking up. The merit is instead of a conventional ultra capacitor, moving towards a sodium capacitor or other potassium capacitor is these are all larger ion. So the solvation radius can be reduced. It means so when the solvation radius is reduced, it can be more mobile. Better mobility you can have. Why better mobility of ion is required? It can support high power density. That's the main reason. Otherwise, you can work with the H plus mobility or lithium mobility. So here we have developed very recently large size sodium ion capacitor, again using some agricultural waste. This acacia, so this tree is very much available in our campus. So we have taken the fruit or the dried fruit of that one and we have captured them, and after carbonization we got this kind of carbonized char, and it was activated using KOH, and you can see that a typical commercial level like a pouch cell we have made it. And what is its performance? These are its performance. So in previous cases, you have seen the energy density less than 50 watt-hour per kg. We have gone up to as high as 100 or close to 150 watt-hour per kg in case of sodium ion capacitor. What is the power density you can get? You can go beyond 4,000 watt per kg. And it can be cycled for 10,000 cycles. So we can go beyond that also in principle because there are no degradations. So a typical large size sodium ion capacitor was demonstrated, and it can be powered to glow a consumer product for more than 20 minutes or so. So very recently it was published in Energy and Fuels. So recycling of electronic waste is one of the ways to derive the valuable product. We know that these batteries are existing for last 50 years or so. Everyday Fujitsu or Panasonic, there are several, Energy Dell, there are many players in these dry cell manufacturers. What we usually do, so after complete discharge of this or usage of these dry cells, we throw into the environment. We have developed a mechanism or methodology or process to recover valuable materials from such electronic waste. We have dismantled it. Once you dismantle it, you get two products. You get a carbon rod and spent bovine. The spent bovine is nothing but 60 to 70% of manganese dioxide is present, and it can be one of the valuable materials both for supercapacitor as well as for the battery, because you can convert manganese dioxide into LiMn2O4, which is a commercially used lithium-ion cathode, and the same manganese dioxide can be used as a maybe pseudocapacitor, more closer to EDLC supercapacitor material. So what we have done was we have heated it to 800 degree in normal atmosphere. You get pure Mn. Okay, then you combine with the lithium source or lithium carbonate. Again, you anneal it maybe 650 degree for 12 hours. You get this material, LiMn2O4, and it happened to be a cathode material for lithium-ion battery. On the other hand, this is from the spent bovine. From the carbon rod, so you crush it, and it is a carbon rod, graphite rod. So you exfoliate, you get a graphene. Or sometimes you can functionalize graphene. So both are characterized using X-ray diffraction, complemented by Raman spectroscopy, the elemental mapping, percentage, whatnot. All material characterization one can take. So then we have gone for fabrication of the device. So both we have done so supercapacitor device and hybrid device. This is the hybrid device. What is hybrid device? So in case of symmetric device, you have a similar electrode, carbon-carbon. Here we have one carbon, another one is Li-Mn2O4. This is more like a battery. So what is the performance? This is the performance. What is the energy density you have here? Here as a 200 watt-hour per kg. This is closer to the battery's energy density. Hybrid device, closer to that of the battery's energy density. Battery's energy density is somewhere around 300 watt hour per kg. So this is 200 watt hour per kg. What is the energy power density? It can be as high as 10,000 watt. So both energy density and power density has been increased. Instead of dwelling on the symmetric capacitor, you move towards hybrid capacitors. How much is the cycle life that you can stabilize? So we have gone up to 10,000 cycles and it is nearly stable Coulombic efficiency. Of course, there is some drifting in the capacitors. And it can be demonstrated practically by powering a consumer electronics. A singly charged such a device, such a small device could power more than 10-15 minutes. So I'm done with the conventional capacitor and the supercapacitor. What is this supercapacitor mean? So we know the features of supercapacitors. So they are power devices. And we know the features of battery. They are energy devices. I think someone made such a question to the previous presenter. Is it possible to combine supercapacitor and battery? It is possible to combine supercapacitor and battery separate devices, but you will not be able to get the intended energy density and power density because there is an equivalent series resistance. So instead of combining the two devices in using a wire or a connector, why not if we have in a single device both features, the features of supercapacitor and the features of the battery, and you term them as a supercapacitor. So a supercapacitor will essentially consist of a battery electrode and another supercapacitor electrode. What is the use of? So we know that supercapacitor electrode can support for high power discharge of high energy quickly, whereas battery electrode can support for energy. So in a single device, if you have a characteristic of supercapacitor and battery, so you term them as a supercapacitor. So it is expected that a new device, so called a supercapacitor, is expected to deliver high power as well as high energy device, high energy density or high energy. So essentially you take one electrode of your supercapacitor and another electrode, for example, lithium cobalt oxide of a battery electrode, and you combine them in a single device with a suitable electrolyte, you will be able to develop supercapacitor. So here maybe I will take another 5 minutes to wind up my lecture. So this is one material, nickel ferrite at the carbon. So we have developed this material by means of combustion process, and it can be done in any MSc lab. So if we have a maybe 600-degree operating furnace, and if you have these components, it is possible to generate these materials, nickel ferrite. So these are the morphologies and element distribution and well characterized using conventional characterization techniques. That's not very important. Important is what is the energy density and the power density of this supercapacitor or capacitor. So this is the cycle life and power density and the energy density of a capacitor. They are not made up of, the electrodes are not made up of carbon. They are made up of almost a battery type material. In fact, these are all battery type materials. So these can be used as alternative anode for lithium ion battery and even sodium ion batteries. So they are battery materials. They can support for more energy, and the carbon can support for more power, and this is the performances. And we have demonstrated this the capacitor that we have made in our lab. So in the same way, why not cobalt oxide also can be used as a supercapacitor materials. So cobalt happen to be a very compared to other transition metal oxides. So this cobalt is having a good electrochemical activity. So we have made this by use of a fissile sol-gel process using SDS as a chelating agent or pore forming agent, and it was very well characterized using standard characterization technique. Then we have made the supercapacitor. So one electrode is carbon, another electrode is cobalt oxide, and the cobalt oxide also can be a alternative anode for lithium ion battery and even sodium ion battery. So they undergo conversion mechanism. It's a battery material. What is the energy density and the power density of the supercapacitor that you can get? So as high as 40 watt hour per kg energy density, and as high as 4,000 watt hour per watt per kg as the power density you can get. And you can, so such a supercapacitor can be demonstrated to work practically. So whenever my student develop any such devices, I ask them to demonstrate practically, either by making a functional LED or running a toy fan or anything. In that line, so we have recently also developed so this carbon quantum dot bismuth oxide composite as a supercapacitor material. So for this, we have explored a sustainable source, and we all consume. Most of us we consume milk. So maybe we either buy from the market or sometimes if you don't consume, so the milk becomes unusable. Or so there is an estimation that at least 10 the milk that is produced globally used. They are into the environment as a denatured. So what we have done was we have intentionally denatured the milk, the edible milk. So by keeping about 5 days at room temperature. Okay. So it undergoes a decay. So whatever the available component, carbohydrate, protein, or vitamin in the milk, so they undergo denaturation. They all having a carbon skeleton. What we have done was we have taken this denatured milk, so and subjected to hydrothermal treatment for about 2 hours at 160 degree. What we got, amazingly, we got carbon quantum dots. And this has been very well characterized using emission spectroscopy and HRTM, etc. We have used this carbon quantum dots as a medium to generate range of metal oxide composites, and one such metal oxide composite, bismuth oxide. We have also made manganese oxide, nickel oxide, etc. And here is one such composite. So to that you add bismuth source, and you get carbon quantum dot bismuth oxide nanocomposite, and it can be characterized using characterization technique, and how much amount of carbon present also can be quantified. And the very nature of formation of composite can be verified or examined using HRTM, and you can see that the presence of carbon and the presence of bismuth oxide, lattice fringes, and SAID pattern support the formation of composite. What is the performance of the supercapacitor? So we can see that, so it shows battery behavior. There is a redox peak, so confirms that there is a redox reaction taking place. What is the energy density and the power density of this supercapacitor? So energy density is as high as 800 watt hour per kg, and the power density as high as 8000 watt per kg. So we have tested it for about 2500 cycles, though there is some drifting, but after 1000 cycles or so, the capacitance or the energy charge stored is highly stable. Okay, so, and we have established so a laboratory prototype supercapacitor by following such steps, and it can be compared with, you can see that ours is the highest power density delivering supercapacitor that we have developed recently in our lab, and at your energy density of 32, except in this case ours is much better than what is available in the literature. So in this line, so we have also developed several other materials for application to supercapacitor. So nickel oxide, cobalt oxide, cerium oxide, lithium manganese oxide, and lithium ferrite we have developed, and their energy density and power densities are highly steady. So I do not want to dwell more on specific details of these things, and it can be very well obtained from these recently published papers. So one of the works on nickel oxide is, so we have generated nickel oxide by using a chip-based metal complex, and so using which we have made a supercapacitor. so which could deliver a possible energy density and power density. So I'm very much thankful to the editor of these journals. So this work was very recently covered as a cover feature, and it was highlighted by media and news media in several places. So in all, what we have developed is we have. Am I audible? Yes. Yes. So in all, we have developed electrode materials from sustainable sources. Anything you name junk consisting of carbon, so they are not junk to our lab. They are potential resources. They are sustainable resources. They are sustainable because as long as the growing of these trees are going to be, so they are going to be available as a waste. So we made use of such waste, either glass waste I didn't touch upon, and even PET waste we are doing, and many other resources we are doing. So we have generated either carbon or metal oxide using such waste, and applied them for energy storage applications. In this lecture, I have taken only supercapacitor or supercapacitor mostly, and so we are also using these materials for lithium-ion battery development, sodium-ion battery development, and potassium-ion, etc. And these are the quantifiable metrics that we have recently obtained for our devices, laboratory devices. The TRL level, I can say maybe somewhere we are between 3 and 4. So it can be scaled up for commercial level, etc. So in all, what we have done was, so maybe in the case, this I didn't touch upon, but so we have made composites from the sustainable source. So what we have seen is we get different morphology depending on the type of the source, and that leads to different conductivity and associated with the different redox process. So if it is a battery material, so we have a different redox process. If it is a EDLC or supercapacitor material, that is having more or better interaction with the electrolyte. So whether it is having a better electrochemical redox reactions or better interaction with the electrolyte, in either case you are going to get better storage device. That has been resulted here in high capacity or high energy density. That's why I told in one of the slides. So these days, so the research and development on the supercapacitor or capacity has taken different dimension. I don't just stop at the capacitance. I talk in terms of capacity, energy density, or specific energy or specific power, because the magnitude of the charge stored has become increased from microfarad, picofarads to farads to now energy density. So as high as 200 watt-hour per kg in case of hybrid device that we have developed. In case of supercapacitor, so we have developed as high as 80 watt-hour per kg. And other sources, they have moderate energy densities. These energy densities are much better than the energy density that you can get from the conventional parallel plate capacitor or condensers. So I think I'm mostly done. So I hope in near future we already have many test vehicles. Even I am seeing even in Pondicherry there's an electric vehicle completely powered by the electrical energy. So electric vehicle can go with the use of battery along with the auxiliary power to be supplied by the supercapacitors. So the conventional carbon-based fuels, definitely it is going to be decreasing as we progress. So we need to have a monitoring system, sensors for monitoring the our diagnosis of the combustion. Also, definitely we are moving. So many nations have already taken the electric vehicle policies. So we will be moving towards electric vehicle, plug-in hybrid vehicles, or EV, what you call. I hope even in our age itself, these efforts are going to be realized, which requires the storage devices. So essentially batteries and can be supplemented by the hybrid energy devices. So I usually tell this in my group during our meeting. So in future, so it's not going to be battery or supercapacitor, it's going to be hybrid device. So hybrid device is going to have the energy density that you can get from the battery and the power density that you can get from the supercapacitor. Okay, so it's going to be a complementary device. I hope so even in our age itself, it will be realized. So I would like to end this lecture by acknowledging funding sources as well as the hard work done by my research group. Thank you very much for your kind attention. I will be open for any discussion. Thank you.
Hello, sir. Can I ask the question, sir? Hello?
Hello, please. Yeah.
Sir, such an informative presentation, sir. And my question is, what is the role
Thank
of
you.
carbon dots in bismuth trioxide in the supercapacitor work, sir? What is the role of carbon dots?
Yeah, so we have done a pristine carbon quantum dot also as a electrode material. They mostly show some EDLC behavior, maybe little increased EDLC behavior. Your point is what it is what is doing the job of getting the composite.
Yes,
It
sir.
does it does the job of getting the composite. So it converts the bismuth nitrate into bismuth oxide. So these bismuth oxides are embedded on the carbon quantum dot matrix. So it converts the metal ions into mostly metal oxides because we have the medium of the aqueous medium. So the oxygen comes from the water, and these carbon quantum dots, they sometimes try to reduce the higher oxygen state to lower oxygen state in such a way that a stable oxide is formed. It acts as a compound forming agent.
Okay.
So when you use them as an electrode, that also contribute to the charge storage, definitely. When you compare with the composite carbon quantum dots, the charge contributed is less.
Okay, sir. Can we use any other quantum dots also, like MOS2 quantum dots, WS2, cadmium?
Definitely. So if they are going to show only EDLC, you are going to get the EDLC behavior. If they are going to give some redox process, definitely. So carbon quantum dots or even phosphorus quantum dots possible, and they can also serve the purpose.
Okay, sir. Thank you, sir. Thank you, sir.
Yeah.
Thanks, sir.
Yeah, so good afternoon, sir. This is Mahendra, sir.
Good afternoon.
Sir, I have a question that you have said that supercapacitor, no, sir.
Yeah.
The construction of the supercapacitor will be like a pseudo capacitor or else electric double layer capacitors, or it will be like a batteries, or in that construction type.
So the cell configuration and constructions are nearly same. Not nearly, it is same only. So only the materials used are of battery nature, and another electrode is a supercapacitor nature. It's a new terminology given to the hybrid device whenever you have one of the electrodes having the battery features. Not all the materials are having a battery feature, right? For example, so there are bismuth oxide, though it can be used as of course it can be used as an alternative anode, but not all the electrodes are battery electrodes. In that case, you call them as a hybrid device. I think I should have been clarified this. So, but there are ample amount of materials, they can be used as a electrode material for battery, either anode or cathode. So wherever one of the electrodes is a battery electrode, you term them as a supercapacitor. Otherwise, it is a hybrid device. That is the distinction. Construction and fabrications are nearly same. Either you can construct a pouch cell or coin cell or any indigenous size.
Thank you, sir.
Yeah. Yeah. Okay. Okay, so I think so if Pautira is a scholar or a PG student, they can visit our lab sometimes and they can experience 1 or 2 days. So with the permission from your supervisor, if you are a PhD scholar, I think so you can better experience that. It's a 1-day job or 2 days job. So getting the activated carbon from the any carbon sources has 2 steps. First step is carbonization. This is done at a relatively low temperature, maybe 300, 350 degree in air. So basically, you remove the moisture and other content, keeping the carbon alone, enriching the bio waste into mostly carbon-rich material, char. Then the next step is activation. Activation is to increase the surface area of the carbon char. There are different ways of methods of activation depending on the type of the activation agent that you use. As I told, you can use KOH and zinc chloride or phosphoric acid. Sometimes people use urea also as an activating agent. So basically what happens is these activating agents, wherever they are at a high temperature, they get lifted, vaporized. Wherever these materials were there, so that kind of pores are formed. So it's a carbon corrosion. So you cannot go very high temperature. You will end up with nothing. Carbon will be completely corroded. That's why we need to optimize maybe between 500 to 600 degree or so. So different methods. If you are really interested, you can fix up time with our scholars. Maybe after all this pandemic over, you can have a hands-on experience. And vacuum setup and also it has to be taken care. It should be done in the organ atmosphere, inert atmosphere. If you handle the carbon in the air atmosphere, you will get nothing. So it will become carbon monoxide or carbon dioxide. You need to have it's not vacuum. It is of course it's a inert atmosphere. It's not vacuum. You need to purge an organ, at least organ. Yeah. Yeah. So, so there are several books available. One of the popular book on capacitor is this. So I have that ebook. Maybe I'm not getting the author. Very popular author. So Scorsetti or someone. I have the ebook. So I can get you that. And so to know the basics of this double layer formation, and also you can get any standard electrochemical books. Maybe Southampton's electrochemistry group, and many such books are there. Maybe very specifically, maybe you can reach us. We will be able to either give the ebook or we will give the exact title authors. There are several books. And I don't know whether I should tell that we have also recently published one edited book that will give the basics of battery. So that's available in Amazon or any other purchasing medium.
So good afternoon, sir.
Yeah.
Sir, I am Dr. Vasant, sir. One question.
Good afternoon. Good afternoon, please.
Sir, while considering the power density, energy density of supercapacitor or this hybrid capacitors, so
Yeah.
what will be the effect of electrolytes, sir? Aqueous or non-aqueous will be the better? How will be the effect of electrolytes on these factors?
So generally speaking, for convenience of working, aqueous electrolyte is good.
Yes, sir.
So it means water-based. You take any salt and dissolve it in water, you get the aqueous electrolyte. This is very convenient. You don't need any glow box or containing inert atmosphere. All those things not required.
Yes, sir.
So the problem is the energy density will be limited because you cannot lift the potential beyond 1.2 voltage. If you go, so water will be decomposed or oxidized. It will produce hydrogen and oxygen. So your cell will be decayed or it will not serve the purpose. So in that sense, you need to go for a non-aqueous electrolyte.
Yes.
So there you can go beyond 1.2 voltage or 1.4 voltage, beyond the water oxidation potential or decomposition potential.
Yes, sir.
So, but the problem is working with the non-aqueous, you need to take care. So you need to be a little away from the moisture. So because otherwise it will become watery. Again, it will become aqueous. And especially if you are working on lithium ion capacitor, potassium ion capacitor, sodium ion capacitor, non-aqueous, so you need to take care of the environment where you are handling. So not like lithium environment or sodium battery environment, but you need to take care. So there the advantage is you can lift the potential beyond 1.2, you are going to get the higher energy density definitely.
Yes.
But again, the problem is you will compromise the power density. You can get the mobility of ions better in aqueous compared to the non-aqueous.
Yes. Okay.
Okay, so you can increase. So you have to compromise.
but it is acceptable.
And again, it is acceptable. It is acceptable. Again, so yeah. Go ahead, please.
Sir, yes, sir. So the Aquas doing the experiments in Aquas is acceptable, sir. Yes.
It is acceptable. So it is acceptable. So,
Yes, sir,
but certain materials you have to do in aqueous only. Certain materials you cannot use non-aqueous. For example, if you are developing hydroxide material, let's say cobalt hydroxide, nickel hydroxide material, you can only use aqueous electrolyte, mostly QOH. You cannot use a non-aqueous electrolyte. If you use such materials in non-aqueous electrolyte, you are not going to get redox property because there is an involvement of OH ion in the redox process. That OH minus is not going to be available in the non-aqueous electrolyte. You cannot expect a redox behavior. You will expect a EDLC behavior. The capacitance of the EDLC is relatively very less compared to the pseudocapacitor. You will lose the redox reactions in certain materials where it should be used suitable electrolyte, mostly KOH or NaOH or sulfuric acid, etc. Otherwise, so they will show only EDLC behavior.
Yes. Thank you, sir.
Yeah.
Yes.
So good afternoon, sir.
Good afternoon.
Sir, I am Nitya, sir.
Yeah,
Sir,
please.
it's a nice presentation. Sir, I have one doubt, sir.
Thank you. Please.
Sir, how to convert metal oxide carbon dots? Is this solid in nature or liquid medium, sir?
So carbon quantum dot you are talking about?
Yeah, yes, sir. Yes, sir.
Yeah, carbon quantum dot we initially got as a
liquid medium.
Liquid.
Yes.
That we have converted into solid.
Solid. Oh, yes. Sir, is there any process to convert from liquid to solid medium?
Yes. There are methods.
Sir,
yes.
Which method is predominant to convert from solid to liquid, sir?
Yeah. So there are methods which can be adopted in the lab. Yes,
okay,
simple method is just to evaporate on the hot plate. That's not a very effective way of doing the evaporation or getting the liquid into solid because there are no controlling in getting the morphology. The best method to use maybe lyophilization or freeze drying. It will retain the morphology of carbon quantum dots. It will only remove the moisture component. So lyophilization or what is that? Another name I told. Lyophilization or freeze drying.
Freeze drying method. Freeze drying.
Yeah,
okay, sir.
Freeze drying. That will retain the morphology of the quantum dots, whether it is a carbon quantum dot or phosphorus quantum dot or any other quantum dots. You will get the solid.
Thank you, sir. Thank you, sir.
Yeah.
Sir, good morning, sir. This is Sai, sir.
Yeah, please.
Sir, I have one doubt, sir. Normally, in the 3 electrode systems, whether it is a EDLC behavior, we can in the units we can write the unit as a farad per gram. Whether it is a hybrid or a hybrid-based material, we are using the milliampere hour per gram. But in the case of 2 electrode system, we are only using the farad per gram only. Is there? Can you give any?
Yeah, very good, very good. So I admire that you are working on supercapacitor field. So as you said, so this 2 electrode data that Satish also explained, it is a preliminary data or basic data to diagnose whether your material is EDLC or a redox material. So only you can stop only at that point. So do not quantify energy density, power density using 3 electrode data. So if any paper comes from any journal, we straightly reject it. Even so, we have changed it. 5 years back we have been doing that. But these days it's of no use. Energy density, power density calculation using 3 electrode data is not recommended.
Yes,
okay, so you need to use 2 electrode data to quantify the energy density and the power density. Now the question of using capacitance or capacity depends on the type of the material. If it is a EDLC material, you please go ahead and use farads per gram. EDLC material may be carbon materials. Wherever you are not going to get any redox peak in the cyclic volt diagram, you can straight away use farads per gram. When you get when you get redox peaks, proper redox peaks in the cyclic volt diagram, please feel free to use either coulombs per gram or milliampere per gram. it is a battery type of the material. Okay. Again, now the other point is, in the case of your device, to estimate the energy density and the power density, there comes the use of capacity or capacitance. Okay, so depending on the type of the contribution that you get, if the charge contribution is mostly by the battery type, you use milliampere per gram. Otherwise, you use farads per gram. So there is a compromise there.
Okay, sir. Okay, sir.
Okay, but this issue is not many people understand this. Not many people hide this. They don't admit it. Appreciate
So,
your.
I saw that in every paper in the two electrode system, we only prefer farad per gram.
Farads per gram. That's
so
correct.
we have to decide depends upon the behavior of the graph.
Contribution of the charge storage, definitely.
Oh, okay, sir. Thank you, sir.
But we should arrive the unit finally for energy density, whatever per kg. So
okay,
you have to select the unit properly.
Okay, sir. Okay, sir. Okay, sir. Thank you, sir.
Even if you use farad or milliampere per gram, final unit for the energy density should be whatever per kg.
Okay, sir. Thank you, sir.
Yeah. So it's a play with the voltage in both cases.
Okay, thank
you.
you.
You can interconvert capacitance and capacity using the voltage. You know, right?
Okay, sir. Okay, and also the people are using the electrolyte concern. Nowadays, from the beginning literature, they are using the aqueous electrolyte and move on the.
See, that's why you cannot simply move to the non-aqueous electrolyte. It depends on the electrode. For example, as I said, one example, nickel hydroxide or cobalt hydroxide, you cannot use a non-aqueous electrolyte. You are not going to get conversion of nickel hydroxide into oxyhydroxide unless the non-aqueous electrolyte is having a KOH or OH ions. It's going to behave as a EDLC behavior. You cannot use for all the materials non-aqueous system. Only for carbon-based materials or where the participating ions are not H plus and OH minus, you can go for non-aqueous system. Otherwise, you have to use the intended electrolyte. I think this need to be clarified. So, so it depends on the material. Yeah.
Thank you so much.
Sir, good afternoon, sir.
Good afternoon.
Thank you for a nice presentation.
Thank you.
Actually, the material has a porous nature in order to ion penetrate into it. Actually, what's the size of the pores, sir?
See, we don't have any designated pores. So you cannot have too much pores. As Dr. Satish told, if you have too much large pores, the stability of the electrode will be poor. You cannot have a very tiny pores. Then it is more dense matrix. There are no surface area. The percolation or penetration of the electrolyte is limited. So there are no defined pores. Maybe you can have a mesoporous and microporous. It cannot be too macroporous. The stability will be poor.
Okay, thanks.
Yeah. Someone has asked in the chat box, what will happen if you do in vacuum condition? I think it refers to the carbon generation. So you don't need to apply the vacuum for generating the activated carbon. You just remove the air or etc. by purging the inert atmosphere. You don't need to have the vacuum. Maybe with that people mistakenly they call it as a vacuum. It is inert atmosphere. No need to be a vacuum. You are not having a vacuum furnace. Jerry's Infanta, I think this clarification will be useful. It's inert atmosphere, not vacuum atmosphere. So I'm seeing the chat box. Someone has written he has studied, or Dr. Mohammed has studied in Pondicherry University. So alumni of our university. Thank you. Okay, so you have done with the Professor GC. G. Chandrasekhar. Okay, good. Thank you. Thank you very much. Thank you very much. Thank you. See you. See you.
Resami, do you hear me? Hello? Resami, do you hear me? Hello? Can you see your slide? Visible. It's a visible? Okay. ஸ்டார்ட் பண்ணலாமா? டைம் ஆமா.
Will you start, sir?
Yeah.
Yeah, thank you, sir. So, good afternoon to everyone. So, I heartily welcome you all to this third session. This session will be handled by Dr. S. Anandan, Professor, Nanomaterials and Solar Energy Conversion Labs, Department of Chemistry, MIT, Trichy. I welcome Dr. Professor Gayatri Prabha to introduce today's chief guest. Please, madam.
Good afternoon, all. Dr. S. Anandan obtained his doctoral degree in energy from the University of Madras. After postdoctoral research work in South Korea and Hong Kong, he worked as a visiting researcher in AAST Nagoya. He continued his research as pool scientist at CECRI Chennai. He moved to NIT Trichy, where he has been professor of physical chemistry and leads the research group Nanomaterials and Solar Energy Conversion Process. He has been awarded many prestigious awards such as DST SCRSC, Fast Track Young Scientist Award, Hiyoshi Young Leaf Award from Hiyoshi Corporation, Japan, for outstanding contribution to applied study for environmental conservation and protection, Best Teacher Awardee from NIT Trichy. He also serving as editorial board member for Journal Nanotechnology, Journal of Textiles, International Journal of Nanomaterials, Nanotechnology and Nanomedicine, Halligan published by elsewhere. He also serving as visiting professor for many foreign universities such as University of Melbourne, Australia, National Research Council of Italy, Fengjia University, Taiwan, University of Concepcion, Chile, Moscow State University of Technology and Management, Russia, and many other universities. He has completed more than 20 funded projects worth of 6 crores, which was sponsored by DST, TEQIP, India Australia Strategic Research Fund, CSIR India, and many more. He has published and authored more than 313 peer-reviewed international publications. With his broad knowledge and enlighten, I pleasure to invite Dr. S. Anandan to take the online forum to enrich our participants. Please, sir.
Thank you for the organizers for inviting me to deliver a lecture in the CSR forum, CSR funded project actually. I thank Dr. Peresami for giving me introduction to deliver my lecture in the supercapacitor area, the Nehru Institute of Technology, Coimbatore. Also thank organizer to introduce about things. So I thank Ms. Gayatri for the introduction. Okay, today morning I heard from the lectures by faculties and scientists who deliver lectures are very interesting and they touch most of the basic things actually. Okay, so in this concept I also deliver this lecture and third lecture, so it's very tough to give how to improve, how to give the most important things to my students actually, students or participants. So hope I will give my best to you. Okay, that's pretty good. So my topic will be ultrasound assisted synthesis of carbon nanotube metal oxide nanocomposite as a promising energy storage material. Okay, think that carbon nanotube. See, I put carbon nanotube. Actually, it is not my carbon nanotube now. After this carbon nanotube metal oxide, it is not carbon nanotube. It is unzipped carbon nanotube. So very interesting here. I hide my title here. that is called unzipped carbon nanotube. Okay, so we don't use carbon nanotube, but we get the thing called unzipped carbon nanotube. What is this unzipped carbon nanotube? When you think actually, it is called graphene. So graphene, carbon nanotube is all material are available in the market as such. So then we don't need this one. Okay, then the research is not interesting. So we want to make unzipped carbon nanotube. That means we have to purchase carbon nanotube and want to open it. That's our work here. So we want to open the carbon nanotube by some method, particularly ultrasound method, to get a carbon nanosheets, or we call particularly graphene nanosheets. So this carbon nanosheets will be how much far better than the initial graphene or initial carbon nanotube what we want to compare. That's our basic work we are projecting this lecture next 1 hour actually. Okay, my topic will be ultrasound assisted synthesis of carbon nanotube metal oxide. That means unzipped carbon nanotube. Okay, as a promising isotope material for supercapacitor applications. Okay, so I just give 1 or 2 slides about the introduction because most of the things are covered by the previous speakers. So just say the total energy consumption in India. That's very important. Okay, because everything talk about energy. So energy, we know we have to buy petrol today 100 rupees, 102, 103. Today once again 103 rupees petrol actually. Very expensive. Okay. So we get the people are saying now more power cut will be possible in next few years actually. Then how do you get energy actually? So then we have to store energy. That's very important. We have to store energy. So we can prepare energy by different methods like wave energy, wind energy, geothermal, tidal, solar, bio, okay, and green energy also. But what is very important here? We have to store energy. Storing of energy is most important to get a lot of energy for.
Sir, excuse me, sir.
Yes.
Sir, slide is not moving, sir.
I think so. Okay, 1 second. 1 second. Okay, I'll go this side. I can see my slides are moving.
Yeah, sir. Sir, can you go the presentation mode?
When I put presentation mode, you are saying not coming actually. That's why. 1 second. Stop presenting. Okay, just 1 second. Share. You want entire screen share or tab? Which is better for you?
Sir, entire screen.
When I go entire screen and then you can see now.
No, sir. No, sir.
Now you can see is better. Now you can see my slide.
Sir, no, sir. As previous slide, as same for this slide, sir.
Now.
Such the same. So there is no other movement.
1 second. Now first slide.
Yes, sir.
Second slide.
Yes, sir.
But
okay,
it is not in the mode of
presentation.
Presentation mode. Okay, once again, I'll check. Put F5. You are saying not moving. Okay, now which first slide?
Yes, sir.
Second slide.
Sir, it's not moving, sir.
That's why. Now?
No, sir.
When I go for this presentation mode, it is not moving actually.
Okay, sir. It's okay. Thank you, sir. Thank you.
Now you can see my slide. Okay, first slide is okay. Second slide, okay.
Okay, sir. Okay.
Second slide. Okay, I think you can view my full slide entirely, correct?
Yes, sir.
Okay. So this energy scenario is very important here. So when you talk about India consumption energy, actually, we can see we are using mostly coal. 40% of our energy we get for our electricity, everything will be coal, and remaining 27% from consumable like renewable solar energy, etc. And 25% we are using will be oil, and 6% will be natural gas, and 2% will be hydropower, and 1% will be nuclear, and other renewables will be 0.5. So we can see still we are using coal. When you use coal for a longer period, what happens? Your resources will be empty one day. After some 20 years or 30 years, your resources will be empty. Once your resources are empty, we have no energy. So we have to go for modern energy by using your other source. Or we can better way will be store energy. Energy storage is better compared to your this one. Okay. So energy can be prepared by many ways, like natural gas, nuclear power, plants, fossil fuel, solar cell, etc. Fuel cell. But we want to save energy is most important. Okay. Save water is very how much important. Same thing. Save energy is most important in day-to-day life. So when you want to save energy, we have different types. One is called batteries we can use. Other will be supercapacitor. So when you go for batteries, its power density will be good, but energy density will be less. That may be a problem for starting up. When you want to start up the engine or anything, it takes some time actually. So as a supercapacitor, energy density and power density both are high, so you can give a very good value actually. That's the difference between your batteries and supercapacitors. When you go for batteries, lithium-ion batteries, metal-ion batteries, sodium-ion batteries, lead-acid batteries are used. But you know about lithium-ion batteries, okay? Lot of advantages are there, but chemical-wise, it's some problem actually. Okay. When you go for supercapacitor, we have symmetric supercapacitor, asymmetric supercapacitor there. There's already a lot of lectures given by today morning, so I don't want to go in depth. So what is supercapacitor and why it is important actually? We want to talk about only with respect to capacitor and batteries. We talk about capacitors. Capacitors have energy density, high energy density, but low power density. Whereas batteries have low energy density, high power density. So in order to make a bridge between these two, we have to draw a Ragon plot, and we can say this energy density of power density of your supercapacitor should be increased. Therefore, it should be far better than your capacitor and batteries. Therefore, supercapacitor is a unique electrical resource system that can store much energy than conventional capacitors, and that can produce high power density than batteries. So supercapacitors are better than these capacitors and batteries. So very important here, batteries can store more energy, but we can see cannot deliver quickly. So supercapacitor can deliver quickly. That's the advantage of supercapacitor. Okay. So we can go for supercapacitors compared to your capacitors and batteries actually. That's the advantage of your supercapacitor. Okay. When it comes to supercapacitors, okay, already this is my last slide about the introduction. When it comes to supercapacitors, we must have some important things called electrolyte, separator, and current conductor. So when you use the electrode, we have used a material. Which type of material we have used? So we can use a carbon type, carbon black, okay, or carbon powder actually, okay, amorphous carbon. We can use, yes. But which is better? Why are people going to carbon and to graphene? Because of high surface area. So we need a high surface area is better for your electrode surface. Okay. When you use this, you know what electrical double layer capacitance, carbon give electrical double layer capacitance, whereas metal oxides give your pseudo capacitance. So which is better actually? Metal oxide is better. Yeah, metal oxide is better for pseudo capacitance, and carbon nanotubes are better for this one electrical double layer capacitance. But we want a hybrid capacitor. We have to mix these two. Okay. When we talk about metal oxides, we take a bulk metal oxide like TaO2 or zinc oxide, for example. Okay. We bang up, you know everything, but we don't surface area. Surface area may be less. But when you prepare the same metal oxides in another size, actually, you are increasing the surface area. Therefore, high surface area material is good for your pseudo capacitors. Therefore, we choose the high capacity material, nanoparticle or carbon with a high surface area. Second point, porosity. So porosity will be very, very important because of the movement of electrons and ions actually. So you have to maintain a good material, okay? Good porosity material we need actually. Not a very big size. We want a porous material with certain size actually. That's a very important point. Then third point, high electronic conductivity. So compound should have a electronic conductivity, very important. Like graphene has good conductivity, we need actually. And last one is low cost and environmental friendly. So if you choose, some people use coconut oil, burn carbonization actually, or they can use any waste particle into carbonization and prepare actually. Okay, so carbonized form of carbon. That means you have to burn the material and waste material and get carbonization, and we can use. So low cost. And it should be environment friendly. When you burn also, it shouldn't toxic to other people. So environment friendly is most important to choose an electrode. Okay. Second method, electrolyte. So mostly in the case of your things, people use liquid electrolyte, that is aqueous electrolyte, like sodium sulfate or KOH, mostly they use. Okay. So in this, we have used the electrolyte better will be pH neutral. pH neutral will be much better because the electrolytes are conductivity will be there, therefore problem. And second thing, stability and thermal stability also you have to concentrate to get better, to act as a good electrolyte. Then separator, you have to separate these things, you need a separator. Separator should not be conducting, therefore non-magnetic, and should be low ionic resistance. So what we can choose, we can use the membranes, particularly biopolymers, like cellulose-based membranes we can use. Okay, cellulose polymer we can use as a separator to get a good thing actually. And last one is the current tractor, which may be a mechanical strength, high mechanical strength, high conductivity, and low resistance. These are all things. But what we want to concentrate in this talk actually, mostly the electrode surface, electrode, which metal we have to choose. Okay. So now people are supercapacitor starting from carbon black, carbon amorphous carbon, many things actually. Okay, charcoal, everything, graphite, etc. But we want to use, because research carbon nanotube, it's already 20 years old actually. Okay, so no one is interested. Graphene already it is also old nowadays because many people are publishing papers. Many people are publishing papers, 5,000 more than papers every year actually in this material actually. Then how we have to stand in a supercapacitor work actually. So we need a material which should be somewhat different. So what we think actually, we want to think a material, carbon nanotube should be unzipped. Okay, that means you know what is graphene? Graphene is a sheet. Okay, graphene is a sheet actually. Okay, graphene is a sheet. You know graphene is a sheet actually. So a graphene sheet. When graphene is a sheet actually, okay, so we know when graphene is a sheet, what happens actually, when graphene is a sheet, we can roll it to a carbon nanotube. That's very important. So graphene is a high material, very good material. When you roll it into a sheet, it forms carbon nanotube. But carbon nanotube is old. So what we think, whether we can open the carbon nanotube and get different properties. So we think that opening of carbon nanotube. So how to open the carbon nanotube? So researchers are finding literature, a lot of groups open the carbon nanotube by many different methods, by longitudinal opening, like we call unzipping. What is unzipping? You have a zip in your purse, okay, by zipping a purse, if some crack in between, what happens? Some crack in between, actually, you can put your hand and just open it. So you need don't need your knob open actually. So if there is something crack inside, you can open the zip like unzipping. That means you can make your graphene into sheets for carbon nanotube, open your carbon nanotube because sheets. So we think that open your carbon nanotube to make a sheet which give high properties like more high conductivity or high surface area compared to graphene. So we think to unzip your multiple carbon nanotube to make a sheet. That's our aim to do research in this part. Okay. So in case of your carbon nanotube opening, a lot of methods are there. Wet chemical method we can use, or dry processing technique you can use, or this method gives a very good storage capacity. We found these compounds have very good high storage capacity in this system. Okay. So when you go for compound opening, actually, there is a material called, you can just see multi-wall carbon nanotube is here. When you do hydrothermal method, you can make a carbon nano ribbons. You can see the carbon. This will be. I can show some in my opening clear images. So carbon nanotube open to sheets like this. If you use a ultra high power dynamic extracting method, we can get your unzipping like this forms. Or use your effective oxidation process, you can get sheets. Or oxidation process, you can get your compound sheets, ribbons. Tour method is one of the method literature available. You can see sheets are formed. Arisen plasma method, okay, unzipping. And modify MS method, we get a CGN. CGN is called curved graphene nanosheets. The graphene nanosheet will be like a curve, like a curve shape will form. It's a curved graphene nanosheet can be formed. And other one will be quasi graphene nanosheets are formed when you use the catalyst RuO2. So now we find literature, lot of things are there. But what we want to prepare, we want not to prepare this method. We want to go by ultrasound approach. Why ultrasound approach? What is ultrasound? Ultrasound nothing but sonication. That is sound in the form of waves. Okay, sound waves. Using the sound waves, we want to prepare a nanoparticle, or we want to open the carbon nanotube to carbon nanosheets. That is our aim. We want to. So what is ultrasound actually? It is nothing but a wave phenomena. Starts from 20 Hz to 200 megahertz. So below 20 Hz will be sound waves, which will come, which will produce by grasshopper, That's okay. We call infrared sound waves actually. Between 20 Hz, 20 kHz will be they can produce the acoustic waves. Mostly the animal, dolphin and bat, they can use these acoustic waves actually. And above 20 Hz kHz to 200 MHz will be we call ultrasound wave, which human can't hear. It will be useful for medical purposes. For example, scanning your body or scanning in the mother's womb, whether baby will be male or female, can be used. So ultrasound is a very easy method. We don't want any reducing agent first of all, we can produce. So we can use this compound to make a opening of your carbon nanotube to unzipped carbon nanotube. So that's called unzipped ring opening, unzip opening of your carbon nanotube. Okay, that's our approach. We want to use ultrasound mainly for. We don't use a bath type. Very important. We use a on type ultrasound, not bath type. Okay. So first topic we want to discuss here. Presence of tin oxide nanoparticle intercalated unzipped multi-wall carbon nanotube via ultrasound assisted synthesis for symmetric supercapacitor devices. So what we do, we take a carbon nanotube and we want to apply ultrasound. When you apply carbon nanotube, taking the water and just make sound waves, we find that carbon nanotube is not open. Okay, it may be broken. It may be broken. So it is not open, it's broken, very important. It may be broken to small particles actually. So we think that we need something to make a ring opening by long cutting actually. So for this we use a Lewis catalyst like tin chloride. Okay, tin chloride may be one of the Lewis catalysts. So we use the Lewis catalyst to open the ring opening. Okay, so ring opening may be one of the process. So we can pick Lewis catalyst. We add Lewis catalyst to doing the ultrasonication, and then you apply ultrasound. When you apply ultrasound with this one, we find the opening actually. But what we do, before we take a pure multi-wall carbon nanotube, we first take the multi-wall carbon nanotube and oxidized it because we want to have some functional group for the ring cleaving actually. So we take a compound, that's your multi-wall carbon nanotube, and treatment with a modified MS method like sodium nitrate and still for 1 hour and then add K1O4 and then we still for 4 hours and heat at high temperature 100 degrees Celsius. We found brown color form. Then we add, because the brown color form due to your manganese Mn plus 5 to Mn plus 7 to Mn plus 2 form. Okay, that is why it may be color change brown. And then we add hydrogen peroxide, we change yellow color. Then we take this compound and check XRD, IR, NM, and then TEM, SEM, etc. We find that the multi-wall carbon nanotube has no functional groups. But when you oxidize by this method, we find epoxides and ketone groups, aldehyd groups, or phenol groups are present in the compound. Okay, this is called oxidized multi-wall carbon nanotubes. Okay, we did your multi-wall carbon nanotube into oxidized multi-wall carbon nanotube by modified MS method. First step. Then second step, take this modified oxidized multi-wall carbon nanotube in a beaker and then add the Lewis catalyst tin chloride in presence of ethylene glycol and we purge the atmosphere for 3 hours. We find this compound will be unzipped, the carbon nanotube will be open to unzipped multi-wall carbon nanotube. So then how do you confirm this unzipped multi-wall carbon form actually? We can go one by one characterization details and then come to your fabrication because it's supercapacitor. That's very important. So we go to we can see here, the multi-wall carbon nanotube has no functional groups. When you do by oxidized hydrothermal method, modified MS method, it will be oxidized to oxidized multi-wall carbon nanotube. We have epoxide group, phenolic group, aldehyd group, carbon group will be there. When you apply ultrasound and add tin chloride, actually, tin chloride is converted into tin oxide. You can see here, tin chloride is converted into tin oxide in ethylene glycol, and your tin oxide go under the surface and separate the sheets into layer by layer and form a sheet particle. So ring opening takes place and also sheets are formed doing this process actually. So we confirm by characterization tools, okay? Characterization tools actually. The first one we go to your XRD. So multiple carbon nanotubes show a peak in XRD, 26.26, approximately 26 actually, okay? And it will be 002 HKL plane. When we oxidize by Monte-Hammer method, this peak is missing. You can see the red one. There's no peak here actually. That means multiple carbon nanotube will be oxidized to oxidized multiple carbon nanotube. That means we have included your functional groups. Once you include functional group, then you apply your tin chloride and your ultrasonication. We get the compound Once again, graphene nanosheets. Graphene nanosheets are formed, but we cannot see, but you can see a peak at 25, you can think actually. That peak may be belong to your tin oxide, because tin will be reduced and form on the surface of carbon. The peaks are belongs to tin oxide peaks. But still we have doubt, okay? Anyone all have doubt? We want to confirm by other methods. Very basic tool will be available, any laboratory will be FTIR. Just multiple carbon tube, we can see two peaks of the carbon double bond, carbon peak, and OH stitching will be there. When oxidized, we can see COC, C double bond C, CO, CH. That means phenolic, epoxy, ketone, aldehyd peaks are there here. When you apply with ultrasound tin oxide, we notice tin oxide peak actually, in addition to these peaks. Okay, so this confirms that there may be ring opening takes place. It's the initial state. Okay, we just go into the next calibration tool. So we don't want UV spectra, just basic tool, any laboratory. Multiple carbon tube, no peak. Whereas when you go for your oxidized multiple carbon tube, you should the peak at 227. It may be your N2 pi star of CC bond. Carbon-carbon bond will show peak at 227. That can be noticed. When you apply tin oxide in chloride, we notice the peak around 210. It may be a solvent peak, for example, but we are used the powder method. Powder we can do. It's not solvent peak. It may be a peak due to your tin oxide, or 227 also there. It may be carbon-carbon bond. But still, it is not a good tool for consume or compare. We go for your TGA. TGA is a tool for stability method, just for supercapacitor. I just did supercapacitor. Multiple carbon atom is stable, almost stable. When you go for oxidized, we can see up to 153 degrees Celsius, removal of oxygen term up to that temperature. Above the temperature will be, we can see it may be impurities or carbon compounds are removed. Okay, our remaining 42% will be, we can see it may be your all carbon burnt impurities. Similarly, your unzipped oxidized multiple carbon tube and unzipped multiple carbon also shows same point of peak. Confirm the compound as remove the 3 different phases of present in this system. Okay. Very important tool for compare this carbon nanotube into graphene nanosheets. It will be by D/G ratio. Okay, D/G ratio is used for very important applications. That is called your. We see the multiple carbon tube. The D band will be less intense compared to G band. D band is less intense. That means if all the carbons are sp2 bond. A simple system. Okay, it shows that when D band is less than G band, we can say sp2 bonds are plus the carbon actually. Okay, when your multiple carbon tube is converted into oxygen multiple carbon tube, you can see there's improvement here. So there may be some epoxides or ketones, etc. There, therefore D ratio is improved. Then you go to your oxidation method. Your D will be increased compared to G. This confirms that compound is sp2 compound is breaking into sp3. That means your ring opening occurs. So this is a basic tool which confirms the Raman band. We can confirm the carbon ring opening. That is your sp2 to sp3 bonds are formed here. So it shows that there may be not a ring. The ring is open. This is a basic confirmation. But still, we want to see. Still, we want to see your SEM or TEM actually. Okay, SEM or TEM. So we went to your SEM image. So this is a real SEM image. Okay, we did actually. You can see carbon nanotubes are here. Okay, when you do oxidation, see, still we find the carbon nanotube. Still we find the carbon nanotube. Okay, partial disappear there. But when you see this oxidation with the sonication with tin oxide, we can see it, all the bonds will be gone. All the bonds will be gone actually. This says that carbon nanotube is converted into sheets maybe. But SEM is not a good tool. But if we want to improve, we go to a TEM. You can see the TEM image. Carbon nanotube structure will be similar like this. Oxidized carbon nanotube also almost same. Some brokerage will be there. But you can see single carbon nanotube. It will be oxidized carbon nanotube. Still, it will be an oxidized carbon nanotube structure will be retained. But when you do with ultrasonication with tin oxide, you can see the structure will be broken. So you can see sheets are formed. Okay, sheets are formed. And some of the compounds will be, you can subtle image. That means you can see some of the things will be subtle carbon nanotube. So we can see here, in this case, the bond structure, calculating SAD pattern matching with the XRD, is confirmed the ring opening takes place. Okay. Carbon nanotube is amorphous by SAD pattern. When you use tin oxide, it will be amorphous with crystalline forms are there. And you can see it has tin peaks are there actually. It's confirmed that carbon nanotube and tin oxide are anchored on surface and still it has good material actually. So semi-image confirms. But still, we have doubt actually, carbon nanotube is opened or not. So what we try, what we do, carbon nanotube, what we do, we oxidize the carbon nanotube into functional group actually. So we think that why not we can take a carbon compounds with functional groups. So we take a simple carbon compound, 1-pyrene carboxylate, okay, similar to your carbon nanotube, oxide carbon nanotube, which have a functional group, aldate group actually. So we take this compound and put your tin oxide, tin chloride, Lewis catalyst, and then sonicate here. And we find this compound also show the COC peak and other peaks are there. Okay, so this double bond, carbon-carbon double bond, CH stitching are somehow missing actually. And we just look into the semi-image, down one. Okay, when you look into the term image, as you can see, it will be sheets. Okay, this is the confirmation. We think that carbon nanotube open. What is this about? We have doubt. We did sonication for 3 hours, the carbon nanotube. So why we take 3 hours? Why not in 30 minutes? Why not in 60 minutes? So we go for 90 minutes when we do sonication, we take a sample and then we do temp. When you do 90 minutes sonication, check the temp, you can see the compounds are breaking actually. You can see the structure is still maintaining the double carbon-carbon bonding will be there. That is your carbon atom structure pretty time, but some disturbance there. You can see it's opening, breaking there actually. So this may be 90 minutes is not sufficient. That's why we take 3 hours to break the compound. So we confirm by taking small compound and we confirm the compound may be break. That is carbon-carbon cleavage. Okay, you can see this is called a CC bond pyrolysis. We simply say CC bond pyrolysis. Carbon-carbon cleavage space. We use a Lewis catalyst and ultrasound actually. That's a proof. We give the compound ring opening of your carbon nanotube. Okay, into carbon nanosheets. That's our proof. Okay. So once we prepare the material, we want to make a supercapacitor. So prepare supercapacitor, always everyone with the standard material will be 80% they use the prepared material and 15% they use the Vulcan XC carbon. This is a standard for any method. And PVDF, we can use PVDF as a binder actually. Okay, so 5%, and they make a with the solvent N-methyl preloading. They make a slurry, and the slurry they can coat on the nickel foam. In our group, we coat nickel foam. Even we can take stainless steel or glassy carbon. So we coat here nickel foam, and area of the stream foam will be 1 square centimeter. Then we use this not 3-electrode system. We use the 2-electrode system here in this case, and use mostly Na2SO4. And some cases we use also KOH. So we use the electrolyte, aqueous electrolyte 1 molar Na2SO4, and we make a supercapacitor device actually in our laboratory. So when you check the multi-wall carbon nanotube, a 2-electrode device, we can find this compound shows a graph here. Okay, the current will be less. When you go for second one oxidized form, it will be improved. When you go for unzipped metal carbon with tin oxide, you can see a very broad curve with no oxidation reduction potential. With this broad curve is a symptom of your supercapacitor. It can store a lot of energy. So this compound is much better than the other one. So we find that compound, this first curve will be with 1 molar sodium sulfate. We find the curve will be very broad one without any oxidation reduction potential. It can be stable. And we do a different potential, same thing, at 20 millivolt to 160 millivolt. The current potential will go on increase actually. This shows that the compound will be better for this one. Okay, it forms a trapezium inside. You can see triangle form, rectangle form, trapezium inside. Good for stable actually. Okay, we do this one with 6 molar KOH. These are the conditions generally used for making supercapacitor. They use standard solutions actually. So we use the standard electrolyte 6 molar KOH. We find this is less potential compared to the previous one. The curve will be like this. So we use this different potential. We can see this will be a trapezium like model will form. So this will be like a trapezium. So this can be another form, stability we can choose. Okay. So among these two, which is better solvent we tried in our research, and we find that 1 molar sodium sulfate is better compared to your 6 molar KOH, because 6 molar KOH will be mostly in a basic site and this will be near to a pH near to pH neutral. So we use your 1 mole of sodium sulfate as a better solution for our system actually. So when you draw this plot, when you do this curve at different scan rates, and we calculate your electrochemically active surface area SCA for this method. Generally, SCA we have to calculate by surface area method also, BET or anything, but we calculate by electrochemical method, electrochemical active surface area. Okay, we find this with 1 mole of sodium sulfate, active area will be 0.0515. With your 6 mole KOH will be 0.0125 above. So this concludes that 1 mole of sodium sulfate is far better for this application compared to your 6 molar KOH. So we find this 1 molar KOH is better for our system activity. Okay, we calculate the surface area for this will be 2.58 centimeter square for 1 mole of sodium sulfate and 0.63 centimeter square for your 6 molar KOH. So that's calculations we do. Use the formula given in the bracket. Okay, see electrical double capacitance equal to SK equal to CDL by CS. That is your capacitance, double capacitance by current density. Okay, different between current density actually we can calculate. Okay, so then we do GCD curves, galvanostatic charge discharge studies. That's a very important property for your supercapacitor studies. So we have to time versus point drop we found. We found your unzipped metal component tube is far better compared to your oxidized and metal component tube. Similarly, we do your charge discharge cycles. Okay, so as different times, again, 24,000 seconds actually, we find the compound stable, same type of curve we notice. So it will be a good specific capacitance. We can find charge discharge capacity will be always neutral or same. Okay, after 20,000 cycles also. So then we find this compound at different scan rates. Okay, different current density, how it looks charge density curve actually. Okay, we can find it may be better for 0.5 milliamps per centimeter square is better compared to 5 milliamps or 3 milliamps or 1 milliamp square centimeter. So 0.5 milliamps square is better actually. Then with this we calculate your charge density and current density and find that specific capacitance formula 351 Farad per gram for your unzipped metal component density, and we can find it will be formula we use will be capacitance will be formula is known formula only. So we use this one and find compound show 351 Farad per gram for your unzipped metal component tube. Oxidized will be 110 and multi-wall component tube 14 in our laboratory. But if you go look in research, it will be 14 from 10 to 40 will be there. 10 to 40 will be there for multi-wall component tube. And in our laboratory, we get 14 Farad per gram is the answer. So we do the same with 6 molar KOH also. And we find the charge discharge, everything will be less compared to the 6 molar, 1 molar NaO into S4, it will be less, answer will be 148 Farad per gram only. Therefore, we feel that 1 molar sodium sulfate is far better compared to this one. Then we find rough and plot energy density versus power density for this curve for these two samples. We find this energy density and power density is much better for 1 molar sodium sulfate compared to 6 molar KOH. So we use the 1 molar sodium sulfate as a best standard for our system. And we also make some small supercapacitor pouch pack, etc. in a laboratory, and we do some other applications. So also we confirm this stability of the electrode by using a electrochemical impedance spectroscopy. Okay, so the compound is stable or not. So using this electrochemical stability impedance spectra, the stability of the compound is found almost okay for us. So we find this compound unzipped metal component tube will be good for our future studies. Okay, it will be good for long stability, will be proved by electrochemical impedance spectra studies actually. So comparison. Always we have to compare these studies with other compound like tin oxide with single wall component tube, tin oxide with RGO, tin oxide with carbon nanotube, or multiple component with tin oxide, or tin oxide with the normal carbon. We find this our work will be much far better. You can see a 351 Farad per gram is much better compared to other studies. So on our ultrasound method will be far better. Okay, that's why we choose our method will be much better. So we find the first conclusion for this one. We find the SNO2 catalyst with the Lewis catalyst tin oxide. We open the compound, ring opening occurs in the case of your carbon nanotube to unzipped metal component tube, and this compound has good stability and good electrochemical stability and show good capacitance. Okay, 351 Farad per gram. You can ask, sir, why use particularly a Lewis catalyst, tin oxide, tin chloride? Why not we can choose other catalysts, other Lewis catalysts? So you can ask, whether this is due to playing by tin oxide or playing by your ultrasound, which is playing a role here. So we just think change the catalyst tin oxide by other Lewis catalyst titanium chloride. So when you choose titanium chloride, you can see multiple carbon nanotube looks like this. Oxygen multiple carbon nanotube will be almost same. And when you unzip TaO2 with titanium chloride as a compound, you can see this unzipping can be noticed. Okay, so this confirms that we can choose titanium chloride also a Lewis catalyst, and we can try this compound. So same method, instead of tin oxide, tin chloride, we choose titanium chloride as one of the system, and we found this compound also show good stability. We find this XRD. So you already know this multi-organ oxygen molecule. We just see titanium oxide. The extra peaks are due to TaO2 formation. So XRD we confirm. IR also almost same to previous one. Okay, ring opening I would think can be seen, and UVS TGA just to measure stability of the compound. Stability of the compound is good for using this compound actually. And Raman, you can see clear image D by G ratio. D by G ratio, D bond increases, sp2 bonds, sp3 bonds are found more compared to sp2. That means the compound's ring opening occurs. That's the stability we can prove here. We can prove here the stability of the compound actually. So this is a dummy image what we did in the laboratory. So we see the oxidized compound at the top and the TaCl2, the compound, all the compounds are broken. That's why this is a sheet-like morphology. Titanium peaks are seen in the SAD pattern. Okay, that's pattern. SAD pattern looks amorphous in both cases. Okay, that's our advantage here. So with cyclic voltammetry, we make a supercapacitor and we find this device. We see very broad curve. Titanium oxide shows a very broad curve actually. Okay, in 20 millivolts scam in 1 mole of sulfate. Since we take 1 mole of sulfate, we just give the value 1 mole of sulfate. But what we do two potentials. One will be 0 to 0.8 volt. Other will be minus 1 to 0.8 volt. We give two potentials, and we give upon the two potentials, which is far better. We find this minus 1 to 0.8 volt. When you do the scale, it is far better compared to 0.0 to 0.8. So we have large window can be seen here. Large window is better for supercapacitor compared to small window. The large window can be chosen here, and we see no oxidation peak in the case, and this compound has good cyclic stability can be noticed. So we calculate the SK here. SK will be very high value, 10.61 centimeter square. We can achieve this compound, and we calculate your charge discharge studies by Gardner-Stone charge discharge method actually, and we find this compound shows 195 farad per gram with the voltage 0.0 to 0.8 volt. Okay, window is less. The window is more. There's next one. The window is more, minus 0.1 to 0.8. Answer will be 475 farad per gram. So that's the difference. So we can use a low window. It will be only 190 farad per gram, and we can see with different scan rates and different current densities actually the compound has good stability is noticed. But when the scale will be increased from minus 1 to 0.8, okay, minus 1 to 0.8, it has a very broad cycle, and capacitance will be increased much better, 475 farad per gram, 3 times more compared to previous one. Therefore, much broader window is far better for making the supercapacitor applications. So that's the conclusion we arrived in this case actually. So, and we do stability. Stability is also good in this compound, and we find this compound as comparison with the other TaO2 catalyst, Lewis catalyst actually, like RGO, but the TaO2, TaO2 with the different morphology method, graphene TaO2, CNT TaO2, etc. We find our method will be much far better. 470 farad per gram is much far better compared to the previous published work by different synthesis used. This confirms that unzipped multiple carbon nanotube is far more better compared to other applications. So we think that carbon nanotube unzipped is better actually. Okay, that may be one of the area we are working at. So how to improve further this compound? We are going to think because we have carbon nanotube. So how to work further to the compound actually? There's a conclusion of this part. 470 farad per gram will be better for TaO2 compared to the scale window opening you noticed. Okay, we published already here. So how to improve further the system actually? We think that we can mix two different sheets we can mix actually, and we can check whether it's possible or not. So what we do, we take a RGO, and boron nitrate nanosheets, and we put another composite, nickel hydroxide, ternary nanocomposite. We just tried it. So we prepared a boron nitrate nanosheets in the laboratory by using melamine as a catalyst, and then we coupled this with a graphene oxide to RGO, and we improve the sheet morphology, and then we add nickel oxide to increase the supercapacitance. We want to try in the laboratory. So how to prepare? First we prepare boron nitrate laboratory starting from boric acid, add melamine in heated high temperature, and then calcinate at 500 degrees Celsius. We get your boron nitrate nanosheets. So we prepare graphene oxide starting with graphite by Amber's method, and we get your graphene nanosheets. So both graphene and graphene nanosheets taken in a another method, and add your nickel nitrate precursor, and we put and then we sonicate for some time, 1 hour, and then heat the temperature, high temperature 1 degree Celsius for 24 hours, and then autoclaved for another 24 hours. We get your RGO, boron nitrate, nickel oxide nanosheets. We can get your sheets can be formed. When we look into the image, it looks like a flower shape morphology. Okay, that's important point. So mechanism here, the graphene nanosheets combined with boron nitrate, it form a interaction between graphene and boron nitrate, form big sheets of form, okay, layer by layer sheets of form actually. And then we add nickel oxide, it will act on both the boron nitrate and nickel RGO sheets. Then we with this we growing at high temperature aerosol method, it form a petals like morphology, and then due to self-assembly and ring opening method, it grow into a marigold flower-like morphology. You can see it forms a marigold flower-like morphology. So RGO, boron nitrate, the ternary composite forms like a marigold flower-like morphology can be noticed. So this compound is much better for other applications actually. Okay. So we compare first with the XRD, boron nitrate peaks higher, boron nitrate nickel oxide we see nickel oxide and boron nitrate peaks higher. RGO nickel oxide peaks are compared actually, nickel oxide RGO is senior, and RGO boron nickel, you can see the peak here, very important here. This peak is made for RGO boron nitrate will form two different peaks. They confirm that both RGO and boron nitrate have an interaction here, and that's why the peak will be separated and form this structure. This can be confirmed by XR. Then comes your FTIR. This is a very basic data actually we always choose. Boron nitrate form here, and boron nitrate with the nickel oxide shows peak, almost nickel oxide peak will disturb. In RGO nickel oxide also we can see nickel peak, but in the case of RGO boron nitrate we can see both RGO and boron can be noticed. Okay, simple XR. So SPS is a very important tool here. We want to confirm your SPS. So we see the boron nitrate peaks, okay, and carbon peak will be there, and oxygen peak will be there, nickel peaks are there. So all confirm that is a ternary composite only formed in this case. TGA always for stability. Stability we can see only 35% will be lost compared to normal temperature. So maybe compound will be stability is good for long applications. So we confirm by TGA analysis actually. So we taken this same image, pure boron nitrate form sheet like morphology like this, okay, and boron nitrate A and B are boron nitrate nanosheets, and C and D are boron nitrate nickel oxide. When you put boron nickel oxide form like this, pore, you can see pore surface actually, and when you put RGO boron nitrate nickel, we form a marigold flower like morphology. So this E to EF, and this one will be, you can see it will be E and F will be RGO nickel oxide, and this one will be RGO boron nitrate nickel oxide, which shape will be A-time. So that confirms compound forms will be a ternary composite with a marigold flower like morphology. So the same morphology, same morphology noticed in TEM actually. So that is the advantage of your RGO boron. The sheet morphology, you open it, you enhance the structure shape, you can sheet morphology is seen here. So we confirm this compound is highly crystalline, okay, and SID pattern now matches here, and we can see boron nitrate, etc. We notice in Redox pattern actually. So just CV, you can see a CV is very interesting, a very high broad window. So you get a very high broad window for your ternary composite RGO boron nitrate nickel oxide. So that's a very advantage for supercapacitor applications. So compared to your boron nitride, boron nickel oxide, argon nickel oxide, this shows a very broad window with high current density. Therefore, this compound is good for supercapacitor applications. So we do different studies, cyclical material, different. We choose here KOH. We find KOH is better here, not sodium sulfate. The KOH we find this compound shows different value. We calculate the SK for the compound. For 0.5 molar KOH, SK will be 25. 0.1 molar KOH is 11.63. 6 molar will be 6.6. So we find this 0.5 molar KOH is far better for our studies. We choose 0.4 molar KOH is a solvent good for our 6.6 molar. We use 0.5 molar KOH is good for our applications. We change the solvent concentration actually. Okay. So down charge studies we find the compound shows a very broad window and also lifetime cyclic stage will be better for this one, and it shows 94 Faraday per gram in 6 molar KOH in 0.5 milliamp per centimeter square. Okay, so we calculate this one different potentials 0.5 molar KOH, 6 molar KOH. So 0.5 molar KOH shows the 349 Faraday per gram. So 0.5 molar KOH is better compared to 6 molar KOH. I told that, so you know what we choose, we always vary this one actually. Among these, which is better, 0.5 molar KOH is better here compared to 6 molar KOH in this case. So we get 349 Faraday per gram using thermostatic charge discharge studies. So when we do a Ragon plot, we found that high charge density and power density for this 0.5 molar KOH. So we think that the 0.5 molar KOH shows a high power density and charge density. Therefore, we choose our system will be 0.5 molar KOH actually. Stability of the compound. So we can see your charge transfer resistance and specific resistance will be resistance can calculate here, and we find this compound will be shunt resistance will be 0.73 and charge resistance will be 13.39 for your 0.5 molar KOH, which is far better compared to other systems actually. So we come to conclude here. Actually. Okay, come to conclude here actually. So which is far better? Which is far better for system? So RGO boron nickel is a ternary composite consisting of sheet morphology with petal shape and marigold flower will be far better in 0.5 molar KOH, which gives a 314 Faraday per gram. Okay, in 0.5 molar KOH, that is a far better value compared to the normal boron nitride or by RGO, etc., or RGO nickel oxide, etc. Therefore, we confirm the system will be much better compared to other systems. So we published this one, sustainable fuel cells. So you always ask why we choose like this material. This is all latest material, but still we choose. If you want to do supercapacitor, we can choose a very low cost material like polyaniline. So just we compared among three compound system, which is far better. That is RGO boron nitride, unzimmable TiO2 or unzimmable tin oxide. So we find TiO2 is far better because cheap cost wise, etc. It's cheaper. We find this is better compared to our other system. So we can just go on. We can also put the data composite data of the three systems. We find TiO2 system is far better compared to the other two systems actually. So we already, Dr. Satish and Dr. Perumal, they show a lot of applications. So this is we are not doing any application in laboratory. We just initiated. So wearable electronics and transportations are possible using supercapacitors. Okay. So the very important side will be you can for industrial applications. For example, if you want to charge your battery smartphone, you need approximately 1 watt power actually. So your supercapacitor gives 1 watt power actually possible. Even if you want to charge your very low voltage, for example, batteries, watches actually, it needs a 1 microwatt. You can do. So that's the advantage of your same supercapacitor can be used for different purposes. You can start from a low system to high power system you can make using your supercapacitors. Okay. So for example, this high cost material we have prepared here is also advantage, but we can choose very low cost material like polyaniline. I can just say this also we are doing in the laboratory. We can choose polyaniline by simple method. We prepared polyaniline compound, and polyaniline compound we coupled with this we coupled with nickel chloride, and we prepare because this is also a membrane, okay, polymer. So we just prepare a polyaniline nickel oxide coupled to get a hybrid capacitor, and we find. I just want to show data. it forms a tubular structure. Tubular structure forms. These tubular structures are good for XRD. Okay, this I just skip actually IR. Okay. So we can see the compound shows we do 300 system. We do 300 system here actually. Generally 200 system possible. Some people do. Some people do 300 system. When you do polyaniline, we can see your oxygen peaks are there because the polyaniline converted into amaniline to recombinant base. That's why some students will ask in the previous slide, so which is better, whether we do 3 electrode, 2 electrode. It depends on the case of the person case. So if we do 3 electrode system, it is formed to amaniline recombinant base. Here you can see peaks are there. In the case of the carbon nanotubes, no such things. That's a difference. When you use polyaniline nickel oxide, you get a polyaniline can turn to one form or another form. As in the carbon nanosystems, no such things are possible. So we did here 3 electrode system to capture this peaks, oxygen peaks actually. So generally in the 2 electrode system, we cannot see such peaks actually, okay? So that's the advantage of 3 electrode, 2 electrode, most basically actually. So you can see here, this is the standard increases you are increasing actually. So charge is like how we calculated. Formula will be here for specific capacitance CS equal to I delta T by M in delta V. So this formula we can use to calculate your specific capacitance formula, because some of our students may ask which formula we can use. This is the formula we use for calculating your specific capacitance. Okay. So even to calculate your area, use same formula for area 2 electrode, 3 electrode, because working electrode is 1 square centimeter. So you not place much active in your system actually. Okay. So effort of current density we calculated and we find which nickel chloride, nickel chloride. Okay. How we can find this charge is a curve from the plot, and we find the cancer. We give different potentials. The specific capacitance, we can say retention of percentage retention can be calculated with formula specific capacitance divided by maximum specific capacitance to 100. This gives you what is the capacitance retention. Generally, this is the use for compound stability. Everything can be calculated. Okay, and we just compare this with the nickel chloride polyaniline with other method, and we find the nickel chloride polyaniline will be far better for our system. 411. You can see still it is carbon nanotube more. Okay, carbon nanotube more, zinc, copper chloride more. Actually, we always ask. So you always show high values. See here I'm showing a low value compared to the other one. So 411 part background, but still it is far better compared to the other researchers who are published. So we get a 411 part per gram, and we found this is much better than a pristine polyaniline. So nickel chloride dope polyaniline far better compared to pure polyaniline actually. So I come to conclusion. We have thanked the funding organizations like DST, CSCR, Ministry of Environment, Forest, and Spark, and my students, 21 PhD students under my guidance already completed. So they are the backbone of this research. So this purpose of publishing high impact journals actually. So I thank my students as well as my collaborators. These images are taken in abroad like Taiwan and Australia. So I thank my collaborators in abroad. They support me in the segmented images actually. I also thank Dr. Peresami to invite me for delivering a lecture about supercapacitors in the Air Institute of Technology. Thank you one and all for kind attention for the last 1.5 hours. So if you have any questions, I am happy to answer your questions. Thank you.
Good afternoon, sir.
Yes.
Sir, in slide number 21, sir,
21.
I just seen that preparation of combination of the reference electrode and the counter.
Yeah.
Counter, sir. Sir, how to prepare this counter and reference electrode?
So counter electrode is you can use your platinum as counter electrode actually. Okay.
Yes, sir.
You can readily use your counter electrode actually.
Platinum electrode. Yes, sir.
Platinum electrode. You use platinum electrode. Okay. And your working electrode only you prepared. We are using reference will be counter will be platinum only. Okay.
Okay, sir.
Yeah.
Thank you, sir.
Yeah. We put nickel foam here. We put, that's why nickel foam also we can use sometimes for cheaper purpose.
Yes,
Mostly
sir.
we are using platinum. Mostly we are using platinum.
Platinum.
So here in this system we use nickel foam, uncoated nickel foam. Okay, that will be used as a material. Any questions? Why specifically tin chloride and TaO2, TaCl2, TaCl4? So that's a Lewis catalyst. So you know you studied your Lewis catalyst is a carbon-carbon bond is broken by Lewis catalyst. Okay, remove one electron from carbon bond is a form of 2 electrons. When you put a Lewis catalyst, you can take a half electron one side, half electron. So that's called pyrolysis. Okay, break the carbon-carbon bond. To break the carbon-carbon bond, we need a Lewis catalyst. So basic Lewis catalyst will be, we check into a literature, tin oxide. Tin chloride is Lewis catalyst. We put Lewis catalyst. The question is, we ask, say you put Lewis catalyst is the one after it retain or it will be removed actually. So we also think that tin chloride is when you do this one, it will be removed actually. But we see the compound tin oxide is formed actually. That means the tin chloride doing sonication, undergo oxidase to tin oxide. That's why we get tin oxide formed. So to confirm tin oxide form, we take titanium chloride and it formed TaO2. Yes, we checked. That is TaO2 form. So that's the reason we give a confirmation tin chloride and titanium chloride, and we form TaO2 is formed in the final state. Yes, SNO2 form. We confirm that. That's our comparison of work actually. Lower specific capacitance compared to 300 system. Okay. So this may be time to time because in the case of your 300 system, we don't use nickel foam. Very important here. We use glassy carbon electrode because when they do polyaniline, the polymer, we cannot do the coating on nickel foam. We tried actually, we failed sometimes. So we use glassy carbon electrode for making the 300 system actually. That's why supercapacitors, people use different electrodes. Some people use stainless steel. We also use stainless steel. We use nickel foam. We used glassy carbon. When we compare the three, we find nickel foam is far better because of the resistance of nickel, okay, compared to stainless steel and glassy carbon. So we use nickel foil for our purpose. Okay. Like Lewis catalyst, Archana's raised question also I answered. Can you explain formula for 2 electrode? Okay. The formula for 2 electrode, 3 electrode, because I saw last seminar also you asked actually. So current density, you use a formula. Current density J equal to current milliamps by active area. That's the formula you have to use. To calculate the current density J, either 2 electrode, same formula only there actually because the active area is same. You use current by active area. Current by active area gives you current density. That's the formula you can use for your calculation of your current density. Okay. Formula is current density J equal to current by active area. Current by active area gives your current density calculations. Any questions more?
Sir, good afternoon, sir.
Yeah.
Sir, nice presentation, sir.
Thank you.
Sir, I have one doubt, sir.
Yes.
Sir, how will you change amorphous to crystalline medium while using activated carbon, sir?
To make amorphous carbon to carbon, that's why carbon is always amorphous. When you add the metal compounds like tin oxide or TaO2, automatically your state amorphous to your crystallinity form increase actually. That's the reason when you use tin oxide, you find your carbon will become into a crystalline form, approximately due to tin present in the compound. Okay, tin and 89% of the compound.
So only metal is doped and then to convert from amorphous to crystalline, or otherwise any other organic solvents or any other materials we have to dope.
Carbon is amorphous. Carbon is amorphous. If you take layman, you say carbon is amorphous. Okay, no one came carbon to crystalline form. Or you can prepare quantum dots. If you want to prepare carbon to quantum dots, you can get crystalline form.
Okay, sir.
That's the only way you can convert carbon to quantum dots. Then you can get your crystallinity increase because of band gap tuning. Okay.
Yes, sir. Thank you, sir.
Yeah. Yeah. Thank you. Thank you for all the participants.
Sir, good afternoon, sir. Am I audible, sir? Yes, sir.
Good noon to all. I'm very happy to invite our resource person for this session, Dr. Shakti Pandi, sir, has made enormous and innovative contributions to materials characterization using online ultrasonic techniques and the conventional techniques. And he has received many laurels and awards from national scientific societies. And he was co-authored in 3 research books. And he also attended more than 120 national and international conferences, both India and abroad. And in order to equate with the research, he is going to lot of collaborative research work with the many leading research laboratories in India. And under his guidance, 2 research scholars have completed the doctoral degrees and 4 scholars are pursuing their PhD degrees. And he is a member of Board of Studies in Doctoral Committee in Anna University, Bada University, and Manoன்மணியம் Sundaram University. And presently he is working in the area of magnetic oxide for different applications, nanofarads from electromagnetic shielding, nano perovskite for energy storage applications, and developing nanoparticles from herbal plants for biomedical applications. And SOR also given many ideas. They are given a research and for me and many research fellows. With this brief introduction, I would like to invite Dr. Shakti Pandi to enrich our participants on recent advances in perovskite oxides for supercapacitors. Sir, please take this forum to for this session. Thank you, sir.
Thank you, ma'am. First of all, I'm thankful to God Almighty for this opportunity to interact with the research scholars. I'm also thankful to the NEER Institute of Engineering and Technology and the principal and chairman for hosting this conference. I'm also thankful to the organizer, especially the Chodi madam and Priyasamy sir for giving the opportunity to talk with you. So once again, I congratulate the Priyasamy sir for getting the CSIR grant for this workshop. So with this, actually I'm working on a magnetic material. Sir, PPT is visible now, sir?
Yes, sir. Yes, sir.
Yes, thank you. In this presentation, we mainly concentrate on a little bit about the introduction and what are the modern materials like a perovskite and ferrites, how are they different, and how these materials will be useful for the battery application and the supercapacitor, and a small conclusions from the studies. So, in day-to-day life, the material science plays a vital role in improving the economical performance. Actually, in the morning introduction section, the principles are mentioned that today we are need of a supercapacitor. Even though the China has built a very large capacitor to store the energy, now the India is also looking for the energy storage systems. So the material science will give the right choice for the right problems. So the more energy convenient devices and recyclable less toxic materials are needed. And also we are concentrating on health, communication and consumer product. So many ideas we are generated through the material science. So once upon a time we are used stone as a material. Again we are go for a copper. Likewise now it is plastic we are using. In future we are using the biodegradable green plastic, so it can be degradable within a day. The newspaper can be degraded within a day, so you can't store the newspaper for a long time. Like that, the biodegradable materials will comes into the play in future. So these are some of the key material to change the world: the gold, zinc, copper, ferrous, silver, aluminium, magnesium and silica. So these are the trends in nanotechnology nowadays. First, we will see about the perovskite magnetic materials. Perovskite is one of the magnetic material. It is found in 1839. So the general formula for the perovskite is AbO3. A and B are the different cations, either the different in charges and different in sizes. So the natural material found in the perovskite, the first is CaTiO3. Here A is a Ca, B is a Ti, O3 is the formula common. So this is the natural mineral available perovskite. In this perovskite, the people are converted this perovskite into mixed valence perovskite. Instead of the same charge, they will put another charge. So mixed charge they will use. So mixed valent. And these materials are generally the multiferrite material, as well as it can be used as a photocatalytic materials. So this is the mixed valent perovskite. La1 X AXMnO3 is the best example for the mixed valent perovskite. La is a lanthanide material. It is a trivalent material. Mn is also a trivalent. So this is 3 plus. Mn is also 3 plus. O2 is a 2 minus. 2 minus into 3 will be 6 minus. So La is 3 plus. Mn is 3 plus. O3 into 2 minus will be 6 minus. So totally the charge neutral will be there. Where the A is a divalent element. Instead of La, we are putting A. A is a divalent element. So it is 2 plus. Mn will take the 4 plus, and this will be the 6 minus. O will be the 6 minus. So this is 6 minus, this is 2 plus. So Mn will take the 4 plus charges. So wherever the La will be there, Mn will take the role Mn 3 plus. If you dope with the A divalent, Mn will take the role of Mn 4 plus. So in the same system, Mn 3 is also there, Mn 4 will be also there. So Mn 3 plus and 4 plus, 4 will be there. So both will be existing in the material. So that this material is called as a mixed valent perovskite magnetic material. In general, LaMnO3 is a mode type insulator. If you put a small amount of doping by the divalent, it will goes to the complex phase diagram. This is called a mixed valent magnetites because it consists of both Mn 3 plus and 4 plus. By doping of A, it goes to the complex phase structure. The magnetic properties are a little bit changes. Not little bit, it largely changes because of the interplay between the lattice, spin and orbital and strain. There is one interaction describe this kind of the magnetic properties. That interaction is called as a double exchange interaction. Double exchange interaction is nothing but the interaction between the Mn 3 plus and 4 plus. Wherever the Mn 3 plus exists, after some time they will change the places. So that kind of interaction will be taken as Mn 3 plus and 4 plus interaction. That plays a key role to determine the magnetic property of the perovskite magnetic materials. Another one, the interesting property of the magnetic material is CMR, cholesterol magnetoresistance. It's one of the special property of the perovskite magnetic. Whenever you are applying the magnetic field, that resistance will be changes. Another one theory will be there, double exchange theory. That is the double exchange theory. I already explained. Another one is John Teller discussion. So whenever the ionic radius will be changes due to the charge, when Mn 3 plus goes to Mn 3 plus, so the bond length will changes. Whenever the bond length will changes, the structure will discussion. So that kind of discussion is also a main play role. That is called as a John Teller discussion. Another one is charge ordering will be also happening. Orbital ordering will be there. CMR also I explained. Even though the material has a different role when you convert it into nanostructure material, the bulk perovskite magnetic material property has been changed, appropriately changed into the nanoscale. Another one is the spinel ferrite. Is also another magnetic material used in nowadays. Here the general formula is M Fe2O4. Instead of O3, it is O4. Instead of B, they will put Fe2. So that is a general formula. Generally, it is a cubical structure. It is a family of the ferrites. Phenyl ferrite is also a family of ferrite. This kind of materials will be used in electronics, bioprocessing, magnetic resonance images. So the ferrite has a lot of applications. In general, the various ferrites are there. The barium phenyl ferrites have the extensive potential application in the variety of fields, including the microwave and switching devices. So here, the important thing to determine the property of the ferrites is the unit cell and its interaction. The A site will be surrounded by the tetrahedral site, and B site of the atom will be surrounded by some octahedral atoms. So whenever you change this arrangement, or if you disturb the arrangement of the tetrahedral cell and octahedral site, you will get the interesting property. So the magnetic property of the spinel ferrite is always depends on the magnetic property of the tetrahedral site minus the magnetic property of the octahedral site. If you put a more magnetic amount in the octahedral site, means the magnetic property of the net ferrites will be decreased. Whenever if you increase the magnetic atoms in tetrahedral site, means it will increase the magnetic properties. So the octahedral will decrease, the tetrahedral site will increase the magnetic property of the materials. So what we did is we include the rare earth. So here the magnetic properties are only determined by the Fe-Fe interaction will plays the main role in ferrites. That called a spin coupling effect or 3D interaction that plays the important effect to the magnetic property of the material. If you put a small amount of rare earth, the interaction plays, the main interaction is the rare earth and Fe interaction plays the main role rather than Fe-Fe interactions. So there is appropriate change in the electrical and magnetic properties will be there. Another alloy is a Hessler alloy. That is also very important in nowadays. The general formula is A2BC. This is a full Hessler alloy formula. ABC is the half Hessler alloy formula. So the stack will be like this: A, B, and then A, C, A, B, and then AC. Like that, it will be arranged. So the interesting thing of the Hessler alloy is it consists of non-magnetic element. However, it has the very high magnetic property when compared to other materials. So this is the positions of the atoms. 8C, 4B will be in the center, and 4A is the positions. Here in general, A and B are the transition elements. C will be the non-magnetic element or the semiconductor. These alloys have the structure of L2-1 structure usually. So this is the phase diagram. Why the magnetic materials for the superconductors? Why we have to use the magnetic material means that magnetic material is flexible with the ionic substitution. So if you see this first diagram, this is the doping concentration, 0 to 0.5 they are studied. Here 0.12, here also 0 to 0.8, here 0 to 0.5. So it is a lanthanum, strontium, MnO3 ferroscite. If you change the concentration beyond 1.5, it will be changes to ferromagnetic structure. Earlier it was a paramagnetic insulator. After some time, if you increase the temperature, so earlier it will be standard insulator. Again it goes to ferromagnetic insulator. If you increase the concentration, again if you increase the concentration, it will be goes to paramagnetic structure. If you increase the concentration, it will goes to antiferromagnetic nature. So see here, this is the different concentration. If you the same concentration, you can get the both phase, antiferromagnetic phase as well as the ferromagnetic phase. That can be obtained by different synthesis method or different grain size like that. Whenever you can increase the temperature here, it will goes to standard insulator to paramagnetic insulator. Here ferromagnetic insulator to paramagnetic insulator. Here it is ferromagnetic to paramagnetic. Here it is AFM to PM structure will be there. So here it is almost the high temperature, it is PA, whereas the low temperature is as the various magnetic phases. Here also the sodium 1 - X, calcium X, MnO3 also the different phases. So this is the advantage of the ferroscrite magnetic materials. So the simplicity of the other crystallographic structure, it is the easiest crystallographic structure. you can increase or decrease the property by choosing the A site and B site. You can change the property, you can play with the property of the magnetic materials. Another one reason is the antiferromagnetic material has the double hysteresis loop when compared to the other material. Usually the magnetic materials, you know, the hysteresis loop. Some of the antiferromagnetic materials like a prisodium doped, they have the double hysteresis loop. See here, here also one hysteresis loop will be there. Here also one hysteresis loop will be there. So the spin arrangements will be changed from here to here. Generally, during my introduction, I have mentioned the ferrites are having the cubical structure, spinel ferrites, whereas the ferroscate has some tetrahedral. But the small change is the arrangement. Here it is tetrahedral arrangement, whether it is here it is a cubical arrangement. So this is a difference in the ferroelectricity in the ferrites. Whenever you change the center of the atoms, you can change the structure. So this can be obtained by the diffusion or the quenching method. You can obtain the structure. So usually there is one example will be there. The peoples are running in 100 meters. They can't go for a 1200 meters or marathon. So the players are different. Like that, the materials for a ferroscate will be different for the battery, electrochemical and conventional. So this is the common chart. So whenever the energy density is higher, it will be used for the batteries. The energy density is medium in the order of 10 power 0. It will be used for electrochemical capacitor. More of this thing it will be used as a conventional capacitors. So this is the hysteresis loop for the 4 different linear dielectric, ferrodielectric, and relaxator ferroelectric and antiferroelectric. So the green colors generally represent the recovery of the energy density. So this is the energy density here, this energy density, this energy density, and the red color shows the loss, energy loss. So if you compare to ferroelectric to antiferroelectric, what is the advantage means? Here the energy loss will be minimized when compared to here to here. So it will be cut down here. It is a double hysteresis loss. So it will, the energy loss will be reduced. So there is an advantage if you go for a antiferroelectric. So that is an advantage of this materials. So the applications are different. For example, some of the materials are used for infrared detectors, and some ferroscate magnetic materials are used as a electromechanical transducer. Something is used for multi-layer in capacitor, and something is a ferroelectric components and battery. Like that, so many applications will be there for the same materials. So what is the effect of doping element in the magnetic property, in the electrical and magnetic properties? So this is of the two of my papers are published in Journal of Electronic Material as well as the Ceramic International. So this is the, we have synthesized three magnetic ferrites. First one is a base CuFe2O4. Another one is, here I replaced Cu by Mn, half 50% of Cu will be replaced by 50% of M. Here I am replaced by Fe by lanthanum. So introducing the rare earth element. So interestingly, the band gap of increased. Here it will be, the base element is 1.66. For the copper doped it will be a 2.1. For the rare earth doped, the same material will be 5.33 electron volt. In general, the band gap is literally connected with the dielectrical property. Whenever we can increase the band gap, we can get the dielectric constant more. And the next way, the magnetic properties. The magnetic properties of the copper ferrite is very less when compared to copper. But in between the lanthanum, we have optimized Here the magnetic property is little bit lowered, as well as the dielectric constant is also increased. So this is another paper. Here I put Le as a function of composition. Le as a function. So x may be, this is the value of x. Here we have identified the band gap as a function of x. The band gap for the 0 will be 4.8, it will be 4.61 or 2.5%. So this is dielectric loss and dielectric constant. Dielectric constant is not there, but the dielectric loss will be decreased. So this is a magnetic property. Magnetic properties is also decreased. When the composition increases, the magnetic property will be decreases. So this graph shows the reflection loss over a wide range of frequency that will be measured from the X band. Around 8 Hz to 12, 15 Hz we have measured. In this, we found the sharp peak around 15.2, almost the end of the X band. It shows some absorption. So these materials are very much useful to observe the X band radiation. Almost here also we have get some of the peaks, but the reflection loss is also related with the thickness of the material. Here we are put only 3 mm. However, the 10 TB is a standard. So almost these two materials and the higher concentration have the more dielectric absorption, microwave absorption. So this is a summary of this element. The band gap was increased, and the dielectric constant here it is 50. It will be converted into 101 by doping of a small amount of the lanthanide with this material. If you put a small amount of lanthanum here, it is 1.9. It is X is equal to 1. So La will be 0.1. Fe is 1.9 in this composition of the ferrite. Whereas we can get the increase in dielectric constant. We are all know the capacitance is always directly proportional to the dielectric constant. Once if you increase the dielectric constant, the capacitance may be increased. For example, if you put this material, the capacitance is 50. The same material we can be put, you can increase the capacitance by 50%. So it is 2 times we can increase the capacitance. Also, the loss tangent is also decreased from 2 to 0.5. And the magnetic property is always lowered from 60 to 41. Why the magnetic property is decreased means this is the reason. So generally the electromagnetic shielding properties is always described by the classical equation Se in dP is equal to 10 times of log sigma AC divided by 16 omega epsilon naught mu double dash plus 20D divided by del into log E. Here sigma AC is nothing but AC conductivity, and mu double dash we already know. Mu double dash is equal to ms by 2 HA by alpha. Sigma AC is given by this equation. Here it is wrongly put, the mu dash. Okay, sigma AC is given by omega epsilon dash epsilon double dash. Whenever you increase the dielectric constant epsilon, sigma AC will increase. Whenever the sigma AC will increase, the shielding property will also increase. So it is directly proportional. So sigma AC will increase when the dielectric constant is increased. So once the sigma AC will increase, SA will also increase. In a reverse way, the shielding property is inversely proportional to the magnetical constant, mu double dash. Mu double dash is directly proportional to ms. Whenever you can increase the saturation, that mu double dash will increases. Once the mu double dash will increases, sigma dash will be decreases. Where in the reverse way, if you decrease the magnetic saturation, mu double dash will be decreases. Automatically, the shielding property will be increases. So the idea is we have to increase the dielectric constant. At the same time, we have to decrease the magnetic property. So if you want to prepare ferrites for electromagnetic shielding as well as the perfect dielectric materials for a battery, we have to concentrate the two parameters. One is we have to increase the dielectric constant. At the same time, we have to decrease the magnetic property of the material. So this can be obtained by PVA. We put some PVA in this ferrite material. In XRD, we didn't find any change. The dielectric band gap is also measured, but little bit change in the band gap will be there. This is the dielectric constant. Here around the scale will be around 1400. With the PVA, the dielectric constant goes up to 1800 scale. So it graph roughly shows that the dielectric constant has increased. As similar to the magnetic property, it goes to around 100, whereas it goes little below than the 100, it is around 80 or something like that. So the magnetic property is decreased. So this is the sigma and sigma double dash without polymer. Without polymer is 1300. With the polymer it goes to 1600. Here it is 639. It is around 648. And also the magnetic property is without polymer is 94. With the polymer will be 84. Generally the polymers will be used to reduce the magnetical property of the materials. So what happened with the PVA? PVA is a non-toxic polymer soluble. So it has some hydroxyl group of PVA. The hydroxyl group of polymer is attached to the lanthanide that forms some weak static interaction of the van der Waals force. This weak interaction only the responsible for the decrease in the magnetic properties as well as the increase in dielectric constant. So same way, instead of neodymium, we put a lanthanum here. This paper is also published in two journals. One is Material Chemistry and Physics, another one is Ceramic International. Here also, the dielectric constant is increased from 329 to 895. Here it is 1500, it is around 1800. So the dielectric constant has increased. So in general, the real part of the permeability is characterized as the storage permeability of the electrical energy. In the previous slide, I showed some of the green color image. The dielectric constant favor to restrict the impedance matching at the interface between the air and surface of the nanoferrite. Thus, is control the electromagnetic behavior at the interface. So the higher dielectric constant is a desirable property of the capacitors. So this is not our work. This is taken by some other article. Here, the reflection loss, the microwave property they have studied from the very long range, from the 2 gigahertz to 18 gigahertz. Even though without the graphene, they didn't found any kind of the proper absorption, the single absorption. By doping of graphene, they found the specific absorption in this case. So Fe composite, the nano composite can be doped with the graphene is also we have this physical absorption. Here 10 dB is a reference. So all the samples have the physical absorption below the 10 dB. That is from the very good absorption up to 40 dB is also there. So in the literature, the people are doing so many kind of possibilities. The people will take as a ferrite mixer with the reduced graphene and they are studied. Ferrite with ZNO. And another paper you can see ferrite ZNO plus copper and ferrites plus CNT, ferrites plus Pani plus reduced graphene. Like that, the so many applications will be there. Ferrite plus multi-wall carbon nanotubes, ferrite plus Al2O3, ferrite plus silicon carbonate, FR composite, MnO2, polymers. So the people are studied the various combinations for kind of to increase the dielectric constant of the material. Just you can refer this paper, Journal of Mechatronics, volume number 5 and issue 4. The page is 503 to 541. It is a review paper. you can get the more idea how the high dielectric constant material has been prepared, how it will be behaving. So this is the work we have done the long back, not now, I think in around 2014. So this kind of setup we have studied from a paper. It is around 5 parts. So it is made up of a stainless steel. So the similar setup we have tried in our lab. So this is our own setup. So using this we have studied some charge discharge studies. So the procedure is the working electrode consists of active material TiO2. Just a minute. And conducting agent, the carbon block or polymer blended. This will be the ratio will be taken and mixed in a foil, fry in a volume oven. This is and pure lithium metal as the counter. But this is the procedure given in this paper. But we have used a different one. Here we are used anode as a Zn metal. And the electrolyte is this. And cathode will be the graphite and MnO2 and activated carbon. And the separator as we are used to the graph paper is used as a separator. This way they are connected. This is the graph paper. These are the two parts. It will be connected, and then that will be mounted with the polymer. Again, it will be shielded. Oh, this figure. Okay, this should be here, and this should be here. It will be molded with this, and it will be attached like this. So this is the arrangement. So this is we have observed during our studies. We studied this charge discharge studies with the two sample. One is a bulk ferroscrete with the composition of LSMO 37. That means lanthanum, strontium, manganese, O. X is around 37. So La1 minus X, SRX, Mn O3 is the main composition of this material. In this, X takes a value of 37. So the TC is already measured by some other measurement that shows the 367 is the transition temperature. So here we have studied the charge discharging studies. We have observed the two findings. One is the open circuit voltage has been suddenly decreased from 1.1 to 0.79, 0.78 or something like that. The open circuit voltage will be decreased, but the discharging time will be increased. Whenever the bulk sample will be around, it is around 7 hours, it is breakdown. For the nano sample, it goes up to the day. Around 1 day it will be taken. So another work we have did in this hybrid electrochemical behavior of the La1 minus X calcium X MnO3 nanoferroscrete. This work done with the ferroscrete. Here it is, this work is we have a little bit interesting. We have prepared our own the graphene by the battery waste. So you know the everyday battery they will put throughout. From this we have taken as a graphene rod. From this graphene rod we have developed the graphene in this. So water inspired graphene we have prepared from the waste cell, everyday cell. So from this we have developed some battery from this work. So this is the graphene preparation. So we have collected the e-waste from Ekatatangal. That company name I forgot. I think this is there. Arai Engineering Works. So we put some MOA with them. So we collected the sample from them. So they are given around 2 to 3 kgs of samples. So after that we have prepared some carbon rod from this, and we have prepared this carbon rod to graphene. So in addition, we have prepared the 3 ferroscate sample in the same composition. La1 minus X, CaX, M1O3, where X takes the value 0.7. Again, La1 minus X, CaX, M1O3, here X takes the value 80, here it is 90. So instead of X, we will put some values here. La1 minus X, X, M1O3. So the X we put as a 0.7, 0.8, 0.9. So that also we have did. From this we have prepared 3 different samples. This sample shows the orthorhombic PNMM structure. Generally the ferrites will be in cubical structure, ferroscate will be in the orthorhombic or rhombohedral structure only. So the ABC values are given here, and the JCPDS is similar to this JCPDS file. The increase in divalent ion concentration has been retrieved from the peaks are shifted to higher theta values when compared to the reference. When the doping concentration increases, it will be shifted to higher values little bit. So from this we can conclude that the grain size is decreased by increasing the full width of maximum, as well as we have confirmed that the increase in dielectric concentration ion shifted to higher level of 2 theta values. So this is the roughness we have measured. The AFM image of the electrode. This is the AFM image of the MG electrode. It shows 2614 nanometer. The variation roughness is 2614 nanometer, but it will be coated with the lanthanide ferrites. Here it will be the roughness will be decreased around 326, 297 and 258 for the A1, A2, A3. That means 70, 80, 90 composition. So the slight variation in the surface can be obtained by the doping of a ferroscate. And this EDX figure shows the ferroscate. So the ferroscate samples are in the spherical like nature, and this intensity figure shows that all the compositions prepared will be in the more or less on the same ratio of we prepared. Here it is A1, A2, A3 will be the composition 70, 80 and 90. So it shows the calcium peak will be little increased when compared to the other samples. Oh, sorry. So the surface area by the doping for the coating of ferrites on a MG electrode, it will increase the surface area. So the surface area is 175 for the A3 sample. So the higher surface area can be obtained by doping of for coating of ferroscate with the MG electrodes. So this confirms the presence of graphite and graphene. So the XRD pattern will be taken for the graphite prepared from the the waste battery materials. And the JCPDS file, then the Raman studies confirmed the presence of graphene in these samples. So usually the Raman studies will use to confirm the graphite. So that will be also we have taken for a graphene and graphite. So you can find out the difference of these 2 samples and the appearance. So this is the EDX pattern of the graphene coated ferroscate. Now the graphene will be mixed with the ferroscate. So it shows the values of calcium, MnO and everything in this order. The corrosion potential will changes when with the different KOH they are measured, but the values will be decreased, I think so. Yes. Again, the semi-image has been taken. The non-uniform corrosion studies in both both KOH and IG KOH they are measured. Even though that ferroscrete coated electrode will possess the minor crack when compared to the other one. So this conveys the major electrode has been remain undamaged, and it has a promising correction incubation. Also, it has been retrieved from the same image. Another one, we have measured the open circuit voltage. The open circuit voltage for around 1.48, and the solution resistance and transfer ratio is also measured. That is around 55 to 55. Here it is 68. So the ferroscrete layer will protect the electrode surface, thereby limiting the flexibility in discharging. Thereby the resistance offered by the charges during the electrode and electrolyte interaction was improved. So this is the charge voltage behavior around it is 6 kVh. It will be noted. So you can change. You can see this behavior. The A3 will have the better performance when compared to this one. Without electrode additive, this is the graphene additive. So graphene plus electrode will have the good amount of the discharging time. And short circuit studies also they have performed, and also they have mentioned the lower self corrosion from the study. So here they are measured the time versus the current for the corrosion one. The flat is used to measure the self corrosion rate and the breakdown of the anode. This is and absorption test is also performed, and this is the summary of the study. Before coating and after coating, what is the difference in the weight loss also they measured. So the A3 sample around 90 for a small amount of lanthanide and most amount of calcium as the optimal electrode for the high temperature stability is around for this sample we have measured transition temperature is around 800 degree. So these are the key finding of the study. From the study, we found that the best out from the waste. Every day the battery we are throw it away, every day cell. From that we have prepared the graphene. From this we have developed our own battery setup. From this, the anti-corrosive property of the ferrite magnetic material will increase whenever the ferroscrete magnetic will be joined with the graphene waste or the electrodes. It will increase the property. Whenever the electrode, if you add the ferrites with this electrode, it will increase. Like that, if you put a more combination, either graphene or multi-wall normal carbon or PANI or MnO2, any kind of combination will increase the further. So like that, we have put the ferroscrete LCMO with the graphene in the study. So in this conclusion, why the magnetic property has been interesting means we can change the A side and B side doping. Easily you can control the A side, B side doping. From this you can control the magnetic property of the materials. Both you can do. Even some of the time and the non-symmetric, non-stoichiometric has been done. Whenever if you cut down the oxygen in the sample, it will be the deficient will be oxygen will be there. So the people will return us AbO3 minus 3 minus 10. Instead of 3, they will put a deficient. Or if you exposure in an oxygen environment, they will put a plus 10. So you can find out some non-stoichiometric, and you can make some composition like a ferroscrete with Pani or the graphene or anything you can do nowadays. Another one is double perovskite. Nowadays, the double perovskite plays a major role because the perovskite moves. So many people are working in a perovskite. In a long time, the people are working in a perovskite. Now, the people go for a double perovskite. Instead of one structure, they are put a two structure. For example, La SR MnO3, that is one. In this LR, I put a CD also. So La GD is another rare earth, and same way SR MnO3. They will put instead of La MnO3, GD MnO3, they are mixed into two La GD MnO3 like that. Or La instead of divalent, they will put a two divalent. And this the metal halide is another material. I mentioned in the previous slide, the general formula is AbO3. Instead of O3, someone will put X3. AB, X3. A and B are the two different material. Here X is the halide materials. I, chlorine, iodine, like kind of a gas that will be used. Halides will be used. So that is called as the metal halides. So they are also having the interesting property. Whereas the perovskite based solar cell has the efficiency of 25, but the metal halide doped perovskite will be around 38 nowadays. 38 or 41 references are there. So now it is efficiency is 41% for the metal halide. Another, all kind of magnetic materials, we can put it as a self-healing materials. Shape mineralize, that can be used as an electrode. As well as the photo detection and water splitting has been happened in a ferrite material easily. So we know the supercapacitor and the hybrid capsules. So many, these all three are the comes under the supercapacitors. But all the things depends upon the desired physicochemical properties. So the perovskite gives the option to change your physicochemical properties by changing the element or the synthesis method or the external pressure or temperature. Like that, you can change the property of the material easily. So the desired physical property will give the open material for the right choice. The thermal stability of the perovskite material is high when compared to easiest method. I already mentioned that the synthesis method is very easy and you can adapt the various synthesis method for various kind of structure. For example, you can produce the LSMO material, that means the lanthanum strontium MnO3 material. By the hydrothermal method will have the different structure when compared to the normal sol-gel method or the solid state reaction method. These elements are used as the oxygen storage. The water splitting can be done here, and it is a low cost material. Improved electrical conductivity has been obtained easily. Thank you. Any questions?
Yes, please.
Hello, good afternoon, sir.
Good afternoon, sir.
Hello.
Good afternoon.
So, shall we use this kind of a perovskite material in the hybrid supercapacitor application? Is it possible?
Yes, sir. The metal halides they are using. People are using a metal halide perovskite.
Oh, okay, sir. Normally in the ABO3 structure, I have on paper in samarium cobalt oxide. Shall we use samarium nickel and this kind of a based materials? Whether it give good results or not?
Yes, sir. You can try it, but in this case, you can add some of the graphene or the polymer to enhance your activities. But we
Okay,
did
sir.
the same work, as you said. I did the same work. Without graphene, I get some other result. With graphene only, I can little bit of the current density is increased.
Okay, sir. Thank you, sir.
Exactly. You can dope any kind of carbon into perovskite, such as yes, it is possible. You can make some composite by using this any kind of carbon. Like even some of the people are doping with the MnO2 again. They will take a perovskite and they will put some of the MnO2 again, and they will make us a composite. And carbon nanotubes, Pani, so many are there. You can see the literature, so many. Yes, madam. That is depends upon the specific application, I think so. Find those, we have to search for each and every one. The ferroids, we didn't use any finders, I think so. We used a graphene as a binder, I think so. No, in this paper we didn't use any finders, I think so. What is that I already answered. We can possible with the any kind of carbon like polymer, Pani, or multi-wall carbon nanotubes. Anything you can put it as the perovskite, and you can enhance a little bit the property. So the polymer has some hydroxyl group. That group will be attached whenever with the perovskite or the ferrites. It forms some weak van der Waals forces. These weak van der Waals forces are the responsible for the increase in the dielectric constant and the band gap. What is the normal band gap of the perovskite of AbO3? Normal band gap is around 2 to 5, but it depends upon the again the element. If you put a lanthanum, strontium, MnO3 means that band gap is different. Even if you put a strontium, it also for the composition you can vary. For I saw one of the slide, the band gap is I have achieved from 1.62 to 5.3 by doping of two ways. One is I have replaced some of the copper, 50% of the copper by Mn. At the same time, Fe is replaced by 0.1. So in this case, I put a two doping. I increased the band gap from 1.66 to 5.3. 1.66 to 5.3. I can't get your question. It is in a base material, copper ferrite, I think so. So the copper ferrites only I have put some of the Mn atom. It goes around 2.3 or 2.1, Again, I put a lanthanide, it will goes to some other value. Photocapacitor using this. But some papers are there for a photocapacitors. Yes, there is possible for the photocapacitors. The material used in water splitting is mostly, I think it is useful for the photocapacitors. Thank you. Which method is that? Okay. But it is based on your own lab facility. Whether you have working in a small college, you can use the salt gel method or the solid state reaction method. If you have any good furnace, if you working in a well defined laboratory in the national laboratory, you can use any kind of methods. Laser vapor deposition will be there. It is up to your lab facility, madam. For a small scale lab, you can use a solid state reaction or salt gel reaction is best.
Yeah, good afternoon, sir.
Good afternoon, sir. Please, sir.
I have a question. Actually, it is a confusion, not a question. That I am also working on the hydral alloys.
SLR alloy, so super.
Yeah.
Is a thin film
I
or a
have,
metal alloy?
yes, sir. That is the metal powders I am using. I did my synthesis with the ball milling,
Oh,
and
okay.
after ball milling, I did heat treatment and I did some this characterizations.
Okay,
And
sir.
in
What is the
accepting,
temperature, sir? May I know the temperature
yeah,
of melting?
my compound is actually the different elements like Mn2, Ti is there, Sn is there,
Yes,
Cu
sir.
is there.
Okay.
Different compounds are used. Although the literature is only in computational work is there,
Yes, sir.
only it has been computational. There is no experimental evidence on those materials.
No.
So I did temperature up to 1100 degree for one compound, for another compound 900 degree. I annealed in different temperatures. Although in one compound I got phase formation was there, but I could not see any ferromagnetic behavior in
Yes,
the
sir.
compound.
Yes, I
When
understood your problem because in general,
yeah.
the SLR alloys are prepared in a melt arc furnace.
Hello, sir.
Melt arc technique, you know.
No, yeah, there is arc melting also, but I did the ball milling. Some
If
people
you
are
did
also
the ball
using.
milling, then you have to put in quenching around 1600 or 1700. Once it is melted, up to the melting only you can be done. So the composite should be melted first. Then after it should be crusted. Then only
But
you can form the SLR alloy. Then you will get the L2-1 structure.
without
Melting
melting,
it
it's
can't.
not
It
possible.
can't. So best way is you can use the arc melt technique. Arc melt technique is the easiest technique. With the small arc, you can melt the sample and it will be mixed. Then you can put it as a small, the calcination temperature is enough. Then you can use that alloys.
We were having the possibility of ball milling availability in our lab. That's why I used this.
No, sir.
And
Ball
the
milling
metal,
it won't.
yeah, we are having the ball milling. That is the reason I used that synthesis process. Although in ball milling we used the powder sample, but if we will go to the arc melting, that's in need of the grains are in the form of chips. The material should be in the form of small chips or in form of grains.
After forming the melt arc furnace, you will get as a ball your sample. Then you can crush it into small pieces. Again, you grind it. You will get the powder. From that powder, you can take all the measurements.
Okay, sir. Actually, from going to the powder to the arc melting, it becomes from nano to the bulk. We got if we will see in the arc melting, we are
Okay,
doing it.
sir. Sure,
And
I agree that again you can grain it. After forming the balls, you crush it and grain it. you can convert that bulk into nano using your ball mill.
Okay, sir.
Any other questions, ma'am? Yes. Sir, thank you, sir. Thanks for your opportunity to interact with the guys. Thank you, sir. Thank you, sir. Thank you, ma'am.
Chemistries, various type of flow batteries we do, aqueous redox. Hello.
No problem. So you are going to Where is Ami? Can you hear me? After the introduction, you are going to play my video, right?
Yes, sir.
Okay. Then towards the end again, I will join. Yeah, you can start. Thank you, Dr. Peresami. So probably you can play, then I will join as soon as the play is done. Yeah. Aqueous redox, organic redox flow chemistries. So some of them I have taken it from the literature. Some of the examples from our lab is what I'm going to discuss here. And these are the areas in which my group is active on research, like oxygen reduction reaction chemistry, which has its application in fuel cells, zinc ion and zinc air battery, electrochemical sensors, and flow battery chemistries. Various type of flow batteries we do, aqueous organic and non-aqueous organic type flow batteries, and aqueous inorganic type of flow batteries, and so on. Apart from that, we also work on metal ion batteries like lithium sodium ion batteries, and organic photovoltaic excitonic type solar cells like perovskites and dye-sensitized solar cells. So for this particular talk, I will be talking few case studies from the flow batteries in this talk. So before I get into any deep into the subject, I thought I will familiarize students and those who are not an expert in this area about the terminologies which are used in the electrochemical field, especially in energy storage. The first and foremost is the voltage that battery that provides is very important, because voltage is kind of decides the energy density, because the charge that is being transported from anode to cathode with the voltage, okay, charge into voltage, that tells you the energy that is involved in the process of moving the charge. So divided by the mass, you get the energy density, or divided by the volume, you get the volumetric energy density. So how much charge you can move from one electrode to other electrode during this battery discharge or during charging of the battery defines your capacity. So you can see milliampere hour.
No, sir,
That's
we cannot hear the
as a
video.
fundamental unit of coulombs, right? Because
We cannot see
milliampere
the
is
video.
aqueous these are the areas in which and I thank the organizer, Dr. Periyasamy, and other organizing committee members for the invitation, and chairperson of this session for the kind introduction. So today I will be discussing about the aqueous redox, organic redox flow chemistries. So some of them I have taken it from the literature, some of the examples from our lab is what I'm going to discuss here. And these are the areas in which my group is active on research, like oxygen reduction reaction chemistry, which has its application in fuel cells, zinc ion and zinc air battery, electrochemical sensors, and flow battery chemistries, various type of flow batteries we do, aqueous organic and non-aqueous organic type flow batteries, and aqueous inorganic type of flow batteries, and so on. Apart from that, we also work on metal ion batteries like lithium sodium ion batteries, and organic photovoltaic excitonic type solar cells like perovskites and dye-sensitized solar cells. So for this particular talk, I will be talking few case studies from the flow batteries in this talk. So before I get into any deep into the subject, I thought I will familiarize students and those who are not an expert in this area about the terminologies which are used in the electrochemical field, especially in energy storage. The first and foremost is the voltage that battery that provides is very important, because voltage is kind of decides the energy density, because the charge that is being transported from anode to cathode with the voltage, okay, charge into voltage, that tells you the energy that is involved in the process of moving the charge. So divided by the mass, you get the energy density, or divided by the volume, you get the volumetric energy density. So how much charge you can move from one electrode to other electrode during this battery discharge or during charging of the battery defines your capacity. So you can see milliampere hour, that's has a fundamental unit of coulombs, right? Because milliampere is millicoulomb per second. So you multiply a time unit hour. So it should be a sort of that a quantity that defines the amount of charge that is being transported. So divided by the mass, you get the capacity of the battery. These two together decides the energy of your system. And then we also important to look at the ionic mobility of the ion which is moving, shuttling between the anode and cathode in the electrolyte, and also the electronic mobility of your electrodes. These are very important because they decide the rate at which we can, charge or discharge the battery. In other words, C rate of the battery is decided by these properties. So all these four parameters together, voltage, capacity, ionic mobility, and electronic mobility, tells you what is the power that is at which we are, charging and discharging the battery. And most important, the stability of the molecule. So in case of lithium-ion battery, we will talk about the stability of the electrode materials. In case of redox flow battery, we talk about the stability of the organic redox moiety or inorganic redox moiety that we are using in the system. And there's one difference between this regular battery and the redox flow battery. The regular battery, it's totally packaged. That means the amount of material that is available on the electrodes are fixed upfront. Yeah. So the capacity of the battery is also fixed. You can't increase or decrease once you package the conventional battery like lithium-ion battery that we are using. Whereas in flow battery, the charge is stored in the electrolyte. Okay, we have an anolyte which flows in the anode side, and we have a catholyte which flows in the cathode side. Okay, the charge is stored in those electrolyte, and we use some inert electrodes like carbon, okay, to do the electron transfer reaction by passing the electricity. Or while withdrawing the electricity from the cell, you have to again still pass the anolyte and catholyte and do the reverse electrochemical reaction. Right? So that's the difference. Since the electroactive material is located outside in the tanks, you can increase the capacity of the tank, volume of the tank. Okay, thereby you can increase the capacity of your battery, independent of the power capability of your battery. So the capacity decides energy, right? So the energy and power of your battery can be decoupled in case of redox flow battery, and which is not possible in case of conventional battery. So that is the reason why redox flow batteries are very interesting, especially for the applications where the energy density or power density is not really a matter. For example, redox flow batteries are used where it's a good choice where you are harvesting the renewable energies like wind and solar, because the wind and solar are seasonal. That means they may produce electricity at a time that we don't want. So feeding excess electricity into the grid probably destabilizes the grid. Hence, the excess energy has to be stored for later use when there is a demand. How do you do that? You need a medium to store the energy. Okay, that is where the redox flow battery comes into picture, because this is going to be stationary, so the weight of the battery doesn't matter. So we can place as big as you want around that windmill. So harvest that excess energy and convert it into a chemical energy and store it in the bottles. Okay, so whenever you need, you can extract the energy from those bottles. So that's the advantage here. Even those energized liquids can be transported from one place to other place and can be used for extracting electricity later. So that is the advantage with this kind of a system. So therefore, it's more suitable for harvesting energy from the renewable sources for later use, right? So in case of lithium-ion battery, we have an anode and cathode. So this is y-axis is energy axis. So this tells you about the Fermi level of your anode and cathode. You need to choose electrolyte such that the LUMO, lowest unoccupied molecular orbital of your electrolyte, is above the Fermi level of anode. Otherwise, lithium will reduce your electrolyte. Electron will transfer from, if LUMO is below this anode, then electron will transfer from the anode to LUMO, then your electrolyte will get reduced. Similarly, in the cathode, should be such that its Fermi energy level is above the HOMO, highest occupied molecular orbital of your electrolyte. HOMO is already filled. It has 2 electrons in those orbitals. So it's all paired up and is filled. So it won't accept any more electron. Therefore, the electron transfer from cathode Fermi level to the HOMO of your electrolyte is not possible. Therefore, this cannot reduce your electrolyte. So this is how the optical gap or HOMO-LUMO gap of your electrolyte should be if it has to operate with lithium and lithium cobalt oxide kind of electrode materials in lithium-ion battery. Same applicable for redox flow battery as well. In redox flow battery, we use an electrolyte such that which is stable at the potential window in which your cell operates. Okay, when it's aqueous-based system, mostly 1.2, 1.3 volts is what the stability window of your water. That again depends on the over potential that is involved for the hydrogen evolution and oxygen evolution on the given electrode. So if you choose electrodes which offer more over potential, enormous over potential for hydrogen evolution, like mercury, it exhibits a huge over potential towards hydrogen evolution, right? So if you choose electrode materials such that they exhibit huge over potential towards hydrogen evolution and oxygen evolution reaction, then probably you can stretch the voltage to 1.5, 1.6 volt, and so on, even with the water-based system. And we need some metrics to understand our system. Okay, so one is voltage efficiency, which is a ratio of the average voltage during discharge to the average voltage during charge. Similarly, there is something called Coulombic efficiency, which is a ratio of the charge you extract during discharge versus the charge you deposited on the system during charging. And energy efficiency is a product of Coulombic and voltage efficiency. So these parameters should be as close to 100%. Then your system is perfect, right? So other important parameter that we talk about is C rate. C rate is the rate at which we are charging or discharging the cell. For example, if I have 1 C rate, that means the entire battery, the capacity of the entire battery, so you can achieve or you can charge the entire battery in 1 hour or discharge the entire battery in 1 hour. That's called 1 C rate. 2 C rate means you do the entire charging of the battery in half an hour or discharging of the battery in half an hour, right? So 0.1 C means you do the charging of the battery in 10 hours. 1 by 10 is 0.1, right? Or a discharge of the battery in 10 hours. So higher the C value, like 3C, 4C, 5C, better is the, for us, because we can quickly charge or discharge the system, okay? And then we also worry about energy density, which is often reported in watt-hour per liter or watt-hour per gram. And this slide tells why we need RFB at all, redox flow battery at all, because there are systems like pumped hydro or compressed air, that is stored underground. But those are very massive systems. They need a specific landscape, and this cannot be turned off or on very quickly. So the response time is very poor. It takes a long time, So then the other option is flywheels or supercaps, but these can charge or discharge very quickly, but the amount of charge it can store or the capacity these systems offer is very limited. Therefore, the energy content in these systems are very limited. Their power capability is good, of course. So these are also not very impressive, because when you have a large amount of energy is produced in the windmill or in solar panel, it may be like you may have to store energy that is harvested for many days or many weeks. Okay, so in such situations, flywheels and supercapacitors are not really ideal choice. So in that case, redox flow battery is a good choice, because if you are intending to store more energy, then you simply increase the electrolyte volume so that you can store more energy, which you can do from outside without touching the cell. And as we know, worldwide, the installation, PV installation or windmill installation growing up. In India itself, we have about 41 gigawatt of solar power installed. Okay, so therefore, there is a need for intermittent storage platform like redox flow battery badly. And this particular slide has some animation. This tells you how this redox flow battery works during charging. In this case, I'm going to show you a vanadium redox flow battery, where vanadium 2 plus and 3 plus are the anolyte, are the species in the anolyte, and vanadium 4 plus and 5 plus are the species in the catholyte. So 4 plus is blue in color and 5 plus is faint yellow in color. So you would see the color transition shortly. And in the anolyte, vanadium 3 plus is green in color and vanadium 2 plus is purple in color. So when we start charging this battery, as you could see, vanadium 4 plus turning into vanadium 5 plus, and vanadium 3 plus goes to vanadium 2 plus. So the electron which is harvested this side is deposited in the other side of the cell, so that vanadium 3 plus goes to vanadium 2 plus. This happens at minus 0.26 volt, and this catholyte reaction happens at 1 volt, so the difference is about 1.3 volt. That's a typical voltage that you would get from a vanadium redox flow battery, right? So during discharge, the opposite will happen. Vanadium 2 plus will go to 3 plus. That means oxidation will happen at this side. And vanadium 5 plus will go back to vanadium 4 plus. That means reduction. So these are the color of various solution that is involved. This video shows the components involved, like a flow field plate and the electrode, which is a graphite felt. And then we place a membrane above the felt, and then the one more graphite felt electrode and the flow field and so on. So here I have shown some, I think about 6 or 8 cells containing stack, which is powering the LED panels around it. So this is one of the battery that we have developed as part of a DST SERI program. So we developed about 320 watt stack, and currently we are in the process of making 1 kilowatt, 10 kilowatt hour stack, which is a ONGC funded project, which we are doing it with the high energy batteries in Trichy. And this slide compares the various technologies, the cost of various technologies. When it comes to a large installation like the one we are talking about, what is important is the levelized cost of energy storage. How it is calculated? You need to consider the total lifetime cost of the investment. That means how much it costs to put the redox flow battery and how much it costs for you to maintaining that or to replace the electrolyte in that time to time. Yeah, all that you have to add. Say if I'm aiming for 20 years, you have to add all this cost that you incur for this 20 years. Okay, right? So that you take it and divide that by the amount of electricity which is delivered by this system, because you are repeatedly charging and discharging. So you keep adding every cycle, you are keep delivering some amount of electricity. All that you add, cumulative of that for 20 years. So you divide by the total energy that is delivered by the system in this 20 years. Okay, then you get the levelized cost of energy storage. Okay, that is what compared here. Okay, this is in dollars per megawatt hour for the system which is capable of going for different duration. As you could see at very low durations, there's not much difference between the lithium ion or vanadium or pumped hydro and so on. As you go for larger and larger duration, you see really pumped hydro and sulfur stand out in terms of cost. Vanadium is little lower than lithium ion, but not really very different from the cost of lithium ion. But it's interesting because in aqueous chemistry, safer to operate. You will not have a thermal runaway problem or fire hazard with this system. And vanadium again is not available in our country. So if you want to have a a reliable energy economy, then we need to depend on the materials which are available in our land. So with that interest, we were venturing into organic redox flow molecules which can replace this vanadium without sacrificing on the performance and so on. So you would see some of the examples I will discuss. So we discussed about what is the levelized cost of energy, and there is something called fade rates. How much capacity you lose every day? That's called fade rate. That should not be too high. It should be in the range of 0.02 to 0.1. That's kind of acceptable. Probably in that case, the economics will work out. Then this technology may be feasible to implement in the field. Okay. So the improving the energy density, it is linked to the how much of redox molecules you can dissolve in the electrolyte. If a redox molecule is sparingly soluble, right, then your capacity will be limited by the solubility of your molecule, right? Then the energy is nothing but the capacity times the voltage, right? So therefore, it is important you dissolve enough, redox molecule into the electrolyte. Therefore, enough charge can be stored, so the enough energy can be stored or delivered by the system. So solubility is one of the important factor along with the voltage in this kind of flow battery system. So some of the flow chemistry which are well known, that is quinone, hydroquinone based chemistry. We know that quinone can undergo gem diol formation, or it can undergo Michael addition and form this kind of trihydroxy compound. This process, gem diol formation, will kind of affect the kinetics of quinone going to hydroquinone. Okay, quinone to hydroquinone is a 2 electron 2 proton process. Yeah, it may affect it because this is a reversible. So it won't affect the capacity, but it can affect the kinetics. Means how fast or how slow you can charge the battery. Whereas these two process here, which we call Michael addition, can degrade this material, therefore lead to loss in the, or therefore lead to higher fade rates, right? That's a problem. We don't like a system like that. And there are other degradation mechanisms are like a nucleophilic substitution that I have shown here, or hydrolysis of this amide bond, which I have shown here. These are the ways by which these organic redox molecules might undergo degradation. In this case, I have shown a disproportionate reaction, how it forms a two different product, which probably may not be reversible, for the electrochemical purpose. In this case, methyl halogen. Okay, so this can undergo oxidation and form a dimer and so on. Or you may have a tautomerization. Again, tautomerization is a reversible process, therefore it will only affect your kinetics, not the capacity so much. Okay, so the theoretical study published indicates that whenever we design a molecule which has a redox potential over 0.9 volt, okay, then it becomes susceptible to this Michael addition problem. Okay, and then the molecule degrades, the quinone degrades into something else. So this is an issue, right? So how do we address this problem, and how do we make a molecule which is cyclable, stable for a long time or for many cycles? So this is a work from Professor S.R. Narayan's group, Southern California. What he has done is, he has taken a molecule. So in this case, it's a dihydroxy compound here, hydroquinone, ortho dihydroxy compound. So in order to as such, this molecule has got lesser solubility in acid medium, sulfuric acid medium. So he has attached two sulfonic acid groups, so that when you drop into the aqueous system, they ionize and improve the solubility of this compound. That is the idea. So, but these two sulfonic acid groups are not the redox center. Redox center is this. So when you oxidize, only these two OH groups will undergo oxidation and form orthoquinone. Yeah. So this is about 0.85 volt with respect to normal hydrogen electrode. But there is a problem here. The problem is these sulfonic acid groups are electron withdrawing in nature, right? Therefore, it will deplete the electron density at the core of this benzene ring. Okay. Therefore, that 4,5-dihydroxybenzene 1,3-disulfonic acid, okay, reacts in the quinone form. Quinone form means this form here. Reacts in the quinone form to the water to form 2,4-trihydroxybenzene 1,3-disulfonic acid. How is that happens? You see the mechanism here. Because the ring is depleted of electron, so water, it's a very good nucleophile because oxygen has two lone pair in water. So it will donate those electron and then undergo this addition reaction. By the way, we all know from our lower class that we have learned, addition reaction is very, very difficult. Almost won't happen on aromatic system because aromatic systems are very stable. They got a special stability, right? Whereas once you oxidize this, it loses its aromaticity. So this is a kind of less stable compound compared to this. Therefore, the addition reaction happens on this easily. So water can attack only this kind of a molecule, which is not aromatic. Whereas this won't attack this. There is no nucleophilic addition reaction here, whereas this happens here. And you can see here, this forms a trihydroxy compound. So this will reduce the potential of the system. Also, it may reduce the solubility and so on. So then what's the way to solve this problem? What he has done here, in this case, he has taken a para-hydroxy compound, yeah, and then he has put a sulfonic acid group for the solubility. Instead of 2, there is 1 here, so that the extent of electron withdrawal from the core can be limited. But in these two positions, because those are the positions where Michael addition was happening, so he has blocked it with the methyl groups. But methyl group, remember, it's an electron donating group. So methyl group will enrich the electron density here, whereas sulfonic acid will deplete. What happens here is this compound gets protonated in acidic medium, and then you can see it undergoes a resonance, and then finally the positive charge comes at the methyl methyl group attached carbon. And here this process leads to leaving of this sulfonic acid group. This is called proto-desulfonation. Generally, organic chemists use this as a way to, if you want to protect some position in organic compound, they will introduce this group. And when you want to deprotect it, they leave it in the acid medium. So automatically a proto-desulfonation happens and the sulfonic acid group leaves and you get this compound. So this compound is sparingly soluble again because what was giving solubility to this compound, the addition of sulfonic acid group was giving solubility to this compound. Now it becomes sparingly soluble because of the side reaction. And if this happens, then the capacity of the battery will come down again. So So that's not a good solution, right? That's not a good solution. Now, what we have done in our group is we have designed some new redox molecules. So instead of sulfonic acid, this is highly electron pooling. So we used this dimethyl amino methyl substituent on this hydroxy compound. Okay, this one in acidic medium will undergo protonation. This amino group will undergo protonation. Therefore, it will bestow the solubility to the compound. And since we have a methylene bridge between this nitrogen and this core, we expect the electron pulling by this protonated amine will be less compared to sulfonic acid group. So likewise, we have made several compounds. Here you can see this is a piperidine based substituent. This one is a methyl piperazine based substituents, right? So these substituents are there mainly to improve the solubility. So they don't do the redox chemistry. Okay, so these are the OH groups which undergo oxidation and produce quinone, and during discharge the quinone to hydroxy compound again. What we did is we made these molecules and we coupled them with vanadium 3+ and 4+. Okay, so in the analyte side we'll have vanadium 2+ and 3+. Okay, the vanadium 4+ and 5+, we will replace it with these organic molecules because they are having voltage very close to vanadium 4+, 5+ couple. Therefore, only half of the vanadium we remove in this process. So the anode we have 2+, 3+. In the cathode we have these redox active quinone hydroquinone molecules. And it's very important to decorate them like this with the functional groups. Otherwise, they will undergo Michael addition process. And this group has a free rotation. Therefore, it will try to minimize the approach of this water nucleophile to this meta position to this OH group. So this is a very simple reaction. You take this hydroquinone and then you can do a one-step Mannich reaction, and that Mannich reaction would give you these products. Okay, so electrochemistry involved here is this hydroxy compound undergo to electron to proton oxidation and produce a quinone, and during discharge quinone will become a hydroxy compound again. So I have shown with the other molecules also similar chemistry. So what we have done here, we have taken the cyclic voltammogram. What is cyclic voltammogram? It is the potential versus current versus potential graph, wherein we will keep on switching the potential linearly at certain scan rate, certain millivolt per second, and then see how the current changes against this applied potential. So this for this hydroquinone compound, this black one. So once you substitute with the methyl group, methyl is electron donating. Therefore, the core becomes electron rich. Then it should be easier to oxidize that molecule. That's why this peak is at lower potential than this black one, because it's easier to oxidize. So this dimethyl amino methyl substituent one exhibits little positive potential than the reference case. The reason why this protonated amine is positively charged, that kind of exhibit a minus I effect and pulls the electron through the sigma bonds. And when we use this one, because it has got more nitrogen than this, so the peak further shifts. But you will notice when I make it more bulky, you can also see the peak current is kind of coming down because such a bulky molecule will have difficulty in accessing the electrode. So if it has difficulty in accessing the electrode in right orientation, then you will not have electron transfer happening effectively. So you have to be careful when designing molecules. Just at the cost of blocking this or at the cost of increasing the solubility, if you decorate too much, probably the redox reaction itself will not happen. In fact, when we blocked these two sites later with the methyl group, we found that becomes redox inactive. Okay, it's not at all able to exchange electron with the electrode. So that was the issue that we faced. And this particular slide shows the cyclic voltammogram recorded for 100 cycles. So these molecules are very stable. So we thought, okay, we can go for the battery because this molecule seems to be very stable in sulfuric acid medium. And we have gone ahead and did this experiment at a different scan rate. So this is an oxidation process. This is a reduction waves. So done at a different scan rates. So we can use this Randall-Sevick equation. So we can take the peak current, okay, plot it against the scan rate. So from the slope, you'll be able to calculate the diffusion coefficient of these molecules. Both oxidized and reduced form has nearly similar diffusion coefficients. And this is actual battery that we made. You can see here one side the organic compound, other side is vanadium 2+, 3+. The battery is running. You can see it is able to drive the load, which is a fan that is attached to this battery. Okay, so what's the chemistry here? In the cathode side, in the catholyte side, this organic molecule oxidizes to quinone during charging, and in the anolyte side, vanadium 3 plus becomes vanadium 2 plus, is a reduction. During discharge, opposite, 2 plus to 3 plus, and this quinone to hydroquinone, right? So, and we did the full cell charge discharge. This is a charge discharge curve, constant current density. So it is done at 10 milliampere per centimeter square using 25 ml of solution on either side. You could see it only survives for a few cycles. After that, the battery kind of loses its capacity. And we were worried what is going on because the solution become very, very yellowish in color. The membrane, which is Nafion membrane that we used, also picked up some of those color. We thought, okay, the membrane is blocked. So we replaced the membrane with a new membrane, but the performance didn't improve. That means something happening in the solution itself for this molecule during charge discharge. So this shows us a UV visible spectrum of this hydroxy compound and this quinone compound. So the hydroxy compound, when you let it stay in acid, even for 120 hours, there is no change. You see the same pi to pi star peak here, and there is no shift in that. Whereas this keto compound undergoes a shift. Okay, it becomes more aromatic now. So why? How I'm saying is becoming more aromatic? You can see there is a red shift here. And also you can see in the cyclic photometry, there's a new peak developing at around 0.2 volt. Earlier it was giving at around 0.7 volt. Now it is new peak at around 0.2 volt. That clearly tells something forming out of this, and that compound is easier to oxidize than this compound, easier to oxidize than this compound. So what is that compound could be? That means there is some transformation happening to this molecule. So this again a visible spectra of these three species. As you could see, there is no change when you compare this and this because this is at 0th hour, this is taken up around 20 hour. Whereas this quinone compound, this is just a quinone, paraquinone. You can see this peak shifts really to around 290 nanometer or so. But the methyl substituted ones, there is not much shift in the peak position, although I see slightly a shoulder absorption in the around 400 to 450 region. But it's not really degraded like the black case, right? Like the quinone, paraquinone case. That's because the methyl groups donates electron, makes this ring electron rich. Although this is not aromatic compound, so it can undergo Michael addition. Because this core becomes electron rich, it kind of impedes this water attack or a nucleophilic attack. Whereas here again, because this is a positively charged mide, it pulls electron out of the system, so it is susceptible to Michael addition. You see this blue one is also showing a shift. So we see our substitution did not yield what we wanted. So probably you may have to protect more those meta sites. Otherwise, probably it will be difficult to proceed with this molecule for a flow chemistry. So this is the Michael addition, the mechanism by which it happens. So the water attacks here, and then there is a series of transformation. You get this kind of trials into the system. So in our case, because we left these two positions empty, hoping that this group, when it spins, probably avoid water coming close to this point, but it did not happen. After some time, eventually, the Michael addition happens in our molecule. So what are the ways by which we can improve the performance? We can block all these positions. We can also extend this methylene bridge. Instead of one, we can have a 2 methylene here. The reason why then the minus I effect of this protonated amine will be reduced. So core will not be affected, right? Or we can have this kind of substitution. You may also have asymmetric substitution. You see here, this is NCH3, this is N-ethyl, right? What is the advantage of this asymmetric substitution? Because it will reduce the packing of this molecule. Therefore, the solubility of this molecule will be better in aqueous solution. That's the idea here. And these nitrogens are here to improve the solubility because they get protonated. And what we have done, we understood that forming quinone from hydroquinone is always a problem, no matter what you do, because when you go and put these two methyl groups as I shown here, this molecule itself is becoming redox inactive. Because of this heavy decoration, it is not going in close proximity to the carbon electrodes, and then electron exchange is not happening. But chemically, the quinone form can be converted into hydroquinone form. But the problem is this hydroquinone form is very difficult to oxidize, so that we can't start the battery with this chemical. Then we thought about it. What we did was we still have quinone, okay, but now we make this quinone as part of this aromatic system. This is an azine, pentazine. Okay, this is an aromatic compound. So since it's an aromatic compound, it's very stable. No addition reaction can happen. So water cannot attack this compound. So that is the idea that we thought. So we have used this molecule and we have developed a zinc anode and pentazine tetraone based cathode, and we could cycle this compound for nearly 5,000 cycles. Okay, so this is the charge discharge of this compound when you use a simple super P carbon, and when you change the carbon to something called CMK3, it's ordered mesoporous carbon, we had a better charge discharge capability. In fact, this compound, this formulation allowed us to go for up to 63C, very fast charge discharging. That means within a minute you will charge and discharge the battery to its full capacity. This one, for example, as I told you, this alpha beta unsaturation that was present in quinone now become the part of the aromatic system, so it cannot undergo any substitution reaction, right? Aromatic substitution reaction, nucleophilic substitution reaction, it cannot undergo. Okay, so that's the idea. So we made the battery, we went up to 5,000 cycles, and we had a stable performance, and we have tested it at different current density. Okay, and we found it is really stable. So our idea of making this alpha beta unsaturation of this quinone as part of the aromatic system has paid very well for us. And this is from an ADZIC. So he has used this kind of anthraquinone, and these two were OH groups, but in basic medium they get deprotonated. So this dianion during charging goes to tetraanion, and this tetraanion is highly unstable. Okay, that can undergo disproportionation, and this tetraanion can become anthrone. Okay, this is the issue. So they don't know how to stabilize this molecule, and this anthrone can become a dimerase and form a compound. If this compound forms, it is an irreversible process, then you will not be able to go back to this original compound. So the electrolyte will go bad. So one of the solution given was we can aerate at this stage, and then this compound can go back to this. But if you aerate it, then you will lose all the charge that you stored. So it's not really a viable solution for this battery. So you can see here the original compound showed a nice redox peak, the black curve, and the red one is for this anthrone. Once it anthrone forms, it loses its redox activity. But if you aerate it, it goes back to the original compound, so that the blue one shows it gains the the redox property once you aerate this molecule. That means it's producing back to this compound. So we wanted to solve this issue. So what we did was we have shifted this OH group from here to this position here. Okay, a beta position from this keto group. So that's what we have done. And then you can see here we have made some model compounds. So this is called jugulone, naphthalene. This is anthrarufin. Okay, in all the cases we brought these OH groups close to that. So in this compound we had only one OH group because we wanted to see what is the influence of this OH group. These compounds show a nice CV, except this jugulone is kind of showing very quasi-reversible kind of a peak. That's because we don't have OH group next to the ketone. The OH group kinds of forms a 6-member ring through hydrogen bonding and activates this carbonyl group. So therefore it undergoes easy reduction. Since on side we are missing this OH group, so it was quasi-reversible compared to other two compounds, which are two hydroxyl groups. We can couple this compound as anode material with a cathode material called ferrocyanide ferricyanide, and we can make a complete cell of about 1 volt. That's the idea here. And here you can see the naphthalene and anthrarufin. They were able to produce up to 1.1 ampere hour per liter of capacity at 20 milliampere per centimeter square. So that's very close to the theoretical capacity of those molecules. Whereas Juglone, which also has got 2 carboxy groups, so it is capable of undergoing 2 electron reduction process, but it gave only half of the capacity of what other 2 members gave. That's because one of the carbonyl groups never get activated in this molecule in absence of this OH group. Okay, and we have done several cycles and it was giving a stable capacity over the time. In basic medium, what happens is this potassium ion that is present gets coordinated with these oxygen functionalities. Thereby, it stabilizes this. So when it forms a tetraanion during charging, okay, in acid case, it was getting decomposed or disproportionate, right? But here it doesn't undergo any disproportionation because this is stabilized by this potassium ion nicely by electrostatic force here. It's kind of crown ether, chelating the alkali metal ions, right? Something similar to that. So you have these oxygen acting as a ligands and coordinating with this K plus ion and then getting stabilized. So this is how we avoided the capacity decay in this battery. Very simple shifting of OH groups to one position to the left. And then the problem there was we didn't have enough solubility of this compound, therefore we were limited in capacity or energy density. Therefore we decided to functionalize this. So one of my students put 2 sulfonic acid group here, therefore the solubility goes up. Okay, and again this will not undergo any Michael addition, although it has sulfonic acid group, because I told you this alpha beta unsaturation now become the part of the aromatic system, so it has a special stability. So these 2 protons, the red one and blue one, are between this keto and sulfonic acid group. That means they are highly de-shielded and their chemical shift is very close. In that case, you will see a nice roof effect out of these 2 protons. You can see this roof effect. So this NMR confirms, okay, this compound is formed. So what next? We take this compound for the cycling, and we could see this compound is slightly quasi-reversible compared to the original compound, which did not have the sulfonic acid group. The reason, again, once you heavily degrade the molecule, the electron transfer also becomes a problem, because these functional groups will come between this carbonyl group and the electrode, so that electron transfer during reduction is a problem with these kind of molecules. So this thing has to be taken into account while decorating these molecules. So we did this, and then we have seen the solubility can be improved from 30 millimolar to 100 millimolar. Therefore, the capacity also went up from about 1.5 ampere hour per liter to about 4 ampere hour per liter. So molecule had a 30 capacity of 5 ampere hour per liter. We almost achieved 4/5 of that capacity, and this is very stable. We don't see any degradation in capacity with the cycles, and very good coulombic efficiency we get with these molecules. So our idea of making this alpha beta unsaturation as a part of this aromatic system has worked in 2 systems. The earlier one I told about pentacene tetra1, and in this case this anthrarufin molecule with the sulfonic acid substitution. We have done this. So this we call it as a molecular engineering. So how do we engineer the molecule such that the issues, one of the main issues we face is a Michael addition that we could prevent. And recall about the pentacene tetraone, and now compare with this molecule here. So both have some similarity. Both are aromatic, and both have this quinone groups, whereas this has 4. This has 4 keto groups. Here it has 2 keto group. Okay, so this is a similarity here. So what's the advantage when you have more keto groups? Okay, the voltage of the system will go up, because pulling the electron out will be very difficult. So the voltage of the system will go up. So we can see here the cyclic odometer of this compound shows a redox peaks at around -0.8 volt, whereas this compound and its corresponding reduction product is the hydroxy compound, right? That's a redox couple here. So this shows at around 0 volt. So about 800 millivolt positive is the potential of this molecule. That's because of the additional 2 keto groups that present. But yet this molecule is very stable. They don't undergo any degradation. I have increased the potential, but there is no degradation. Whereas in the beginning I told you, whenever you have a potential of about 0.9 volt versus NHE, those organic molecules kind of undergo Michael addition very easily, right? So here we have shifted nearly 800 millivolt, but there is no degradation at all. The molecule is very stable. That's because of this aromatic nature of this keto. Again, there are ways by which we can improve the performance. We can have asymmetric substitution, or we can have this kind of functional group to increase the solubility of this molecule so that energy density can go up. Okay, so and the last one, for example, here you could see, yeah, in this case. So I have introduced a methylene bridge here, and instead of sulfonic acid groups, I introduced also a carboxylic acid group. Carboxylic acid is another very good, group for improving the solubility of these molecules. So we can improve the solubility by this kind of substitution. But again, the heavy substitution around these molecules probably might cause this Michael addition kind of not Michael addition, but electron transfer issues during the charging and discharging of this process. So the one problem that we yet to address is how to have a functional group which makes this molecule soluble. At the same time, it will let this molecule undergo redox reaction at the electrode-electrolyte interface. So one of the issue in this case, whenever we have the groups like this kind of carboxylic acid or sulfonic acid group, like in the previous case here, let me show you. Yeah, these kind of things. Yeah, they get in water system like in aqueous sulfuric acid. So these guys can get hydrated because SO3 minus, so it may also get hydrated. So once it get hydrated, again the distance between the electrode and the species goes up because these water molecules which are hydrating this molecule, in case of other solvent, we call it solvation. So solvation of this molecule also has a role to play on the electron transfer kinetics of this molecule. So those are the things that we should bear in mind while designing these molecules. So our future interest would be finding a moiety or a substitutional or functional group such that it will not impede the electron transfer. Okay, it will not impede the electron transfer. At the same time, improve the solubility so that we can get the enough energy density out of this material. So substituting with electron withdrawing groups obviously increase the voltage, so that's advantage. Your battery voltage can go up. And you could see my students here. Some of them are missing here, but this is a really old photograph. But what I want to do is end this seminar with a famous Ragon plot. The Ragon plot is nothing but a power density versus energy density graph. So we always want a system which is full of energy, right? That means energy density should be as high as possible. At the same time, that system able to deliver that energy quickly. That means power should be also higher. That means we look a system in this region. So in the top right side corner of this plot, right? In this region is what we look for a system. So that is why we keep working on it to improve the energy density and power density of the system. For example, supercaps are very good in terms of power density, but they are very poor in energy density. Fuel cells, for example, very good in energy density, but very poor in power density. But we want to have both the characteristics in one system. Okay, so how do we do that? The answer to that question is my students, because they are the one who work with me day and night and then identifying new molecules, new chemistries, right? So the alpha beta unsaturation, making it as a part of the aromatic system was done by Chinmay, who is here. The other organic molecule where I had this quinone decorated with dimethyl amino methylene kind of substitution was done by Jagdishwari. She is a postdoc with myself and Professor Indrapal Singh. And there's one Mr. Raja, is my postdoc. He's also working on this kind of chemistry. So I thank all my students for the wonderful work they carry out in my laboratory, and also the funding agencies who are amply funding our research. And I thank you all for patiently listening to my talk, and I'll be happy to answer if you have any questions. Over to you, sir.
Okay. Yeah. For EDLC and pseudocapacitor. Okay, because I have not presented anything on capacitance right now. But if you want to estimate from the cyclic voltammetry, we know that the capacitance C is Q by V, that is charged by the voltage window V, right? So the numerator going to be dq by dt, and your denominator going to be dv by dt, right? So what is dq by dt? That is charge by time, that is current. Okay, so in your cyclic voltammetry, you get the current, right? And what is the dv by dt? That is scan rate. So at particular scan rate, you have a particular current. Generally, if it's a EDLC type capacitor, it will have a rectangular shape, nice rectangular shape. If it is a pseudo capacitors, you may have additional peaks embedded on that. So let us take the case of EDLC. Okay, so in that case, for each scan rate, you will have a particular current, and the current will go up with the square root of the with the scan rate. Current is proportional to the scan rate. So if you take that current from the cyclic voltammetry, that means anywhere in that flat line, right? So when you run the cyclic voltammetry, you have a rectangular shape curve that is coming. Your y-axis is current and your x-axis is the voltage, right? So you take that current and divide that by the scan rate that you have used. That will give you the capacitance, because that is nothing but capacitance C is the dq by dt by dv by dt, that is scan rate, right? So current divided by scan rate will give you capacitance. Or you can take the charge. What you can do, the cyclic voltammogram, instead of plotting as current versus voltage, you can plot it as a current versus time. Then you can integrate the area under that rectangle, right? That will give you charge. So take the charge and divide by the voltage window that you are using. That also will give you capacitance. Both will give the same value. Yeah. So Divya, did I answer your question?
Yes, sir. Yes, sir. Double A capacitance was clear, and for pseudo capacitor, we get a PC. So,
What you should do for pseudo capacitance, you follow the second method. You plot current versus time. The CV itself, you can plot it as a current versus time, and integrate the area under the curve. That will include your double layer charge as well as the charge under the peak. Correct?
actually, I got a question from a reviewer. He is asking me to calculate the charge density from cyclic voltammetry for pseudo capacitor.
Yeah, you can do that. Yeah.
From cyclic voltammetry itself for pseudo capacitor instead of current versus time. From cyclic voltammetry itself, I can calculate current density from cyclic voltammetry for pseudo capacitor.
You can. So in pseudo capacitors, you will not have a perfect rectangular, profile for IV, right? So you will have some humps here and there, some peaks, right? So all you need to do is you have to extend that background current so that the peak can be isolated from the rectangular region, correct? And then the area under the peak alone, if you calculate, that will give you the charge, okay? And divide by the area, it will give you charge density, correct?
Thank you, sir. Thank you.
Yeah. Yeah, hope the video went well. So, okay, because I just wanted to make sure. Yeah, because outside I don't know about the internet connectivity. That's why I just gave you. So that way we are sure that it will play well. Yeah. Okay. So hope students benefited. Although they didn't ask much questions, but I hope they will think about this, these kind of systems, and then work on such systems. Okay. Yeah.